touch, a little bit. Listen, I know it starts early in the morning. I'm waking y'all up. So, but you have to go in and configure everything from interface to interface if you want static routing, a direct line of sight to your next router. Yeah, it's a lot of work. Now I have a question for you first thing in the morning. It's a light question. I know you're still yawning. What needs to happen if you want to configure? Well, I don't want to say what needs to happen. Who needs to own the devices in the middle in order to do static routing effectively? I think that's the way I wanted to say that. Can I just jump in somebody else's network and do whatever I want to their items, Martin, Mr. B, Leah? Or does it help if I own them? Yeah, Leah's like, yeah, sounds right. Sounds about right early in the morning. Sounds like you need to own them. Yeah, you're right. You're right. So here's the thing. You either paying a subscription to work with that item, like cloud services. Correct, Mr. T. Infrastructure as a service. So if it's in the cloud, you either have to pay a subscription to get these devices and own them under your domain or control them. You need to control them under your domain. You've purchased them, and your IT is facilitating these devices. Or, here's the last one. You have no association with the other company, but you get special permission through their IT in order to access or configure something. It's a relationship. It's a have-to-have relationship, so they let you do it. Okay? So those are the only 3 ways you're going to be able to do it. All right. So that's where we're going to be going into today. Don't forget to clock in, y'all, if y'all didn't already. So we'll also be hitting 101 labs in Net Plus. So it'll further explain or enforce what we're going to be talking about this morning. We're going to do that later this afternoon. Pick a lab, go through it, bring up NetCat Academy, and go through it. Around 1400 or so, we'll do a breakout study hall for about an hour. But today, probably this morning when we're done with the lesson, we'll go ahead one by one and start. Or I'll just send out all of your vouchers and y'all schedule the Net Plus exam. Because I think y'all are pretty savvy on scheduling an exam right now. I don't think anybody needs like a one-on-one to do it. So I'll just send out vouchers and then everybody could schedule the exam at one time. How's that sound? We'll do that before lunch. All right. Any questions for me so far? Anything from yesterday? Did y'all get the email though? Did you get the email? Yeah. Word up. Hey. Okay, tomorrow, so it won't be a shock. We got to do something first thing in the morning. As a requirement, us being a higher learning institution, we have to do something that's mandatory tomorrow, all the students. It's called what they call Constitution Day. We'll see this in the morning. Constitution Day is a lesson that I should facilitate about 15 minutes, going over some information about the U.S. Constitution, when it was signed, talking about Mount Rushmore, just history about the United States. Okay? With this, there's a requirement, there's a crossword puzzle, something fun to do. It's an exercise that counts as your attendance. You hand it in, saying that you were here and you did it. During the Constitution lesson, I ain't going either right nor left. I'm just going to straight teach down the middle what the thing is. I'm not even going to ask opinions. It's just a requirement. So I'm setting the stage to say it's just a neutral lesson. Does that sound good? Something that we all have to do. I have to teach it. We need the students to complete the crossword puzzle. and hand it in. Does that sound good? I just don't want y'all to be surprised when you see it in the announcements in the morning, like, what is this? Yeah, it's something that we all have to do. So leave it like that. All right, y'all ready to get started this morning? We'll drop some emojis then. Y'all drop some emojis. I want to see some emojis. Come on. The more emojis I see, the more I get active. That's what I'm talking about. Give me some motivation to get going this morning, people. Yes. All right, so what we're going to do this morning, yay. Thanks for playing along. We're going to be talking about, let me bring it up on the screen. I'm going to play this nice little YouTube video. It's called Routing Protocol Simplified. BGP, OSPF, RIP. Right? Border Gateway Protocol, Open Shortest Path First, and RIP. Routing IP Protocols. You might see a commercial in here once or twice. It's almost 20 minutes long. But it gives you more simplified background of why we have routing protocols, where they originated from, and you'll see AT&T, Cisco, these companies have created this stuff since the internet had come about. Okay, so they were on the ground level creating all of this stuff, which we now use today. So without further ado, we'll go into this and then we'll break into the lesson in a minute. Ichabod could pick the right screen.
Ever wonder how your favorite YouTube video loads so fast? Or how a simple message travels across the world in seconds? Behind the magic of the internet are routing protocols. Routing Information Protocol, RIP. Open Shortest Path First, OSPF. And Border Gateway Protocol, BGP. Acting like expert traffic controllers, ensuring your data takes the fastest and most efficient route. These protocols keep the digital world running smoothly, from your home network to the global internet. Today, we're diving into how RIP, OSPF, and BGP work to keep us connected every second of every day. If you're passionate about tech and want to learn more, make sure to hit that subscribe button for more deep dives into networking and technology. Here's the roadmap for what we'll cover today. We'll begin with an introduction to routing itself, what it is, why it matters, and how it functions in a network. Then, we'll move into an overview of the three main dynamic routing protocols, RIP, OSPF, and BGP. We'll dive deep into how each one works, their strengths and limitations, and finally, we'll compare these protocols to help you understand when to use each one.
Wouldn't it be nice if work was just smooth? It can be. So,
Hi, welcome to Knowledge Catch. In today's episode, we'll break down the OSI model, an easy way to understand how... Ever wonder how your favorite YouTube video loads in with an introduction to routing itself, what it is, why it matters, and how it functions in a network? Then, we'll move into an overview of the three main dynamic routing protocols, RIP, OSPF, and BGP. We'll dive deep into how each one works, their strengths and limitations, and finally, we'll compare these protocols to help you understand when to use each one. Along the way, we'll look at real-world applications to give you a practical understanding. We'll wrap up with a conclusion summarizing the key takeaways. To understand routing protocols, let's start with the basics. What is routing? In simple terms, routing is the process of directing data from one place to another across different networks. Just like how a GPS helps you find the best route to your destination. Routers find the best paths for data packets to travel across the internet or local networks. Routers use a routing table, which is essentially a map of all the paths data can take, to decide which direction to send data. Now, why does routing matter? Well, without routing, data wouldn't be able to move from one network to another efficiently. Think of the internet as a giant, complex web of interconnected networks. Routing ensures that data takes the best possible path to reach its final destination, whether that's across the street or across the globe. Good routing keeps networks running smoothly, reducing delays and ensuring that data gets to where it needs to be. Routing plays a vital role in keeping data transfers efficient and reliable. When data is transferred, we want it to reach its destination as quickly and reliably as possible. Good routing ensures that this happens by finding the most optimal route. If a direct route isn't available due to a failure, congestion, or maintenance, routers are smart enough to redirect the data through alternate paths. This ensures continuous communication even when there are issues in the network. Routing also supports scalability, which means as networks grow, routing protocols help manage the increased traffic without manual intervention. Imagine a small business expanding from one office to several locations across the country. Routing protocols will adapt to ensure all locations remain connected. On a larger scale, the same principles apply to the global internet, which routes data millions of times every second to keep websites, emails, and online services functioning. Without effective routing, the internet as we know it simply wouldn't exist. There are two main types of routing: static and dynamic. Static routing involves manually configuring paths in the routing table. This works well for smaller networks that don't change often, but it becomes cumbersome as networks grow. For example, in a small home or office network, static routes might be fine because there aren't many routers or changes happening frequently. But if the network expands or changes, each new route will have to be manually updated, which becomes time-consuming and prone to errors. Dynamic routing, on the other hand, allows routers to automatically discover and update routes as the network changes. Routers exchange information with each other to determine the best paths. And when there's a change, like a link going down or a new router being added, dynamic routing protocols automatically adjust the routes. This is crucial for large or evolving networks where manual updates would be impractical. In a way, dynamic routing is like having a GPS that reroutes you when there's traffic or road closures, ensuring you still reach your destination efficiently. Dynamic routing relies on protocols, sets of rules that routers use to communicate with each other and determine the best routes. There are several dynamic routing protocols, but today we'll focus on the three most common ones: RIP, OSPF, and BGP. RIP, or Routing Information Protocol, is one of the simplest dynamic routing protocols. It uses something called hop count to measure the distance between routers. While it's easy to set up, it has limitations, particularly in large networks. OSPF, or Open Shortest Path First, is more sophisticated. It uses a different approach called link state, where routers exchange information about the quality of the connections, not just the number of hops. This makes OSPF more efficient, especially in larger, more complex networks. Finally, BGP, or Border Gateway Protocol, is a specialized protocol used for routing data between large networks, known as autonomous systems, like those run by ISPs or global organizations. BGP is the protocol that makes the global internet function, as it routes data between different networks across the world. Let's start by diving deeper into RIP, the Routing Information Protocol. RIP is known as a Distance Vector Protocol, meaning it measures the number of hops or routers that data passes through on its way to its destination. A hop is simply when data passes from one router to the next. RIP is simple to configure and understand, which is why it's often used in smaller networks. However, it has its limitations. One of the main constraints is that RIP uses a maximum hop count of 15. If data has to pass through more than 15 routers to reach its destination, RIP will consider the route unreachable. This makes RIP unsuitable for larger networks where data might have to pass through many routers. Despite these limitations, RIP's simplicity makes it an excellent choice for small office or home networks, where ease of setup and basic functionality are more important than scalability or efficiency. So, how does RIP work? Routers using RIP exchange information every 30 seconds, sharing their entire routing tables with their neighbors. Each router in the network only knows about the routes directly connected to it and receives updates from neighboring routers. These updates contain information on which routes are available and how many hops are needed to reach them. RIP's metric for choosing the best route is based solely on hop count. The fewer hops, the better the route, according to RIP. This works well in simple networks, but becomes a limitation in larger networks because RIP doesn't take into account the speed or quality of the links between routers. So, while RIP may select a route with fewer hops, that route might not be the most efficient in terms of speed or bandwidth. There are two primary versions of RIP: RIP version 1 and RIP version 2. RIP v1 is an older classical protocol, meaning it doesn't support subnetting. This limits its flexibility as it can't handle more complex network designs that require subnetting for efficient management. RIP v2, on the other hand, is classless, meaning it supports subnetting and allows for more granular control of how IP addresses are assigned and used. Additionally, RIP v2 includes support for authentication, which ensures that routing updates are secure and not tampered with. This makes RIP v2 a more flexible and secure choice for modern networks, even though it still retains the same basic limitations in terms of hop count and scalability.
So you're already using ChatGPT, and while that's awesome, there is one little problem.
Let's consider a real-life example of RIP in action. Imagine a small business with a simple office network. They have a few computers, a printer, and a couple of routers. The network doesn't need to handle large amounts of data or complex routing tasks. In this scenario, RIP is a great solution. It's easy to configure and maintain, and the small size of the network means the hop count limit won't be an issue. However, if the business grows and adds more routers or branches out to other locations, they'll quickly run into RIP's limitations. The 15-hop limit might prevent some locations from communicating efficiently, and RIP's simplicity could lead to inefficient routing, slowing down the network. At that point, they might need to consider upgrading to a more advanced protocol, like OSPF. Now, let's move on to OSPF, or Open Shortest Path First. OSPF is a more advanced and scalable routing protocol designed for larger and more complex networks. Unlike RIP, which uses hop count, OSPF is a link state protocol. This means that OSPF routers don't just count hops. They also take into account the quality of the links between routers. For example, a link with higher bandwidth or lower latency will be preferred over one with slower speeds or more congestion. OSPF is also hierarchical, which allows it to scale efficiently across large networks. It divides the network into different areas, with one central backbone area known as Area 0, connecting all other areas together. This helps to reduce the amount of routing information that needs to be processed and keeps the network running smoothly, even as it grows. OSPF works by exchanging something called link state advertisements, or LSAs, between routers. These LSAs contain detailed information about the state of the links between routers, including things like bandwidth and delay. All routers within an OSPF area use these LSAs to build a complete map of the network. Once the map is built, OSPF uses an algorithm called Dijkstra's algorithm to calculate the shortest path for data to travel. But unlike RIP, OSPF's idea of the shortest path isn't just about hops. It also factors in link quality. This makes OSPF much more efficient in selecting the best route, especially in large networks where speed and reliability are important. One of OSPF's most powerful features is its ability to divide a large network into areas. At the center of every OSPF network is Area 0, also known as the backbone area. This area connects all other areas together and helps ensure efficient routing across the entire network. Each additional area in OSPF can contain its own routers and subnetworks, and routers at the border between areas, called Area Border Routers or ABRs, are responsible for connecting these different areas to the backbone. By dividing the network into areas, OSPF reduces the amount of information that each router needs to process, making the protocol more scalable and efficient for larger networks. Let's take a real-world example of OSPF. Imagine a large enterprise with multiple regional offices, each with its own local network. Each office can be set up as its own OSPF area, with all areas connected to a central backbone through area border routers. This keeps the routing information within each area manageable while still allowing the entire network to communicate efficiently. In a situation like this, OSPF's fast convergence is crucial. If one link goes down, OSPF quickly recalculates the best alternative path and reroutes the data, ensuring minimal downtime. This is why OSPF is often the protocol of choice for large organizations and ISPs that require reliable and scalable routing. Now, let's turn our attention to BGP, or Border Gateway Protocol. BGP is quite different from RIP and OSPF. While RIP and OSPF are used to route data within a single network, BGP is used to route data between different networks, what we call autonomous systems, or AS. Each AS is a large network, often run by an ISP or large organization, that operates under its own policies. BGP is responsible for making sure data can travel from one AS to another, allowing the internet to function as a global network.
We have got to the point where literally anybody can build a fully working app without knowing how to code.
This is why BGP is often called the protocol of the internet. BGP can handle vast amounts of routing information and make complex decisions about how data should flow between autonomous systems based on policies set by the network administrators. So, how does BGP decide the best route for data? One key attribute that BGP uses is called the AS path. This attribute tracks the sequence of autonomous systems that a piece of data has passed through. When BGP routers are deciding which path to take, they typically prefer the route with the fewest ASs in the AS path. Another important attribute is the next hop, which tells the router the next destination for the data on its journey to the final destination. BGP also allows network administrators to set policies that control how traffic flows. For example, an ISP might choose to prioritize certain types of traffic or routes based on business agreements with other ISPs. BGP uses several other attributes in addition to AS path and next hop. One of these is the multi-exit discriminator, or MED, which helps routers choose between multiple exit points for an autonomous system. For example, if 2 exit points are available, MED can be used to influence which one is selected, based on factors like link speed or cost. These attributes give BGP a lot of flexibility in managing routing across the internet. By allowing network administrators to set policies and priorities, BGP ensures that data takes the most efficient and cost-effective route, while also preventing routing loops and ensuring that data doesn't get stuck going in circles between autonomous systems. BGP plays a crucial role in keeping the global internet running smoothly. ISPs, large enterprises, and even governments use BGP to manage how data flows between their networks and the rest of the world. For example, when you visit a website hosted in another country, your data might pass through several autonomous systems, each using BGP to decide the best path. A real-world example of BGP in action is the relationship between two large ISPs. Let's say ISP A is based in North America, and ISP B is based in Europe. They use BGP to exchange routing information, ensuring that data traveling between their networks takes the best path. Without BGP, the global internet wouldn't be able to function effectively. Let's now compare the three protocols: RIP, OSPF, and BGP. RIP is simple and works well for small networks, but it's limited by its hop count and can't scale effectively. OSPF is more sophisticated, offering fast convergence and scalability for medium to large networks. It takes into account not just hops, but also the quality of the links between routers, making it much more efficient in larger environments. BGP, on the other hand, is designed for routing between large networks or autonomous systems. It offers extensive policy control, making it ideal for managing global traffic across the internet. Each protocol has its strengths and weaknesses, and the right one to use depends on the size, complexity, and needs of your network. To wrap things up, RIP, OSPF, and BGP are three routing protocols, each suited for different types of networks. RIP is simple and easy to configure, but works best in smaller networks due to its scalability limits. OSPF, on the other hand, is fast, scalable, and ideal for larger enterprises or ISPs that need high-performance routing. BGP is the internet's backbone, responsible for managing traffic between large autonomous systems with advanced control over global traffic flow. When selecting a routing protocol, it's crucial to match the protocol to your network's needs. Smaller, more static networks may find RIP sufficient, while larger dynamic networks will benefit more from OSPF or BGP.
All right. So how'd y'all feel about that? Any key takeaways that y'all learned or y'all that y'all got from that video there? Pretty good. Now to set the expectation, well, first of all, I love the way he does the simplicity of the lesson. If I would have showed you the slides first, it helped knowing how all this yes, sometimes slides are good, and even though he did a slide presentation, the way he broke it down on each slide was very digestible, okay? And he kind of went up to say, this is when you're going to use these different routing protocols. So let's do a quick quiz. We still got to go through the lesson because there's a lot of other stuff other than routing protocols in the lesson. However, for the Net Plus exam, this is what you're going to see. So I'm going to ask you some questions. Okay, which type of routing can make decisions on its own? You have two choices, dynamic or static. Which one can make the decisions on its own? Pretty much generic. Cool. Now, when the internet first came about, You had, well, first of all, you have distance vector routing protocols. Okay. What's the other one that you have? These are like the basic ones you'll see on the exam. Link state. Way to go, Martin. So you have link state routing protocols. So you have distance vector, and then you have link state. Okay. Distance vector routing protocols makes their decisions off what? Correct, Mr. T. Hop, hop. Kevin got it too. Hops. Mike got it. Hops. Okay. 4, what's the maximum hops that it will go before it dies? 15. You got it. All right, here we go. These are the small stuff you'll see on the exam. I want to use RIP, routing, routing information protocol, internet protocol, RIP, whatever the I is. I know that's sad to say, but sometimes I forget these acronyms. Which one is good for classless routing? Correct, V2. That was important to see, wasn't it? Yep. So RIP V2 is good for CIDR when you want to create networks. It works very well with that. Will it still accommodate V1? Can V2 still accommodate V1? Trick question, huh? Can y'all remember what V1 is applied to? RIP V1. Class full. Correct. Now, RIP V2 can still perform V1, but V1 can't do V2. Yeah, you're right. It's just inline update. Yep, you're right. So remember that. So if that gets kind of janky on the exam, just know it's backwards compatible. Okay, you do it, V2. All right, here we go. Now, where will I see any type of RIP being used primarily? Soho. Next, y'all said there was another one. It was called link state routing protocol. Where would I see, now we're upgrading. We're not in Soho anymore. So we're going to a link state. What environment will I see that in? Correct. Everybody's got it correct. All right. Because we have a bigger network, I can no longer rely on it coming from Aaliyah's computer to go straight from Charles because we have small computers. Like, it's not efficient. So it has to take a couple of other things into account. In link state, what are those items? In order to route efficiently, let me rephrase it, it takes a couple of other items into account to ensure it's efficient. There you go. Link quality. What's the other one? Hierarchical. What's the other one? Area 0. One more. LSAs, link state advertisements. Please no LSA for the exam. That's what throws a lot of folks off. LSA, area 0. Puts it all in hierarchical order. The link state advertisements are advertising packets that go out every 30 seconds. That's why I was playing around yesterday. Hi, router, 59250, dark hair, right? It's advertising Advertising, right? So that's what it's going to do. All right, way to go. Please tell me the commonly used, because there's more, the commonly used link state routing protocol for enterprise that the video talked about. You're correct. There's a backbone. It is a backbone. It uses the backbone. So area 0 starts with an O. Open shortest path first, correct. OSPF, open shortest path first. Now there's another one. It's called shortest path first. Then there's open shortest path first, but we'll go back over that. But for what we're doing right now, we're good here. All right, last one. Oh, wait a minute. So give me one thing that's good about OSPF. Because I grow fast, it can. Scalability. Fast scalability, yes. And you'll hear this word called, just like STP, convergence. All the switches will converge, which means it'll give you a nice working environment. Optimal transmissions are happening, right? That's a sweet spot, the convergence. Okay. OSPF. Obviously, scalability pretty fast. That's how, yep. Oh, I like that, Kevin. Yeah, okay. Kevin's got a new acronym to help remember it. Obviously scalable, pretty fast. That's how I remember. Okay, good stuff. All right, let's move on now. So now, that's why I like learning like this, the way this dude did the lesson. RIP, Soho, RIP version 1, RIP version 2. OSPF, Enterprise, link state. We can't go on hot count no more. We got to go link state because there's a lot more involved. There's a lot of stuff going on. So now, once you have the link state for enterprise, this information moves up. It's got to get out the router now. So once it hits the World Wide Web,
How are you
what
doing?
protocol is being used? Correct. BGP, Border Gateway Protocol. Okay? Border Gateway Protocol. It's the same as kind of like OSPF. It's just on a grand scale. Now, this is what the ISP uses.
US.
Okay? Now you're here.
The US. Where are you? Where are you guys watching from?
Interior Gateway Routing Protocol, Border Gateway Routing Protocol. There's some different flavors, but all in all, BGP is what's being used down on the internet to route things from one ISP exchange IPX to another to get you what you need on the internet. All right, and it's essential for the global networking piece. Way to go, y'all. Y'all like that. Y'all are where I need you to be. Great job. All right, so let's jump into today's lesson. I'll bring up the slides. Please get that channel too. That channel, for that YouTube channel, for that link, follow that channel too, because they got a lot of other good stuff too. All right, so here, day 5, we just went through the introduction to configuring, or let's say routing protocols. Let's leave it that way. You'll find all of the stuff in domain 1, 2, and 5. Domain 1, compare and contrast network appliances, applications, and functions.
So what I'm doing right now is currently classes and lectures, interviews, or video calls.
2.1, that's where you find the routing.
And information technology, IT.
2.2, switching technologies and features. 5.3, we know that whole domain is about troubleshooting. What to do if something's not working right, this and that. So that's what's going to happen in domain 5. Everything with a routing protocol is going to deal with these, just as the video explained. We need to give it a protocol, find out what the destination is, translate that to the interface, and then get it out to the gateway and or next hop. This is where it's talking about the router. Okay?
Complete the classes and be certified.
So the gateway needs to be configured. Entries need to be made. So as information is being forwarded, routing tables are being updated. It's cool to know where the information is going because you can always backfill the routing table from where it came from. So routing tables are primarily made off forwarded information to where it's going. With static and default routes, with the routing table entries.
So to answer your
it's just
question,
like
that
the
would
yellow
be to
pages,
complete all the
excuse me,
classes
like
and
yellow
be
pages with
certified.
Waze or GPS, right? Anything you use for mapping. Once you put it in, it gives you the route it needs to take. So the routing table entries remember directly connected routes, remote routes, host routes, and any default routes that may be out there. Now here is an example of a routing table entry. Now, will you see this trash on the exam? Heck yeah. Yeah. There's a PBQ stating that a manual entry may need to be made in the routing table. Okay? Give me 1 second, Charles, and I'll make you a snippet. How about that? And I'll drop it in. Give me 1 second. I'm snipping right now for you. Snippety snip. That way you can look at it as we go. There you go. Put that in your file. All right, there you go. So this is something for you to have. So when you see this, let's walk through it first of all. Okay? Let's tackle the first thing first, /24. I need some telemetry. Let me know. Quick telemetry, /24. What should I need to know about that /24? 512 hosts? How many VLANs? What's the subnet? I don't care about the IP right now. How many VLANs can I have on it? What's the subnet mask?
24 can house what? 250.
Okay, subnet mask 255.
255, yeah.
How many VLANs could be made or LANs? One subnet. Yep, you got it. All right, so as we go, we got our telemetry, figured it out real quick. So as we go through this, gives us an idea of what we're working with. So right here, it's stating routing, router A, router B's table, router B's table, and here's router C. When you see this, when you go through the exam, look at your IP addresses, scan them real quick. I'm getting a good idea of what I'm seeing. 1, 2, 3, 4. How many VLANs y'all see here? How many segmented LANs do you see in this picture?
There's 3 right there.
It's telling you in the IP addresses. 4. I have 4 segmented networks here. This can confuse an individual if you're looking on the exam because all you see is, I just see the same IP address. Well, this is the delimiter right there. All these networks, all these VLANs are separated by a different number. 1, 2, 3, and 4. So these different links have been segmented. Okay. So as it's going here, as So this is a VLAN, this is a VLAN with a whole bunch of computers, this is a VLAN with a whole bunch of computers. 512 items over here, 512 are here, 512 are here, 512 are here. See what I'm going? See what I'm talking about? They're not showing you all the other computers. They're just giving you an example of the routing table. So 1.0 right here is on interface, gigabit interface 0. That's what that means if you see it on the exam. That's an interface. You'll also see fast Ethernet, like fast 0, or ETH 0, meaning Ethernet. They're all interfaces. Really doesn't matter. It's just telling you what sits on that interface. Okay? So, as 10.1 wants to talk, and it's going through the network, through gigabit interface 0, and you have to know how to read this, because they're going to give you some examples saying something's not configured right. Okay? If ever this is what's going to tell you on the exam. If you get lost, you're going to see this. It's going to bring this up. Show interface, show configuration in switches. Okay? Show interface, and it's going to show you this. What's on each interface? How was it configured? So, but this is the routing table. So when it's going through, once going through, entries being made in gigabit 0, it's connected. All right? And it's being forwarded, boom, out of gigabit interface 1. Says it's right there, it's going out of 1, and it's going to 2. It even states it's in gigabit connection 1, puts the entry in there, and it's staying connected. All right? As it gets over to router B, okay, it states here, oh, we have an incoming packet from 10.001 gigabit 0 static. 10.0 right there, gigabit connection 0. Over on router B, it's connected. It's coming out the other side at G1, stating that that link is connected, and it's forwarding the packet. Router C is looking at it, oh, here we go. 10.3.0, gigabit connection 0. And then we have gigabit connection 1, which is right over here. That is connected and it has the right interface. But we have a problem. What do you see? And this is on the Network Plus exam. Anybody see it? Through all the routing tables. Look at the entries. Primarily on router C. Something doesn't look right. Okay, the others aren't listed. Michael says the other 2 aren't listed for table C. You're correct. And he's right, 0. What is 0? What have I always said about that IP address?
Default.
I always use the analogy, break glass in case of emergency. There you go. That is a network default address. For when there is no address, it's saying right here on router C that that is the IP address configured on that interface. On this interface on router C, it's already taken into account this address coming from gigabit connection, right? Coming in to that. But for it to go back this way, there's nothing. It's not configured to anything. All right? For it to go this way. It's got it coming in, but going back out, there's nothing. It's a static address. It's a static route. And then 4, they're accounting for 4 going out this way, so it's good. But that's the issue. Okay? You might have to log into that router or suggest it being configured from G0. An entry may need to be made from G0 to G1. And you have to suggest what type of entry or IP address needs to go in here. Okay? Mike, you about to ask a question. I can see it. You good? Now, for all intensive purposes, to send information out of this port, it'll broadcast. Now remember, that's broadcast. So you got the broadcast subnet, and you have the IP that it's going to use to broadcast. So it'll find its way. So I want to let you know, networking, it'll find its way back if it needs to, because it'll use that default address to say, hey, I'm trying to find 10.0.3.0 on a /24. Anybody seen it? That's what it'll use this. And they say, yeah, we're over here on router B. So it'll send it. And it'll keep on going, finding its way back to 10.1. But no, that's the default address, 0/0. Who does not understand the use of a default? Will you use a default? Will you manually correct? The network will find the default address, if need be, to broadcast or push information to find somebody. For when there is no address, it will use that address. That's why we never use it. You notice we never use it in CIDR, right? And you'll never see it on a class full chart, right? Mm-hmm. Right, that's why, because the network will use it. We don't. All right, good stuff. Y'all are rocking. Y'all are cooking. So those are the routing table entries that you might see. Now, Mike made another good point. This is what I want to circle back to. All right? How comes there's 4 for each one of these, but there's 3 for here? Sometimes when you're building a routing table, sometimes the first transaction will be taken by the network. Or a transaction can be taken. Right? So if it does broadcasts or is trying to find something, you're -1 address until the routing table can catch up. Okay? Like an ICMP command, nmap, right? nmap is a broadcast. Marco, Polo, I tell you something, you tell me something back. Sometimes you don't get anything back. That first one goes to the network. It's trying to build its routing table. So you could be 1 address short in the routing table until it catches up. Okay, so that's when you'll start. That's just a little tidbit that you'll see. Good stuff. So for packet forwarding, routing tables are built off forwarded information primarily. So the appliance will receive the packet, examine it. What 2 areas of the packet will it be looking at? First of all data being transmitted has what? At the beginning of it? Header. What are 2 items in the header? Every appliance will look at primarily to help get data where it's going.
Mac and IP.
Yeah? MAC IP. If we look at it, so it'll say host address, destination address, originating address, destination address. It'll look at MAC and IP. You're still right, Charles, because on layer 2. It's got to look at the MAC. It looks like the MAC address. Layer 3 looks at the IP address. Okay. So those two will come into account. Then it will consult the routing table, regardless if it's MAC or IP and which appliance. It looks at that to say, where is it? Okay. Now, when Charles said MAC and IP on layer 2 and 3, it's primarily using this to verify the destination. ARP, Address Resolution Protocol. Address Resolution Protocol. I already know the physical address, that's MAC address, 48 bits. But just to make sure, what's the IP that MAC was associated with last? It's like when you get arrested, Ocean's 11. Every time Danny gets nabbed, right? The police be like, Danny Ocean. Who are you working with? But I don't think, I love George Clooney. He's one of my favorite actors. The way he just acts is so smooth. Well, I don't think I need to tell you that. But we'll find out who your associates is. It's the same thing with ARP. It's the same thing. We're going to find out who your associate is. I got your MAC address. Now I need to know your IP, right? So that's ARP, Address Resolution. Then it consults the routing table, pushes it, make a forwarding decision. So if it gets to the next appliance and finds you, right? We're good. You're on that appliance, which is the switch. And if you're on a certain port, it'll stop there. But that's at switch 2, layer 2. Now, what if it can't find you? Now it has to make a forwarding decision. It forwards the packet to the next layer. Layer 3, routing. Router needs to find you, right? Looks for your IP address, then the MAC address. Okay, what's going on? Still can't find them. So if it can't find you at the route at layer 3 on your network, now where does it go? Where's it going to push that? Where's it going to forward that packet out to? Notice I said your network. If it can't find you on your network, it has to, yes, it's going to push it out, Martin. It's gone. But where's it pushing it out to? It can't find you on your network, so now it pushes you out to the 3 letters. They're all the same. They're at the end of the alphabet. Martin's on it today, boy. He knows his networking. It pushes it out to the World Wide Web. Dub. It can't find you on your network. So it has to make a forwarding decision. Hey, guys, can't find him here. Used ARP, sent out SEAL Team 6. We can't find Jesus. We need to forward this out to the big Air Force. We need a drone in the sky. That's where Brian comes in, because I know he's got one circling my house right now. But we send it out there, and then they try to find him. When we're looking at this, oh, Lord, I'm talking. It's break time. I done talked over an hour. Let's hold it up right there. Go ahead, y'all, and take 10 minutes. I'll see you when you get back. Hey, welcome back, everybody. Everybody get their refills and coffee, tea, Gatorade, Red Bull, powdered milk. I don't know. Leah, did you get your RAM put in? All right, good, good. Who else is upgrading their RAM? Most of y'all probably have more powerful computers already at the house. Martin, you already updated yours? Or you already got a computer that's kind of like good to go? Using, I figured so everybody's using. Oh, you're waiting? Okay. Yeah. Mike, we got to get your image installed because we're going to start getting into some stuff next week. So, but you'll be fine for just basic terminal stuff. So, just getting it installed, not no heavy lifting type of stuff. Charles said he did his, yep. So good, everybody's getting up to speed. All right, so picking up where we left off. Here, we have an example of hop count. Now, let's just look at hop count and not RIP or RIP version 2. Let's just take those out of the equation first. Just looking at this example real quick. A hop count is when it's the time to live where if it's leaving your network, an item is leaving your network and it needs to go to another router. All right. So right here, we see the switch here. See, we have B that wants to talk to, it's trying to come down to remote server over here. All right. But what's going on is once it starts to leave, it goes through the switch. You cannot count the switch as the originating. You can't count it as a router. It's not a router. It's not the original hop. It's not the first hop. You understand what I'm saying? Now, if it's an all-in-one device, is it the first hop? Yes, Aaliyah says, yeah. It's an all-in-one. Yeah, I got you. So for here, though, they have the two items separated. This is distinctly down here. It says it's a switch, and they separated that as a distinct router situation, right? So from router to router, all right? So it travels here. In this scenario, they have an internal router, which means it's the router cut in half. It's kind of like the same router, if you see what I'm seeing. Who understands that? They're trying to say there's an interior router and then an exterior. Is that true? Mike says, yeah. Leah says, doesn't sound right.
No.
Somebody explain to me what I mean. They're showing two.
No, because
Generally, is it two?
but can
Private and public side. Technically, this is a router cut in half. The router has an internal IP. The router also holds the public IP. So it's your first hop. Yeah, way to go. You know, because it's two, it can, but can count as one doing the command. Yes, you're correct. It's an all-in-one, basically. Yeah. It's doing everything in one. So yes, you're right. Both of y'all are right. Both ways y'all said it is right. So, but the router, if you envision it, it's cut in half. One side will take care of your private routing or private IP. The other one will take care of it's connected to your public in order to do network address translation, to move it.
yeah.
Okay. Then it's saying from this local LAN over here, it hops. Doink. So there's your next hop going on. So that's hop number 2. Then from here, from this router to this router, now you got 3. Here's your 4th connection. There's your 5th, 6th, 7, interface to interface, 8, and then here's your other interface. Do we count this one?
It's an all in
No,
one.
it's a switch.
No. Yeah.
So that's where it ended, at 9. So that's how you got 9 hops from interface to interface. It's going. All right. Now the switch, once it gets on the inside, this router is technically cut in half too. Has its public side and its private side. Public facing, private facing. And it'll make sure it looks in its routing table, does network address translation, finds the private address of the switch it needs to go to. The switch looks in its routing table and finds what port it needs to go out of, and then it sends it straight to the remote server. So that's how that's gonna happen. All right. So that's regular hop count. Now, what is the maximum hop count when using a routing protocol, RIP v1 and RIP v2? Correct, 15. So it's saying on the inside of a domain, we're not going to have a time to live to be forever. We're not doing that. We can't have packets just out there on the network clogging up stuff. So we're going to give them a maximum hop count of 15. If you can't find where you're going in 15 hops, you don't need to be out there. That's basically what it's saying. You're clogging up my network. When it comes down to the router configuration, router placement is good. You want it on the same subnet or IP network, must not be separated by a router. So you can't have a router separating a router. That's not ideal. Okay? So you have the edge router firewall. You could have an internal switch or internal router or all in one that could do it. Now, a layer 3 switch you can have on the public. You can't have 2 switches. You can have, okay, let me back up for a second. Let me ask this correctly. You may have a situation where you want to isolate a public facing item that the company is providing, meaning a server for you to go shopping at, like Amazon. You may need a firewall on this side and a firewall on this side where you may use 2 routers. What is that area in the middle called? It's a public facing. I'm inviting the public in, but I wanted to keep it safe and separate from my internal network. DMZ, you're correct. Leah, you can use the firewall and the proxy to do the same thing. So yeah, you could have a proxy on one end separated and firewall, yeah. But the area in the middle, DMZ, screened subnet. All right, to protect your network assets. As it's doing here, ISP has their own edge router, comes in, internal router, and then from there, these ports are configured to have these LANs. These are local area networks coming off of the switch. Somebody give me some quick telemetry on /28. With some quick numbers about that. /28.
That would be
How many hosts, MAC address, subnet address, and how many VLANs can I make? 16 hosts, 16 subnets can be created. What's the subnet mask? 240. There you go. That's what you need to do for the exam, to easily identify stuff, to know that's your starting point. And then from there, you're like, okay, now what is the question asking me? You understand? Now we can get to the question. I got the telemetry, basically. Now let me dig into the question and see what they want to ask me, so I can break it down. Your routing tools, these are your command line, CLI. So if you see this, just like Linux in the terminal, this is what you'll see inside of a switch. It's nothing different. A switch is a computer. You have to have a laptop connected to it to get to your command line interface to configure it. If you're trying to figure out what's going on, you might remotely log into it, or you might be on-prem, plug directly into it, and you can get to the command line. And you want to do things like show route, displays the routing table of the switch. Here, you want to make sure everything's good. You want to make sure nobody's put any manual entries into that, right? Or disrupted your configuration somehow. That's why we were talking about, it says, there's another one that says show address table, show route, show ARP, list current ARP table entries, address resolution protocol with MAC and IP. You can type route and shows IP routing table of the host or trace route. You can also do that. That's inside of your computer too, show route. With dynamic routing technologies, static versus dynamic, it all comes down to configuration, flexibility, control, and use case. Of course, static is manual, dynamic is automatic. With static routing, it's not flexible. You have to do all the updates and manual intervention because you manually wanted to map out where you want your information to go. Dynamic takes all that telemetry into play, right? Bandwidth, distance, all this different stuff, delay, and it makes the decision for you. Yeah, you got complete control with static. Well, oh, God, help you if you have more than 512 static links you did. Oh my gosh, Lord, don't do that. And then you have less direct control over the routes that takes place. But then down here, static is good for small networks, like for your house if you wanted to do that. But there's one reason why I just don't like static networks, primarily security. Somebody gets into your network and you do not know that they're there. You've got static IPs on everything and they know it. There's no expired leases. You can't refresh IP addresses. You can't do it. They pretty much mapped out your whole network and they can go in and out as they please, right? Because there's no security. So that's what static networks can do for you, give you less security. We looked at these different routing protocols with RIP. We know that it's a legacy dynamic routing protocol. Finds the best path between the source and the destination. Maximum hop count of 15. Not ideal for enterprise. But it's slow to converge. Can somebody tell me what the converge means again? Converge. There was a movie with Leonardo DiCaprio talking about convergence. Convergence. What's convergence? Somebody dropped the definition of convergence into the chat. Let's understand this terminology. Let's understand this wizardry. What is this? Okay, Charles says meeting at a point. So all of them are working together, right? It's the transactional point, the interface. Everything's flowing together. Pretty seamless, right? Yep, consolidate the traffic. Yep, it's kind of like a perfect world. You got a perfect world of things happening, working together. So it's slow to converge with RIP. All right, here's the other one I told you about that the lesson, the overview didn't go over. It's called Enhanced Interior Gateway Routing Protocol. In advanced, this is what you need to know, distance vector. So we already know if its distance vector is taking things into play like bandwidth, delay, load, reliability, and path selection. Supports 4 and 6, and you don't need separate configurations. But it's more complex to configure. And Cisco told you they were at the bottom of this. They're there when the internet was created and routing. So yeah, they're in. They created this. Now let's bring back something. Let's go back into time, into 1201. We talked about IPv4 and IPv6. And there was a way you could send a packet. You could send an IPv6 packet disguised as an IPv4 for this type of routing right here. Because y'all were like, when would you ever use that? And I'm like, that's for server farms and stuff like that. See the guy in the picture? He's inside of a network room, probably a server farm somewhere. Big data is being moved. Primarily out on the internet, IPv6 is being used, but on SOHO networks, on the private side, we use IPv4 predominantly. So what is that? What is that IPv6 disguised as an IPv4? I'm only saying this because you might see it on the exam. You might be able to Google it too. Google's our friend in this class. How to send IPv6 traffic in an IPv4 packet. What do you come up with? And vice versa. Well, the proxy and the VPN gives you a secure tunnel in which to send it in. That keyword tunneling. You're right, Elaine. You got the first part, tunneling. So how's it moving? I'm gonna type it out for you. Yep, it encapsulates it into 4 to 6 or 6 to 4. All right. Oh, y'all were right there. Mr. T and Leah said encapsulation. It does that. This helps do tunneling, which is a private tunnel. It's 4 to 6, 6 to 4. So let's say, let's go back to this example. All right, you see this here? This is the inside of the network here. On the private side, this is primarily a private, and they're using IPv4. But when it gets out here, it needs to go to 6 because ISPs primarily use IPv version 6 in server farms. You get what I'm saying? So as it comes out of here, 4, and goes out on the internet, they might require it to go from, we need to take 4 to 6 because we have designated routes and we need it to move. We're all IPv6 out here, right? So with network address translation, we always say when it's going, it adds the header to the next destination address in order to forward it. When it's coming back, it strips off the previous address on the header to remember how it gets back. Remember that? So in the header information, it'll change. It'll still say IPv4 information on the inside, but it gives it like an IPv6 header. Goes through all of this out on the World Wide Web. See, there's another interchange that it has to go to. And as it comes back in here, it changes it back from 6 to 4. Does that make sense? So it's a packet disguised as another packet, just in order for it to get routed. efficiently. Michael says, will it move slower or stay the same speed during encapsulation? Same speed. It's quick. It's nothing more than just saying, it's your mode of transportation, that's all. That's like, Michael, you going from a set schedule, city bus, route, you go to your interchange point, right? And all you did was switch to a train. You got encapsulated inside of a train car, you took the subway, in a tunnel, you came out the other way, you jumped out, you got back on the bus for your last mile. You get what I'm saying? It's the same thing, same theory. But out here in this world, they use IPv6. Yeah, which is dope. Hopefully I explained that so everybody can understand it. All right. Next, open short is fast first. We talked about that. Dynamic link state. Remember, that's a link state routing protocol. Here, this is a distance vector. Distance vector. Link state. Okay. That uses an algorithm to find out what's the best path to take based off link state advertisements, LSAs. Can be more complex planning and configuration and requires more bandwidth than distance vector. We know we have BGP, primarily used for the internet, the World Wide Web. It's a gateway protocol that enables the internet to exchange that information. It's scalable, uses path vector protocol for establishing routing decisions. And it supports CIDR, allowing for efficient IP address management and route aggregation, which goes back to Michael's question. Does it move slower or not? Nope, it uses that address management and route aggregation. It takes longer to set up from interface to interface those IPv6 addresses, but it wants it to go direct routes or use dynamic. All right, couple of questions for you. When would it be most appropriate to use static routing over dynamic? What y'all say? Somebody said C. In a small network where path direct between does not frequently change. Yep, I would agree with you. 2, Peter is tasked with implementing a routing protocol that supports rapid convert. They're telling you rapid conversions, and it's proprietary to Cisco. Which one is it? Is it 2? Is it EIGRP? Sure it's not OSPF?
It's the
We'll look at that in a second. I might be wrong. Your company wants to create highly available data centers. Which of the following will allow the company to continue maintaining an internet presence at all sites if the WAN connection goes down at their own site? Yep, Border Gateway Protocol. Key thing says internet presence. Internet presence. I think that question got me a little twisted in too, though. Something in there I didn't like the way they asked it. Okay, yeah, y'all all right. All right. What got me was I didn't remember hearing rapid conversions for EIGRP. But obviously y'all did. Yeah, Cisco proprietary. Okay. Hey, we trust them. We verify up in here. Y'all got to take this exam. I want y'all to have the right information.
Yeah.
It ain't about, the big head up in here. We got to make sure you had the right stuff. So it is EIGRP. Good catch, y'all. Way to go. All right. So let's get back to this. Any questions so far? This is pretty cool when you get into routing protocols. If you take it too fast, you'll get confused, but y'all have it. All right, here we go. Let's talk about network address translation. This is when you have a private address that needs to be routable for the internet. Okay? Now, how all this is able to happen is the fact that the headers, we know that everything that travel has a header on it. As it go up and down the OSI model, it adds the header of each layer, correct? In front of it, right? So there's nothing different when you're using a private address that's not routable on the internet. It's not routable on the internet. You have to get that information to be routable. That's where you have your router being fictitiously cut in half. And you need to have your private address assume or disguise itself as your public address in order to get out to the internet. Now, for every piece of machinery or node that packet has to travel through, okay, it will assume the identity of the IP address of that new item it just passed through. Does that make sense? Kevin's like, yeah, I got it. So, we'll make it real simple. If your PC has address 192.168.0.1, then it goes straight to your Soho router at your house to get out to the internet. It's going to add a header. It's going to take your address, push it to the back, and it'll add the header of the router internal address, which is .1. Your address is still there. It just says move. Didn't we say routing tables are built off forwarding? So then it forwards it to the public side of your router and says, I can't find this on my network. We need to go to the dub. Then they say, okay. Router says, use my public address. So now it'll tag its public address in front of its private address, and your address is third in line. You see what I'm saying? Because it's pushing it. Now, once it goes out to the web and comes back, it remembers how it got there. Packets come back, it's got 3 addresses on it. It's got your public address of your router, it's got your private address of your router, it's got your PC address. So Kevin says, so is the router a bit selfish in that it wants to always make sure everybody knows its name? Yep. I'm King, like Denzel. I'm King Kong up in here. Ow, I gotta lift some more weights. Listen. But yeah, so the router wants to know, you know my name, you don't know their name. All right, they're the general. So as it come back into the network, strips off the public address, gives it back its private address. When it starts forwarding it, it says, oh yeah, I remember that PC address of a .1. Starts forwarding it, strips off the router private address, and it lands back in your PC. That's network address translation. Enables multiple devices on the local network to share a single IP address, the public one. Why is it needed? Increases network security, hides all internal addresses. Now, you can be cool if you want to and put everything in your house on a public address, but what will happen then? Who wants to try it? Aaliyah's like, no. You can let anybody inside your computer if they have your public address. They can look around all day. So don't do it. Yep. Network addressing, NAT types, network address translation types. The dynamic maps automatically and allows for everybody to do, it just does it automatically. Or you do static, you can map it out. Okay? Allows inbound connections initiated from the outside. No, I'm not doing that either. That's a security risk. Now, what's cool about this, you can have an edge router. Edge router is located at the boundary of a network that connects to external networks. The internet manages the flow of the data between the internal and external networks, routes data to its destination, performs NAT. That's the example where we were using where you could have a strict router that's private facing. You'll have a public facing router, firewall in the middle. There's your subnet. This protects everything. Usually you're dropping a server. You doing good, Jesus? You all right? All right. So it'll take that and put it in the screen subnet to do that. Now you have customer edge, private edge. Private facing, public facing, it's the same thing. I don't know why they make up these new terms. Located at the edge of the customer's network, connects customers internally. Focuses on maintaining integrity and confidentiality of the customer network as it travels across the provider. That's ISP, this is the customer. ISP, customer. That's all that is. And this is what it's gonna look like for port address translation. Now, if we're looking at just ports, for port address translation, this is what it's looking at coming off of a switch. That's all it is. It remembers your IP address, and if you're connected to a switch, it remembers what port you were using or what port was initiated at the time of the request. (1024), right? When requests are being initiated to go to the internet, like google.com, you will find that your computer will pick any available port to initiate, unless you strictly went in and said, I only want this application to use this port, or I only want this traffic to go out on this port. If you never did any of that, it's going to do it on its own. So that means it's going to pick any port between 65,000 and 65,532. And it'll just go out on any port that's available and it'll just start talking. Okay? It's like a snitch, right? Dude, the cops came around yesterday. Did you talk to him? Yeah, I did. Oh, you a snitch. Okay, you got to do port security. You only want him talking to direct people, right? So you'll designate. It's like that movie, American Gangster. Who's seen American Gangster? Great movie. The part where Denzel beat up the dude with the piano. Remember that? Huey, I don't want nobody talking to nobody. I don't talk to nobody no more. You go through Huey, Huey goes to me, I talk back to Huey, Huey talks to you, right? He made a barrier. He's like, nobody talks directly to me no more, right? This is basically what this is saying in port address translation. Take this path to get to me, right? Off of a switch. All right, got some questions for you. Your company's security policy states that its workstations must hide their internal IP addresses whenever they make a network request across a wide area network, meaning the www. Which one are you going to use? What's the best solution? Bingo. Whoa. Whoa. Let's look at it again. Hide their internal IP address. Yeah, 3. See, sometimes I get got. I'll read a question too fast. Like, wait a minute, let me go back and read it. Yep, hide your. 2, you typed IP config at the command line, at the command prompt to find out your IP is this. 192.168.12. Then you go to google.com and search your what's my IP. You get this. How do you explain why your computer has 2 different IP addresses? Okay, somebody put 2. Jesus put 2. Lane put 2. Leah put 2. Mr. T, everybody's hitting 2. You are correct. It is 2. Because this is what's happening. Remember port address translation? Your router controls both of these. That is the gateway. It's either going to add or subtract an address as it goes or comes back. It wants to be the big dog. You want to talk to me, Huey? You talk to Huey? Huey talk to me? I talk to Huey? Like, Denzel played that part, man. Yeah. That way we don't get nabbed by the cops, right? All right. Any questions so far, y'all? Y'all are doing real good on this novice. I'm pretty impressed. I'm excited to see what the network plus results are going to be. All right. Good call, Leah, because we're taking a break right now. 10 minutes. See you when you get back.
Hello everyone, I'm James Messer. We'll start our Network Plus course with a broad discussion of something we refer to as the OSI model. This is referring to the Open Systems Interconnection Reference Model, and it's a model we use in IT to describe the process that data takes as it traverses our networks. The OSI model is not designed to be a detailed description of this data, but instead is intended to describe a broad overview of how data traverses our systems. We're also not describing the OSI protocol suite. Indeed, most of the protocols we use today are based on TCP/IP. But the OSI model is one that we can apply to many different protocols, and it works perfectly with the TCP/IP protocols that we use today. Also keep in mind that there are many different protocols that might operate at an individual layer of the OSI model. So as we step through an individual layer, keep in mind there might be tens or even hundreds of protocols that might exist and work at that particular layer. By understanding this OSI model, we can converse with other people in information technologies in a way that we would all understand. It doesn't matter if they're working inside of your own company or with a different organization. When you mention OSI layer 7 or OSI layer 4, everyone understands what that means and what effect it has on the overall operation of the network. If we start at the top of the OSI layer or OSI layer 7 and work our way down to OSI layer 1, we have layer 7 being the application layer, layer 6 is the presentation layer, layer 5 is the session layer, layer 4 is transport, layer 3 is network, layer 2 is the data link layer, and layer 1 is the physical layer. There are many different mnemonics that people use to memorize this, but if you start at the top and work your way down, you can take the first letter of each one of these layers, and you might have a term such as, all people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. Let's start our conversation of the OSI model at the bottom of the OSI model, or layer 1. We refer to this as the physical layer because it's describing the physical signals that we send through the cable and fibers on our network. At this layer, we really don't have many protocols to speak of because we're really just talking about getting a signal from one part of the network to another. When we refer to a physical layer problem with the network, we are referring to the OSI layer 1 physical layer. This means that we might have a bad cable, a bad fiber, there might be interference on a wireless network, and it may require us to do a series of tests to determine if we are really able to get a signal across this particular wire or this particular fiber so that we can keep this network running. A lot of the troubleshooting that you do at layer 1 is running loopback tests, testing cables and fibers, and checking different adapter cards and other devices to make sure they're working properly on the network. One step up from the physical layer is layer 2, the data link layer. This is the fundamental layer that's used to communicate between two devices on the network. We often refer to this as the MAC address layer because that is the data link control layer, or DLC layer, that is commonly associated with the network cards that are in our devices. And most of the time, these are Ethernet adapters or wireless adapters, and we refer to that physical address on that device as the data link control address, or the MAC address. In this case, MAC address is not referring to an operating system, it's referring to the media access control address. So anytime you hear someone talk about a MAC address, they are referring to the hardware address of that particular adapter card. Since the network switches that we use on our network determine how to forward traffic based on the destination MAC address, this is a layer that we often refer to as the switching layer. So anytime we're referring to a MAC address, a problem with a switch being able to operate, or anything else that may be associated with this particular hardware address, we're referring to OSI layer 2, the data link layer.
People can get crazy trying to stop a cyber attack.
The next layer up is OSI layer 3, or the network layer. We often refer to this as the routing layer because this is the layer that routers use to determine how to forward traffic. And they are specifically looking at the destination IP address in order to determine what the next hop might be for traffic traversing the network. This is also the layer that we're able to fragment these frames into multiple pieces, especially if we're sending it across a network that may require smaller frames than what is on our local network. So we can cut those frames up into smaller pieces to be able to fit them through the network and then put those pieces back together on the other side. Anytime we're referring to a problem relating to IP addressing, subnet masks, anything related to an IP address or anything about routing, then we're probably referring to layer 3, the network layer. Layer 4 is the transport layer, and as the name implies, we're referring to the ability to transport information from one device to another. You might also refer to this as the post office layer, because this is responsible for getting your letter or your information from one side of the network to the other. The protocols that are often used and operate at layer 4 of the OSI model is TCP, that stands for Transmission Control Protocol, and UDP, or User Datagram Protocol. These two protocols are commonly responsible for getting all of the information within our IP packets from one device to the other. In many cases, this involves taking a large amount of data, putting it into smaller pieces to be able to get it across the network, and then putting those pieces back together on the other side. Before we can send that information from one side of the network to the other, we may need to create a session so that a device is able to receive that data. Layer 5 is the session layer, and it provides communication management between point A and point B. Anything relating to the initiation of a session, stopping the session, or restarting the session can commonly be associated with that layer 5 session layer communication. If an application is using some type of control protocol, or you're tunneling information within existing data, then you're probably using OSI layer 5.
At home, your phone
OSI
is
layer
Instagram,
6 is
your laptop is
responsible
streaming
for
YouTube,
putting
your
all of
TV
this
is on
data into a
Netflix, and
format
your
that we
console
will
is gaming
eventually
online.
see with
All
our
these
human
devices
eyes.
are talking
This
to the
refers to
internet at the
character
same
encoding,
time. But
application
here's the
encryption,
catch.
and
Your home
decryption,
usually has
and it's
only
often
one public
combined
IP
and
address from your
discussed in
internet
conjunction
provider.
with
So
the
how is this
application
even
layer
possible?
at layer 7.
How do multiple
Layer
devices
6, or the
share that one
presentation
connection
layer, is
without
the layer
crashing
that
into
is
each other?
commonly in
That's where
operation
NAT
just
network
prior
address
to us seeing
translation
this data
comes
on
in.
our screen.
NAT is like the
And the
silent
top layer
hero
of
of
the OSI
networking.
model is
And in
OSI
the
layer
next few
7,
minutes,
or the
we'll uncover its
application layer.
magic.
This is the
Before
layer
we
that
move
we
ahead,
see
if you
on our
enjoy
screen.
simple
So
explanations
anytime
for
that we are
complex tech,
interacting
do hit
with an
like, share, and
application,
subscribe.
we are operating
Otherwise,
at layer
you
7
might miss the
of the
next video
OSI
that could
model.
make your exam
Common
prep or interview
applications
way
that would
easier.
operate at OSI layer 7 are HTTP,
Let us understand NAT
HTTPS,
now.
FTP,
Think of
DNS,
NAT as the bridge
POP3,
between
and
your private
thousands
home
of other
network and the
application
outside
protocols.
world.
Well,
Inside
that's a
your
broad
home,
overview
devices
of
use
the
private
OSI
IP
model, but
addresses
how do
that the
we
internet
fit
doesn't
things in the
recognize.
real
On
world
the outside,
into each
websites
of
only
those
see one
layers?
single
Let's
public
start
IP
down at the
address.
bottom with layer
NAT is
1,
the
or the
translator that
physical
makes
layer.
this
When
possible,
we refer to
ensuring each
cables,
request
fiber
and
optic
reply reaches the
connections,
right
the
device.
signal going
Without
across those
NAT, every
connections,
gadget
or a
in your home
wireless
would need its
network,
own
then
public
we're
IP,
operating at
which is
OSI
costly,
layer 1,
inefficient,
or
and
the
in many
physical
cases
layer.
impossible.
When we refer to
In
OSI
short,
layer 2,
NAT
or the
allows
data
many to
link
one
layer,
sharing,
then we're talking
making
about
the
internet
internet
frames,
usable in
MAC
every household
addresses,
and
or
office.
addresses referred to as extended
Let's zoom
unique
out and see the bigger
identifiers,
issue.
or EUIs.
The original
There are
IPv4
EUI
system
48
has only
addresses
about
and
4.3
EUI
billion unique
64
addresses.
addresses, for
Back
example.
in the
And as we
1980s,
described
that seemed
earlier,
like more
anytime
than
we're
enough.
referring to the
But
switching
fast forward to
process,
today,
we are
billions of
referring to
people, each with
OSI
multiple
layer 2.
devices, phones,
At
laptops,
OSI layer 3,
smartwatches,
or the
IoT
network layer,
gadgets.
we're referring
If
to
each needed
IP
its own
addresses.
public
So
address, we
anything
would
that
have run
has
out
an
a long
IP
time
address
ago.
or subnet
NAT
mask,
helps stretch
or
these
refers the
addresses
way
by
that
letting
routers
entire
forward
households
traffic,
or
all
companies share
happen
just
at
one.
OSI
It's
layer
like
3.
carpooling for the
If you're
internet.
referring to a
More people,
TCP
fewer
port,
cars,
or a
smoother
UDP
traffic.
port,
To really understand NAT, think of it as a reception desk in an office building. Employees inside the office have their own internal extensions that outsiders don't know. If someone calls the company, they dial the main number, and the receptionist connects them to the right person. NAT works exactly the same way. Inside your network, devices use private IPs. When a device wants to reach the internet, NAT rewrites the address to the router's public IP and keeps track of it. When a reply comes back, NAT checks its list and delivers it to the correct device. NAT comes in 3 main flavors. Easy to remember with the letters SDP. First, static NAT. This is a one-to-one mapping between a private IP and a public IP. It's fixed and predictable. Next, dynamic NAT. Instead of a fixed mapping, devices borrow addresses from a pool of public IPs. Finally, the most common one, PAT, or port address translation, also called NAT overload. Here, many devices share a single public IP, and NAT uses different port numbers to separate their conversations. For most homes and offices, PAT is the go-to method because it's simple, efficient, and saves addresses. Let's look at an everyday example. Suppose your laptop, your phone, and your console all go online together. NAT gives each one a different port tag, say 5001, 5002, and 5003. On the internet, they all appear to be coming from the same public IP. When responses arrive, NAT checks its table and routes them, Port 5001 goes back to the laptop, 5002 to the phone, 5003 to the console. It's just like a hotel mailroom. The hotel has one Main Street address, but the receptionist makes sure each package goes to the right room. That's how NAT keeps everything organized. NAT has a lot of advantages, and you can recall them with the letters SHPF. S for save, it conserves the limited IPv4 addresses. H for hide, your private devices are hidden behind the public IP. P for protect, this hiding adds a light security layer by blocking direct outside access. And F for flex, NAT scales easily, whether you're a single home or an entire ISP network. In short, NAT saves resources, keeps your devices less exposed, and makes modern internet possible. It's not just a translator, it's a multitasking protector too. Of course, NAT isn't flawless. Some applications like gaming, VoIP calls, VPNs, or peer-to-peer services need direct inbound connections. NAT can make those tricky unless you use workarounds like port forwarding. It also adds a small translation overhead, though usually negligible. And most importantly, NAT is only a temporary solution. It was designed to stretch IPv4. The real long-term fix is IPv6, which has a practically unlimited number of addresses. So while NAT keeps us running today, the future is about moving to IPv6, where every device has its own unique identity online. Let's wrap it up. NAT is the doorman of your network, translating private addresses into a public one so multiple devices can share the internet. Remember the mnemonics: SDP for static, dynamic, PAT, and SHPF for save, hide, protect, flex. NAT solves the IPv4 shortage for now, though IPv6 will eventually replace it. The next time your Wi-Fi just works for every device in your house, remember, NAT is the invisible helper making it possible. And if
That's a good vid to understand. I'll drop that for you guys so you can look at it at your leisure. We're working on assignments right now, but the one thing about this too that it tells you, IPv6 does not need network address translation. Doesn't need that because it's the network identifier and the IP address all in one address of the 128 bits. That's why it's easier to use out on the World Wide Web, down on the inside of your house. So it eliminates that. And IPv6 eliminates STP, Spanning Tree Protocol. No broadcast storms. Everything's unique. Yep, so it's pretty dope. All right, with that, I'm gonna work on getting your vouchers on a list and email it out there. It'll be one list, everybody's voucher. Just be careful not to use your buddy's voucher. Look at your name, copy the right one, and schedule the exam based off that one. So I'll get started working on that. I'll be right back.
Way where everyone understands exactly what we're referring to when we talk about a layer 1 physical problem or a layer 7 application problem. If you were to walk through a data center, you will see many of these racks all together with a lot of different equipment installed in each one of them. All of these devices work together to be able to take data from one part of the network and move it to another part of the network. Each of these devices is installed for a specific reason, and it's helpful if we understand why we installed that particular piece of equipment to begin with. Over time, we may be installing more of this existing equipment into our racks, or we may be installing new technology. So in this video, we'll look at different types of devices and how we might use them in our data center. Let's start with one of the most common devices that you'll find, which is a router. A router allows us to take data on one IP subnet and route that information to a different IP subnet. These may be subnets that are next to each other in the same data center, or these IP subnets may be located in different parts of the world. We refer to a router as an OSI Layer 3 device. At the OSI Layer 3 or network layer, we're referring to IP addresses, and IP addresses is exactly what's used by a router to be able to determine the next hop for this information. You may sometimes see this routing functionality also included inside of an existing switch. We often refer to these as Layer 3 switches, which of course is referring to that OSI Layer 3 functionality. It's not that the switch itself is now operating at a different OSI layer, it's just within that same piece of equipment, we have both a Layer 2 switch and a Layer 3 router, so we've abbreviated that as a Layer 3 switch.
Getting everyone in your home on the same page about energy use is hard, so we're making it easier. Xcel Energy offers programs and services like a home energy assessment and smart thermostat rewards, plus rebates to help reduce the cost of energy upgrades in your home. We make energy decisions easier. Who gets to control the remote? That's up to you.
These routers often connect many different types of networks. So we may be connecting a local area network, or a LAN, to a wide area network, or a WAN. These might also be copper-based connections or fiber-based connections. So we may have routers with many different connections or interfaces on them, and we're connecting many different diverse networks to all of those different interfaces. Another common device is a network switch. Switches operate at the MAC address layer to be able to forward traffic, so we'll often refer to that as an OSI Layer 2 or data link device. These operate mostly in hardware. The hardware inside of these devices is referred to as an ASIC, that is an application-specific integrated circuit. There are many different functions and capabilities inside of these switches, especially if you're using one designed for the enterprise. For example, many of these switches have the ability to include power on the same wires as your Ethernet connection, and we refer to that as Power over Ethernet, or PoE. And as we mentioned before, you may hear folks refer to this as a Layer 3 switch if the switch includes some type of routing functionality built into the device itself. Security on our networks is also important. That's why you probably are using a firewall at home, and you most certainly have a firewall in your office. A traditional firewall allows you to filter traffic based on a TCP or UDP port number. But if you have a more modern firewall, you're probably using a next generation firewall, or NGFW, which is able to identify applications traversing your network and allow you to manage whether that application should be allowed or not allowed on your network. Most firewalls also have additional functionality. For example, it's common to find firewalls that will allow us to encrypt traffic traversing the network through a virtual private network, or VPN. It's very common to have a firewall at one remote site and a firewall at another remote site, and be able to create an encrypted tunnel between those firewalls using this VPN functionality. And most firewalls can also operate as a Layer 3 device, which means the firewalls themselves can act as a router. That's because they're often sitting right between the ingress and egress point of your network, where all the traffic on the inside of your network is going to the outside or internet connection, and your internet traffic is coming inbound to your local network. We rely on the firewall to be able to manage the communication between the inside and the outside of the network. To be able to perform this functionality, many firewalls also provide network address translation, or NAT, and because they are a router, it's very common to have dynamic routing protocols supported inside of the firewall as well. Many data centers might also have standalone IDS or IPS devices, although much of that functionality is also integrated into the more modern next generation firewall. IDS refers to an intrusion detection system, and the IPS refers to an intrusion prevention system. Both of these work in similar ways. They're looking for attacks that are inbound to your network and are able to identify, alert, and in many cases prevent that attack from gaining access to your network. These are commonly known attack types. These might be exploits against operating systems or the applications that you're using, And they might take advantage of known vulnerabilities with those applications or systems by taking advantage of a buffer overflow, a cross-site scripting vulnerability, or other known vulnerabilities to those systems. If you're using an intrusion detection system, it's able to alarm or alert if it ever sees any of these inbound attacks. If you're using an intrusion prevention system, it's able to go a step further and block that particular attack before it gets inside of your network. Since an intrusion detection system is not able to block that traffic, it's very common to see an intrusion prevention system used on our enterprise networks. If you've ever used a website that may be accessed by millions of people every day, you may be wondering how that site is able to remain up and running without any type of downtime. In most cases, it's because that site is using a load balancer to be able to distribute that load across multiple physical servers. As the end user, you may have no idea that this load balancing is taking place, but if you were to look at the data center for this organization, you might find a large number of web servers or database servers in farms that can be used in conjunction with this load balancer to maintain uptime and availability. These load balancers are also very good at identifying any outages to these servers. So if one of the servers happens to fail due to a hardware error or some type of software problem, the load balancer can recognize the issue, take that server out of the rotation, and continue to provide access to these services using the remaining devices that are connected to the load balancer. Here's a common design for a load balancer where users on the internet would be accessing a service at a location. To the end user's perspective, they're accessing a single server, but they're really accessing a load balancer that is distributing that load between multiple servers inside of that company's data center. These load balancers can also optimize the communication. For example, it may perform TCP offloading so that the communication to all of these servers on the inside of the network are occurring as quickly as possible. These load balancers can also act as an SSL offload, which means that they will provide the encryption and decryption capabilities instead of having the servers themselves manage that process. Data might also be cached on the load balancer, so requests made to the load balancer can be answered immediately instead of going all the way down to the server to provide that data. And load balancers are also very good at prioritizing different types of traffic over others. There might be certain web pages that have higher access than others, and you can commonly perform that prioritization using quality of service or QoS. Load balancers can also provide application-centric load balancing, where certain pages may be located on certain servers, and all of the requests to those pages would go exclusively to those individual servers. Many organizations have security concerns about individual users being able to directly communicate with a server or service that's on the internet. One of the ways that the organization can manage these connections is by putting a device in the middle of this conversation called a proxy. This proxy is responsible for taking the user's request, performing that request on their behalf, receiving the answer to that request, verifying that the answer doesn't contain some type of malicious software or malicious code, and then providing that answer to the end user. That is the purpose of a proxy, to sit in the middle of the communication and make that communication on the user's behalf. Since the proxy is sitting in the middle of the conversation, it's a perfect place to do caching. So the user can make a request to a web server. If that request has already been cached by the proxy server, the answer can go right back to the user without having to access the internet. We might also provide access control from the proxy server so that we can request a username and password from the user in order to gain access to the internet. From that point, we might want to filter URLs or perform some type of content scanning to make sure that the user is not receiving any type of malicious software. Some proxies require you to configure the operating system or the applications that you're using to identify the proxy and be able to use that to send and receive communication. But not all proxies work in that explicit manner. There are also transparent proxies that will work invisibly without making any changes to the operating system or the applications in use. It's very common to store documents and other files on centralized storage facilities inside of our data centers. One type of storage is referred to as a network attached storage, or NAS. We often refer to this network attached storage as providing file level access. That means that if we wanted to gain access to information within a file, we need to pull the entire file across the network into the memory of our system, and when we're writing information or changing information in that file, we will need to write the entire file back to the NAS. A more efficient way of communication might be through the use of a storage area network, or a SAN. This is very similar to reading and writing information from a local storage drive, where instead of copying the entire file to be able to change just a bit of information within it, we have block level access, which means that we can change just the blocks that have been modified. And when you have very large files, this could be a very efficient way to modify just a little bit of information within that very large document. Whether you're using a NAS or a SAN, you're probably transferring a lot of files to these systems. And for that reason, we want to be sure that we're using the most efficient method of communication. It's very common, for example, to put the NAS or the SAN on its own isolated network, and it's commonly a network that has very high bandwidths. If you're in your office and you look at the ceiling, you might see a device like this. This is an access point. This device allows us to communicate wirelessly from our device to the rest of the network. This is not the wireless router that you might be using at home, which is a router and a wireless access point and a switch in the same device. When you're in larger enterprise environments, you're usually using a device that is purpose-built for a single function, and having an access point means that we're using this for wireless communication and wireless communication only. On the other side of this wireless access point is very commonly an Ethernet connection. So this is bridging communication between the wireless network and the wired Ethernet network. That's why we refer to access points as an OSI layer 2 device or a data link layer device, because it's making that translation between the 802.11 wireless network and the 802.3 Ethernet network. In most businesses of any size, you probably have more than one access point. That's because you probably have a very large building or a series of buildings, and you need to be sure that everyone is able to access that wireless network wherever they happen to be inside of these buildings. But this means that we have to manage many different wireless access points wherever they might be in our local network or in a remote site network. And we might need to manage security settings, access policies, and other configuration parameters within that access point. We also have users that may be very mobile and moving between different parts of the building or moving from one building to the other, and we need to make sure that they can seamlessly roam from one access point to the other so that they are always connected to the network. Instead of connecting to each individual access point to make these configuration changes or manage this process, we can have a centralized management tool that allows us to manage all of our access points from one central place. This is a wireless LAN controller, and it gives us that single pane of glass so that we can manage the entire infrastructure while we're sitting in one chair. From this single device, we can deploy new access points with a full configuration. We might want to set up performance or security monitoring and be alerted if we happen to see anything across any of our access points. We can also take any changes that we need to make and deploy those automatically to all of our access points with one click of the mouse. This also allows us very commonly to create reports on how much our access points are being used and be able to understand if we need to update or change any of our access point locations. These are often proprietary systems, so if we have an access point from one particular manufacturer, then we're also using the wireless LAN controller that is also from that same manufacturer.
At Capital One, we start with applied research, leveraging our data to build models and embed AI solutions throughout our business. That's how we stack. And that's technology at Capital One.
If you were to somehow get inside of the networking cable and see what was going back and forth over that connection, you would see there was a lot of different activity going on across many, many different systems. All of these are designed to focus on specific functions. For example, we may need to get a piece of data from our network to a network that is on another part of the world. or we might need to access a system that is already located somewhere else and provide technical support or be able to share a screen. There's also a need to have traffic management on our network so that certain applications have a higher priority than other applications. And lastly, we need to be sure that all of our systems are up and available, and it may take specialized protocols to make sure that that occurs every step along the way. One way to speed up the process of getting access to data is through the use of a CDN. This is a content delivery network. And as the name implies, it is designed to provide a way to get data very efficiently from one central point to an end user. These are often set up in geographical areas. So there might be a CDN server in North America, South America, Africa, Asia, other parts of the world, and you're able to cache information at each one of these points. It takes time to get data sent from one part of the world to the other, so if you can have all of your North America users access the North American CDN, it's much faster than having them all go out to a centralized server that might be located in Europe. So if you're watching this video on YouTube or on the Professor Messer website, you're using a CDN right now. It's a way for very small or very large sites to be able to distribute their data to users all over the world and make sure that that data is as accessible and efficient as possible. For those of you that work outside of your corporate facility or perhaps do a lot of work from home, then you're probably already familiar with a virtual private network or a VPN. This allows you to connect to a remote network while sending all of this data encrypted across the network. It's a very secure way to transfer data, even across networks that would be inherently insecure.
How you doing,
such as the
John?
public internet. VPNs often use a device called a concentrator or a head-end device to be the central connection point for all of the users who are accessing that VPN. This is often a purpose-built appliance that's designed to do high-speed encryption and decryption of network data in real time so that you can have many people being able to send secure data across the network, decrypt all of that data, send it to the inside of the network, and then reverse that process to get the response back to the user. This can be a standalone device, but very commonly we integrate this VPN concentrator function within a next-generation firewall itself. Because of the encryption and decryption process required to perform this VPN concentration, we usually will use a purpose-built appliance or piece of hardware to be able to do this. That provides very high throughput and can support hundreds or even thousands of users simultaneously. But if you have a smaller network, you may not need a purpose-built appliance, and there are many VPN concentrators that will run as software on an existing operating system. You may have to install a specialized piece of software to be able to use a manufacturer's VPN, although there is VPN software that does ship with Windows, Mac OS, and Linux operating systems so that you can connect to many different kinds of VPNs using that generic software. Not all applications are designed to run simultaneously on a network, and certainly some applications may have a higher priority to your organization than other applications. For example, there might be a real-time audio or video stream that has a higher priority than a file transfer. Because of these requirements, it's very common for network administrators to provide some type of prioritization to these applications. This is often done through a quality of service or QoS configuration. You might also refer to this as traffic shaping or packet shaping. This allows the administrator to control what type of applications can flow through their network, usually based on bandwidth usage or particular data rates. This might allow your real-time applications to have full control or access to the network and put a lower priority on other applications that may simply be transferring files. To control this quality of service, you may need to make configuration changes inside of a firewall, a router, or a switch. These devices might have a pre-built list of applications and might also allow you to add your own applications to the list. And at that point, you can decide what priority the applications might have relative to everything else that's running on the network. One of the challenges we often run into with technology is that it's very good at performing a task. And often it can perform these these tasks over and over and over again without any type of human intervention. Unfortunately, this could also put a device into a state where it's performing the task over and over and over again and never finds a way to complete or end that particular task. For that reason, we've often built in different functions with our protocols so that we can recognize when a task may be going on too long and simply remove that task from the network. One common way to provide this identification is through the use of a time to live, or TTL. A time to live is effectively some type of timer. This timer may be based on the time of day, or it may be based on the number of iterations that a particular task completes. Once that timer hits 0, we can then have that task stop what it's doing, or we can drop that task from the network. There are many different cases for a time to live. One is a packet that is constantly looping between different routers. We might want to have that packet automatically dropped if that loop occurs a certain number of times. Another good example of a time to live might be to clear a cache, where we might access a website, have that website stored in a cache, and then that cache is only available for the next 60 seconds or number of minutes. When that timer hits 0, the cache is cleared, and the next time that website is accessed, you would have to go all the way out to the site to be able to bring that information back, at which point that is placed in the cache and another timer starts. Another example of using a time to live to stop traffic that is looping around your network is through the use of a routing loop. This is a really good example of where you might have router A thinks the next hop is router B, and router B thinks the next hop is router A. And what you'll find is that the packet goes back and forth between those routers over and over and over again. If you were going to perform a trace route, you would see this loop in the trace route itself, where the route goes to 10.1.10.1, then it goes to 10.2.10.2, then back to 10.1.10.1, then back to 10.2.10.2, and so on. And this will continue all the way through until it reaches a time to live.
People can go crazy trying to stop a cyber attack. Acronis take the headache out of IT security.
This is something that does occur occasionally because you might have many different routers, and those routers have many different routes. So it's very easy to make one single IP address mistake in a static route and create this routing loop on your network. For routing loops, we use a TTL field inside of the IP packet itself. This allows us to identify and stop a loop automatically if one occurs. In this example, we have router 1, and router 1's next hop is router 2. We've configured router 2 with a next hop of router 1, which means that this packet is going to go back and forth between these routers until something stops that loop from occurring. Fortunately, we built functions within IP, or the Internet Protocol, to look for this loop to occur and stop it if it finds that it's occurring over and over again. In IP, the time to live is referring to the number of hops that a packet will go through a router. Each time a router processes a packet, it decreases the time to live by 1. And when that value gets down to 0, it discards the packet, effectively ending the loop. The default time to live for Mac OS and Linux is usually 64 hops, and the default time to live for Windows is 128 hops. Since the router is decreasing the time to live by 1 each time the packet goes through, it's watching that number decrease every time it goes through a looped connection, and when the time to live gets to 0, the router drops that particular packet. If we were to look at the frame of IP, you can see there's version numbers, header length, type of service, total length, and other fields within the IPv4 header. The one we're interested in is the one called time to live, and that's the one that the router will use to determine if it's gotten down to 0 and if it should discard this packet from the network. Here's a very simple protocol decode of an IP header. You can see this is frame 1. We have the Ethernet information with the MAC addresses for the source MAC address and the destination MAC address, and this is an IP version 4 header. You can see the source IP address and the destination IP address in the header itself. If we were to break this header open and look at those individual fields that we mentioned from that previous slide, you can see there is a differentiated services field, a total length field, an identification field, and right here is a time to live field. The time to live for this particular packet is 58 hops. So this packet would need to go through 58 more routers until this got down to 0, at which point it would be removed from the network. In most cases, our total number of hops between us and the destination that we're trying to visit somewhere on the internet is usually around 12 to 16 hops, sometimes more and sometimes less. But that's a relatively small number when you consider that the total default time to live on macOS or Linux is 64 hops, and the default on Windows is 128 hops. That gives us plenty of room to be able to get data from one side of the internet to the other and not have that information accidentally dropped by a router. Depending on the protocol you're using, time to live may have a different definition. With routers, time to live is associated with the number of hops. But in DNS, or the domain name system, the time to live is associated with the total number of seconds. Let's take a scenario where we're performing a DNS lookup, and you can do this yourself by using NSLOOKUP or DIG, and you can resolve or look for the device www.professormesser.com, and your DNS server will return some type of IP address associated with the Professor Messer web server. Inside of that DNS resolution is information about time to live. This tells us how long we should cache this local entry on our system. So if we want to cache it for a certain number of seconds, how many seconds? Well, we're going to cache it for the time to live seconds. The time to live is included with the configuration on a DNS server. This is the output from the command dig www.professormesser.com. You can see that the answer section, where the DNS server is providing us information, says that the server www.professormesser.com has a time to live of 300. This is an internet address. The A is for address. And then we have 3 different IP addresses associated with my web server. This 300 value is the one telling our local machine, keep this IP address in your cache for 300 seconds. If you do the math, that is 5 minutes. Once that 5 minutes has elapsed, our local cache removes that particular resolution. And if you want to know the IP address for that same server, you would need to perform another DNS query to update your cache for another 5 minutes. This allows me, as the administrator of my web server, to be able to change the IP address in my DNS configuration, and I can feel relatively secure that most people will have an updated version of that IP address within 5 minutes. We use time to live for many other protocols as well, so make sure you look at the documentation for that protocol to understand exactly how we're measuring time to live for that particular protocol.
I would describe Underline as fast, affordable, and incredibly fast, very reliable, zero lag.
That's kind of fast.
Consistent, fast, simple. It's a no-brainer.
Cloud computing has undeniably changed the way we approach technology. With one click of a button, we can deploy an application and multiple services, all seemingly with unlimited resources. We're able to scale up and scale down these applications as we need, providing elasticity, especially in times when we have large demand, and then scale it back down when that demand goes away. We also have applications that we can now scale up or scale down and access those applications from anywhere in the world. Cloud computing also uses multi-tenancy, where many different customers are using the same cloud infrastructure. This allows for efficiency in the use of technology and efficiency in how much it costs to use this technology. Not only do we have virtual servers that can live in that cloud computing infrastructure, we can also have virtual networks. Let's take the scenario where we might have 100 individual servers that are running in our data center. That's a relatively large farm of servers. We've designed this infrastructure to have redundancy in the network. There are multiple servers, we've got load balancers and multiple firewalls, and we've designed it for uptime and availability. But now let's take this entire physical infrastructure.
All right, I've sent out
and let's
everybody's
move this
voucher
infrastructure
on
to
one
the cloud.
email.
We're going to
Please pay
migrate
attention to
100
the
physical
number
servers
assigned next
to
to you
effectively
at your
one very large
line.
physical server.
Please
Inside that
respond
one
to
very
the
large physical
email
server, we will run 100
with what
virtual
time you
servers
schedule,
inside of it.
and
Now that
if
we've
you are
taken these
testing at
100
home
physical servers
or in
and
person.
migrated them to a cloud infrastructure, what do
Yeah,
we
so
do
you can
with
just
our
respond real
networking
quick.
infrastructure?
This is the time on the 30th
Not
at home.
surprisingly, we
That's
will
it.
virtualize this network infrastructure
Appreciate
as
y'all.
well. This is referred to as Network Function Virtualization, or NFV, where we can replace our routers and our
It will be the
switches and our
30th.
other networking devices with virtual versions of those networking devices that
Tuesday
are running
the 30th.
in this virtualized environment. Although our firewall and our switches and our routers are no longer physical, they still have the same functionality. We can see those devices, our network interfaces, and everything about the network configuration all from our hypervisor. So we have the same functionality, it's just now in a virtual appliance. Just as we're able to push a button and deploy a new server, we can push a button and deploy a new firewall, or a new switch, or make a router configuration, all within this virtualized world. This gives us a lot of flexibility for deploying applications, designing the network connectivity for those applications, and connecting our different cloud infrastructures wherever they might be in the world. A common application instance inside of a cloud infrastructure might include a web server, a database server. There could be load balancers, virtual switches and routers, and virtual firewalls. All of these will run inside of a virtual private cloud, or a VPC. It's very common, especially in larger environments, that you would have separate VPCs for different application instances or different parts of the company. This allows you to keep all of these systems separated, but still allow you to manage all of them as individual virtual appliances. Although these VPCs may be different application instances, we might still want to have devices within those separate VPCs be able to communicate with each other. To provide that communication, we need a device.
Yep, it is the
called a
30th. I made sure
transit
because
gateway
you start
to be
Security
able to
Plus
connect
on
all
the
of these
1st.
VPCs together. You can think of this transit gateway as a cloud router that allows us to connect and allow communication between all of our different VPCs. If you need connectivity to these VPCs from the outside, you may need to add additional security in the form of a VPN connection. This allows someone who may be at a remote site to be able to bring up a VPN tunnel, connect to the transit gateway, and effectively have communication to all of your different VPCs. It's very common to use a VPN at a remote site or from a user's workstation to be able to gain access to these private VPCs. But there may be times when you want to make your application instances available to
Oh no, this is
anyone
for
on the
Network
internet.
Plus. You already
In that
passed
scenario,
A
you might want
Plus.
to use a VPC gateway,
So
or what
Net
we refer
Plus,
to as an internet
September
gateway,
30th.
so that users anywhere in the world will have access to your applications. We might also want to have these devices in each of our VPCs communicate outbound over the internet to other resources. We would use a VPC NAT gateway to provide this communication, and the NAT stands for Network Address Translation. Our VPCs and the private networks that we're running inside of those VPCs can translate to a public IP address to be able to communicate out over the internet. This includes security rules so that your VPCs can connect outbound to internet resources, but you may not necessarily allow inbound access from external
You have to
devices.
do me a favor,
And
respond
it's
to the
not uncommon
email.
for
I
many
don't want it to get lost
organizations to
in
use
the chat.
multiple
This is
cloud
you're doing it
providers,
at home
but still
and you're
require
starting.
connectivity between those cloud providers. We can provide that connectivity through the use
Appreciate
of a VPC endpoint, where we create a direct connection from a VPC on one cloud provider to a VPC.
Get more flexibility with NFL Sunday Ticket month to month. Join now and cancel anytime to watch your favorite team's out-of-market Sunday games. Sign up now. Terms and embargoes apply.
Charmin reinvented the square for a smoother tear. Oh yeah, Charmin Ultra Soft Smooth Tear.
On another cloud provider. Here's an example that has a number of different VPCs. We've got a virtual private cloud with a public subnet or public applications that people can access from anywhere on the internet. We also have a private subnet on this same cloud provider where we have a private virtual machine. Well, if we have a different storage network, which certainly could be at a different cloud provider, that cloud storage can easily connect to the public subnet over the existing internet and using a VPC internet gateway. But our private subnet is not accessible from the internet, so we need to add a VPC endpoint that will allow our cloud storage to communicate directly to what is a private subnet and virtual machine. Many cloud providers will include additional security that you can layer on top of your VPC.
You can use your military cat card,
lists are effectively
valid
a
driver's
firewall
license,
that's created
active
for your
driver's
cloud-based
license.
services. This allows you to control what traffic can go outbound and inbound to your VPC.
If you have an active military, active duty cat card, they'll take
a
it.
series of port numbers and protocols. So you can define a TCP or UDP port number and add that to your inbound or outbound rules in your security groups. You can also add layer 3 addresses to this. So you can add IP addresses that are individual addresses, maybe an entire block of addresses using CIDR block notation, or specify
Nothing wrong with the
IP4
jitters there,
or
Mr. Charles.
IP6 ranges directly within your security groups.
This is
very
with a
similar to
rubber beast
configuring
road.
a traditional firewall, which
It
operates
gets
looking
real.
at TCP or UDP port numbers. In this example, the inbound rules have a number of predefined rules, but you can customize these as well with your own port numbers specific to your application. In your cloud provider's front end, you would include in your network security list the list of rules that you would like
Good
to
call
select.
out there,
For
Kevin.
example,
Yeah, Social
I have a
Security
rule that is
card because it has your
inbound
signature.
to TCP
Yeah.
port 443, and any IP address is allowed to communicate inbound with that rule. I have another rule that's an inbound rule for TCP port 22, and it's the same broad range of any IP address. Once you define your network security list, it will be applied to all of your virtual private clouds. You can see that I have a virtual cloud network for Subnet X, Subnet Y, and Subnet Z. These very broad
Since we're on that
network security
topic, if
lists
you're still in,
automatically
you're about to
be assigned
transition,
to
please
each
go to
one
your
of
security
those
officer and make sure they
individual
updated your
One of
secret
the
or top
challenges
secret.
with these network security lists
I've
is
had
that
two
they
students
don't
graduated,
provide a lot of
and theirs was
granularity.
expired 2 years
Configure
before they
a
even
network
got out.
security list, it's
Go to your
automatically
security
assigned to
manager
all of
and
your
make
virtual
sure,
cloud
hey, did you
networks,
update my stuff?
even if you don't
Before
need
you
that
get out,
particular
within 6
rule
months,
in that cloud
they can
network,
do it.
and even if you need additional
Or send them an
rules
email.
for one of the individual cloud networks. Fortunately, there
This
are
helps you
ways
with your
to add
job search when they're doing your
additional
background
granularity
check to see
using
what
a
clearance you
network
have if
security
you're trying to walk
With
into
the network security group, I can assign rules to individual virtual network interface cards, or VNICs. So you can see I have similar security rules that I've defined as a network security group.
Right,
I have
they're
network
not laminated. You
security
gotta get them
group A,
laminated
which
on
is
your own.
inbound TCP to port 443, and I have a network security group B, which is also an inbound rule to TCP port 22. I've identified these as the network security group A with the green shield and the network security group B with the blue shield. And you can see that I can assign those network security groups to individual network interface cards that may be inside of a virtual cloud network. This one is on a single subnet where I've defined different rules for different interface cards within the same virtual cloud network subnet. You can see by using these network security groups that we do have additional granularity that we can bring down to the individual interfaces. This also increases the amount of
Nice one,
administration
Kevin.
required to
Social
manage all of
engineering.
these different lists.
Hey, send me your social security card. He'll laminate it for you.
Above this, you might want to look into a virtual firewall or
That
other
was pretty clever.
virtualized platform to include additional
Michael, you can send it to him
security
if you want.
application instances.
People can get crazy trying to stop a cyber attack. Acronis, take the headache out of IT security.
Get fresh groceries delivered to your door with Kroger Delivery proudly serving King Soopers.
When you're deploying a cloud-based application, you also need to consider who will be accessing that application and from where. If you're creating an application that anyone on the internet would need to access, then you would probably want to include it in a public cloud so that everyone can gain access. But if you're building out a cloud-based application that is for internal use only, you may want to deploy this to your own virtualized local data center where you have a private cloud. In many organizations, we often use both of these, and we need a hybrid configuration of both public and private clouds for all of these applications. One type of cloud model is software as a service, or SaaS. This is commonly associated with software that is on demand. You have a login screen on your browser, you log in, and now you have access to the application. Someone else has written the application, someone else manages the application, your data is stored somewhere within that application, and you don't have to do anything else to be able to use that particular app. You don't have a local installation of software, you don't manage or upgrade any of the software itself. Instead, you simply log in and use the app. This allows for centralized management of the application and the data that you're putting into the application, which means everything is being stored on a
All right, I got 2 scheduled so far.
This is a complete application offering, and you don't have to do any type of development work to be able to use that app. A good example of software as a service would be an app like Google Mail or Office 365, where you simply log in and use the app. There may be times when you would like to build your own application and deploy and manage your own data, and all you really need are the computing resources to be able to run that application. In that model, you want to use infrastructure as a service, or IaaS. Sometimes you'll see this referred to as hardware as a service, or HAAS, because you're effectively using hardware in the cloud and then using your own software on top of that. This means that you would be responsible for installing your software and managing all of the data associated with that software. If the software needs to be upgraded, you would be the one to upgrade it on your infrastructure as a service model. The application that you're using and the data that you're putting into that application is still in the cloud, but you have much more control over the access and security of that data when you're using infrastructure as a service. A good example of infrastructure as a service is with web service providers, where you can buy time on a particular web server and they make that server available to everyone on the internet. A middle ground between software as a service and infrastructure as a service is platform as a service, or PaaS. This is still in the cloud, but you're the one who manages all of the development efforts to customize the application to your specifications. The cloud provider gives you all of the tools necessary to build this particular app. You can think of this as a series of building blocks provided by the platform as a service infrastructure, and then you build out those blocks to create your own application. The underlying engine that runs the application is the responsibility of the platform as a service provider, and your responsibility is to build and maintain the apps that are running in platform as a service. A good example of a platform as a service infrastructure would be something like Salesforce.com, where they give you all of the tools necessary to create a customized application running on the Salesforce.com platform. Here's an example of a cloud responsibility matrix that you might find with any cloud service provider. In this chart, I've separated out software as a service, platform as a service, infrastructure as a service, and then an on-prem device that you would manage yourself. Obviously, with on-prem, everything from the data.
All right, they're starting to roll in now.
Physical data center.
Yep, Kevin,
are all the
N10
responsibility
009.
of the customer. But with infrastructure as a service, you have the physical data center, the physical network, and the physical host, all provided by the cloud provider, and then you handle all of the other pieces of that particular application. With platform as a service, you can see that network controls, applications, and the identity and directory infrastructure may be shared between the customer and the cloud provider, but you'd still be responsible for the accounts, devices, and the information and data. With software as a service, much more of these are provided by the provider themselves. For example, everything associated with the applications is clearly in the responsibility of the provider. Everything above that would still be the responsibility of the customer. So depending on the type of infrastructure you want and the type of responsibility that you're willing to take on, you'll need to pick the right cloud model for your application deployment.
Capital One, my team's transformer-based AI model,
Then, using contextual data helps personalize your experience in real time. That's how it's done.
that's technology at Capital One.
Beat the family curse of hair loss. Through Hims, you can break the cycle and get the thicker, fuller hair of your dreams. Genetics started, but our range of personalized treatments can help you get ahead of it. Stop hair loss and regrow your hair in just 3 to 6 months with clinically proven ingredients like finasteride and minoxidil. See why 79% of customers say they wish they started treatment through Hims earlier. Take control of your own hair destiny. Start today at hims.com.
In this course, there will be a lot of conversations about TCP/IP, moving packets across the network, and very often we lose track of exactly what that means. So I thought it would be good if we start with an overview of Internet Protocol and how it operates. The goal, of course, is to get data from one side of the network to another. And there are a number of
Waiting for
different
4 more
processes
responses.
involved in being able to transfer large amounts of data from one computer to another. In the analogy that we use today, we're going to describe this transfer of data from one device to another as using a moving truck to get data from one house
Waiting for
to
2
another.
more responses.
We can also think of the roads that we're using as the network that we've created. This might be a wired Ethernet network, a wireless network, a wide area network technology, or many different types of network connections. But in this explanation, those network connections are referred to as the road that our moving truck will drive on. In this example, this truck is the Internet Protocol. It's the one that is doing the heavy lifting and moving that data across the network. Just as we might pack up items or objects in a room into a box and put that box onto the moving truck, we do effectively the same thing with our application data. We package that information into a virtual moving box, and we put that moving box onto the truck, which in this case would be IP. So now we have a highway, which would be our network. We have a moving truck, which would be the Internet Protocol. We have boxes within that moving truck. We commonly refer to those boxes as the TCP or UDP protocol. And then inside of those boxes is application data that we need to transfer from one device to another. This process of encapsulating data within other protocols, which are then encapsulated within even larger protocols, is a fundamental process when we describe the transfer of data across the network. If we were to visualize the Ethernet frame that we use on our networks, it would look a lot like the one that we have on our screen now. We have a client that is communicating to a server, and information is being sent between those two devices. You'll notice there is an Ethernet payload in the middle of this frame. At the beginning of the frame is an Ethernet header, and at the end of the frame is an Ethernet trailer. If we were to provide a little more detail about what's inside of that Ethernet payload, you would see there would be some IP information, and within the IP header, the rest of the packet has the IP payload. Deconstructing this further, you can see that the IP payload consists of
And Michael and Martin, I think those yours two were the last one.
that part of the packet is the TCP or UDP payload. So if we were to look at a protocol decode of a single frame on our Ethernet network, we would see an Ethernet header. Inside that Ethernet header would be an IP header. Inside the IP header might be a TCP header, which would hold HTTP or website data. And then finally, at the end of the frame, we would have the Ethernet trailer. You'll notice that inside of that IP header, we had either TCP data or UDP data. So it might be useful to break out those two protocols and describe what the differences might be. Both of these protocols are very similar in their function. They're obviously moving data from one device to another, but the internals of how those protocols work are a bit different between the two, and an application will use the one that makes sense for its particular function. If you recall our video on the OSI model, you'll remember that TCP and UDP
What is that,
operate
Chintoid? How you
on
doing?
layer 4, or the transport layer. It's in this layer that we're able to send many different applications across the network simultaneously between exactly the same devices. We refer to this as multiplexing, and it describes the efficient process of transferring multiple applications simultaneously between multiple devices. Let's first look at TCP, or the Transmission Control Protocol. We refer to TCP as a connection-oriented protocol. That's because there is a formal process to
What platform does that
between two devices.
that came out on?
Is done, there's a formal process to tear down that particular session. One feature that makes TCP different than UDP is the ability for a station to acknowledge that it has received data. We refer to this as a
Console and PC. Okay.
That's because sending data to another device will always result in an acknowledgement that that device has succeeded.
Nice. Then I'll check it out sometime today.
Information was properly delivered to the destination.
Have you already gotten it and started playing it?
The device can recover from any type of errors. If it doesn't receive an acknowledgement, it can assume that that information was not received by the destination device, and it will resend that information to ensure that it's able to receive all of the data. These packets are also numbered, so the receiving device will also be able to request anything that may have been lost along the way without having to resend multiple packets and recreate that data. Having this conversation.
So is it just a demo or
about how well traffic is able to be transferred allows the receiving station to configure flow control. This describes the process of the receiving station telling the sending device to either send data slower or speed up the transmission. UDP, or the User Datagram Protocol, is a much more bare bones protocol. There's no
absolutely.
process to set up a session.
Yeah, I think sometime during later after all my lives, then I will log on to my console and
information may be inbound to a particular device. This means that we can send packet after packet.
yeah, I'll log on to my console later and download it.
And no UDP acknowledgement is ever sent back to the originator.
So it says it's an early access, so I'm not sure if they're just giving a demo version of it now, and then later we have to get the other version. But either way, I will
communicate in exactly the same way with exactly the same probability of getting that information sent across the network. The difference is that we don't receive any acknowledgments.
Oh, it's officially out today. Okay, awesome.
Guarantee that that information has truly been delivered. And since there's no acknowledgement and no notification that anything has been
so you can
any type of error recovery,
you can look for my gameplay on my gaming channel. So all my gameplays I will be streaming on my gaming channel.
There's no way to configure any type of flow control. The receiving station can't reach out and tell the sending station to speed up or slow down because nothing is ever sent back to the originating station.
Rolling in the mud?
So once I download it later, I will
Tide Pods can handle it.
I will start streaming it.
All right, everybody.
Thank you for the update. I appreciate it.
See you in 10.
It's got to be time.
Let me know what you think of the game after you played it.
Gemini, show me the concealer.
The long, thin tube.
Come back and drop a comment.
Pixel 10 Pro plus Google AI Pro for 6 months.
Appreciate you dropping by, giving me an update.
Now that we've loaded our boxes of data into our IP truck, we need to tell the truck driver where to take this information. And in the moving truck, we do this by giving the truck driver the destination address for the truck. In the world of IP, we give it a destination IP address. But of course, in a house, we have many different rooms that we might deliver these boxes to. Some boxes might be for the bedroom, others might be for the kitchen or bathroom. And when we bring the box into the house, we can take that box directly to the appropriate room. IP works in a similar way, where each box of data is provided a room name. And in the world of IP, it's provided via a TCP or UDP port number. Instead of having bedroom, living room, kitchen, or bath, there will be a number associated with that data, such as port 80, port 443, port 123, or port 25. When those TCP or UDP boxes arrive at the house, we simply look at the TCP or UDP port number and deliver that box to the appropriate application running on that server. If you were to look at a protocol decode of IPv4 traffic being sent over the network, you would see a set of IPv4 sockets for the server and for the client. This socket is a combination of data that consists of an IP address, a protocol, which would be TCP or UDP, and then there would be an application port number. For the server side, there would be a server application port number, and on the client side, there's a client port number. Once both sides of the conversation know what the IP address is, they know the protocol, and they know the port numbers of both the server and the client, we're able to send information properly between both devices to the appropriate application. If you were to look at well-known applications that are using TCP or UDP, you'll notice that many of those port numbers are from 0 through 1023. We refer to these as non-ephemeral ports, which means they are permanent port numbers. If we need to communicate to a web server, we're almost always going to use port 80 and port 443. Those are very common and permanent port numbers that you would find on almost any web server. On the client side, we tend to use port numbers on a temporary basis. We refer to those as ephemeral ports. Those are ports that are commonly associated with 1024 through 65,535. Although it's very common to find applications using non-ephemeral ports and the clients using ephemeral ports, the reality is any device can use any port number that it would like to. And although we commonly associate servers with non-ephemeral ports and clients with ephemeral ports, the reality is you could find application servers using port numbers within the ephemeral port range. So you can see this is not a hard and fast rule, but instead broadly describes the way that we use these port numbers on our network. Anytime you see a TCP or UDP port, it can be a number between 0 and 65,535. That is a lot of room to be able to use different port numbers for different applications. Most servers, as we mentioned, will use non-ephemeral or non-temporary port numbers, but that's not always the case, and you could see applications using port numbers that are in the ephemeral port range. Remember that changing port numbers is simply a way to designate what room inside of the house will be receiving that particular data. It's used for communication, and this is not a security mechanism. You'll still need a firewall to decide whether traffic is truly allowed or disallowed through the network, and simply changing a port number doesn't increase or decrease any type of network security. If you're connecting to a web server, the browser automatically knows that it should be looking for port 80 or port 443 and will use those ports by default. If you change the port numbers of the server, your browser will no longer know how to connect to that web server. That's because we expect web servers to always use port 80 or always use port 443. These are well-known port numbers, and if you change those port numbers, you have to make sure that all of the clients use the new port number instead of what normally would be well-known. Also keep in mind that TCP port numbers are different than UDP port numbers. Although both of them can be between 0 and 65,535, TCP port 80 is a different port number than UDP port 80, and you could theoretically use two different applications with both of those protocols at the same time. Here's how this might be practically configured on our network. In this example, we have a server. Its IP address is 10.0.0.2, and we have a client at 10.0.0.1. These two devices are communicating across the network using three different applications. The server has a web server at TCP port 80, a voice over IP server at UDP port 5004, and it's also providing email services over TCP port 143. This means the client can communicate to the server with all three of those applications simultaneously because they all have different TCP and UDP port numbers. If we were to then look at the IP data that is being sent on a single communication, you can see that this IP address of 10.0.0.1, our client, is sending information to this 10.0.0.2 address. You'll also notice that the client is using a temporary port number for this session. In this case, the randomized temporary port number is 3000. And this device is communicating to the web server, so it's using the well-known port number of port 80. And you can also see there is HTTP data contained within this packet as well. This data is received by the server, and when the server needs to send information back to the client, it simply reverses the TCP source port and destination port and the IP source and destination to be able to send that information back to where the original request was sent. This same process occurs if you're using voice over IP data. In this case, the client is using a source port of 7100 and the UDP destination port would be 5004, which would be the voice over IP service on that server. And for email data, the source port that's being used is a random number of 4407, and the destination port is the well-known port for email, port 143. So every device on the network that is communicating via IP is using this fundamental process to transfer data. This allows us to scale up into a worldwide internet and be able to send data between two devices anywhere in the world.
Acronis, take the headache out of IT security.
As a networking professional, you may be asked to configure port numbers associated with a particular application. So in this video, we'll look at the well-known port numbers associated with those apps. We'll start with a generic form of file transfer that's used across many different operating systems. This is FTP, or the File Transfer Protocol. This is a very common and generic form of file transfer that can be used on Linux, Windows, Mac OS, and practically any other operating system. Unlike many applications that use a single port number to communicate, FTP uses 1 and 2 port numbers, specifically TCP port 20 and TCP port 21. TCP port 20 is commonly associated with the file transfer process itself, and port 21 is commonly sent to send control information between one device and another. FTP has an authentication method, so you can use usernames and passwords, and when you're transferring information, you can choose to not only transfer a file, you can list information in a particular directory, add different files, delete, rename, and perform other types of file maintenance. TCP port 22 is commonly associated with SSH, or Secure Shell. This is a way to communicate to a remote device from a console. So you have this text-based front end, and you're able to configure and manage this device over this text-based command line interface. An important characteristic of SSH is the secure part of SSH, because all of the communication between your device and that remote device is all sent across the network in encrypted form. Well, if there's encryption being used with Secure Shell, it would be great if we could use encryption with our file transfer protocol. So, of course, there is a version of the FTP called Secure FTP, or SFTP. This allows us to transfer files from one device to another, and that entire communication across the network is all encrypted by default. Interestingly enough, Secure FTP is really using the SSH protocol to be able to perform this encryption. So SSH and SFTP use the same port number of TCP port 22. And just like our FTP protocol that allows us to perform file management of that device, we can also perform the same file management using the secure version of FTP. So you can view the directories, you can make changes to the directory names, you can modify files, delete information, and perform all of the normal file management from the Secure FTP application. Both Secure Shell and Secure FTP have that foundation of SSH as the underlying protocol. So not only does Secure Shell allow you that remote terminal communication, you can also have remote file transfer communication, and all of that communication will be encrypted using the SSH protocol over TCP port 22. Before we had encryption over SSH or Secure Shell, we used a non-encrypted form of terminal communication referred to as Telnet. This stands for Telecommunication Network, and it commonly uses TCP port 23. Visually, this looks almost identical to what we use with Secure Shell. The difference, however, is the communication that we're sending between our device and the remote station is all being sent in the clear. There's no encryption that's taking place across the network. This means that someone could potentially capture those packets and view everything that's being sent back and forth over the network, including your login credentials. It's for this reason that you don't commonly see Telnet being used on our network, and instead we'll use SSH to ensure that all of this communication will always be encrypted. Another important application on our network is the use of email. And of course, we need protocols to be able to transfer these emails from one email server to another. To be able to do that, we use SMTP, or the Simple Mail Transfer Protocol. SMTP is commonly associated with server-to-server email transfers using TCP port 25. All of this traffic sent over TCP port 25 is sent in the clear, or in plain text. There's no encryption that's automatically configured when using TCP port 25. That's why many SMTP servers will use TCP port 587, which is SMTP using TLS encryption, or the transport layer security. SMTP is also used from client devices that are sending email messages, and it's often sending those to a mail server using this SMTP protocol. For receiving email messages and being able to manage your email inbox, we often use other protocols such as IMAP or POP3. So anytime that you are sending email or you're transferring email between email servers, you're probably using SMTP or the Simple Mail Transfer Protocol.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless. Get $20 off your first order. We'll deliver your groceries in our refrigerated trucks and bring them to your door. King Soopers, fresh for everyone.
The finest luxury fragrances are now exclusively available at your local store. Unstoppable's unlimited collection makes everything smell magnifique. Luxury Montre Saint-Pete, so you can smell unstoppable.
We don't often memorize the IP address of devices that we communicate with. Instead, we use the Fully Qualified Domain Name, or FQDN. And the way that we translate between the Fully Qualified Domain Name and the IP address is we use a DNS server, and that stands for Domain Name System. DNS commonly uses UDP port 53 to be able to perform this name query. So we'll ask a DNS server what the IP address of www.professormesser.com might be, and it will respond back with the IP address that your device can use to communicate to that server. For those small queries, we commonly use UDP port 53, but if there's a large transfer of data from one DNS server to another, we commonly would use TCP port 53. These DNS servers are obviously very critical resources because without them, we wouldn't be able to communicate to servers such as ProfessorMesser.com. This is also a very common protocol to find on the network, and if you take a packet capture, you're almost guaranteed to capture some type of DNS traffic. We've become very accustomed to simply plugging into a network or connecting to a wireless network and automatically being able to communicate across that network. But behind the scenes, there is an automatic IP configuration process using DHCP, or the Dynamic Host Configuration Protocol. This is the protocol that allows us to automatically configure IP address settings for anyone that connects to the network. By default, DHCP uses UDP port 67 and UDP port 68. To be able to use DHCP, we need a DHCP server. At home, we commonly use a DHCP server that's integrated into an existing wireless router, but in an enterprise network, there are often standalone DHCP servers. We usually configure a pool of IP addresses on DHCP, and anyone who connects to the network will be automatically assigned an IP address from this available pool of addresses. There's also a lease time associated with this IP address, so you're only able to use that IP address for a certain amount of time, and if you are still using that address at the end of the leasing period, you can choose to renew that lease with the DHCP server. We can also configure certain devices to always receive the same IP address every time they connect to the network, and we associate that IP address with the MAC address of that device. We configure that in the DHCP server. That's often referred to as a DHCP reservation. All of this communication that occurs across the network for DHCP will almost always use UDP port 67 and UDP port 68. We talked earlier about the FTP, or file transfer protocol, that we use to send files from one device to another. and we described the process of authentication and the many different management functions associated with FTP. But what if you just needed to transfer a small bit of configuration information from one device to another? You don't need to view the name of a directory or change any of the file names. You simply need to transfer a small amount of information very, very quickly. To be able to do that, you might use TFTP, or the Trivial File Transfer Protocol, and by default, it uses UDP port 69. You'll often see TFTP used for very simple file transfers. Usually, this is something that doesn't require any type of authentication or login process, so it may be something like a voice over IP device that has no IP address and no configuration. And when you plug it into the network, it is powered on using power over Ethernet. It uses DHCP to get an IP address, and then it uses TFTP to be able to download the latest configuration file from the server. This is a quick and easy process. It transfers data without any extra overhead, and it's able to do that very efficiently and very quickly using UDP port 69. If you're communicating to a web server, you're probably using one of two different port numbers. This is using HTTP or HTTPS. This stands for Hypertext Transfer Protocol, and it's a communication that is commonly associated with browser-based communication. If the information between your browser and the web server is being sent in the clear without any type of encryption, it's commonly using TCP port 80. If you need to perform encryption of that data, and that is probably the default for most websites that you'll visit these days, it is using SSL, that stands for Secure Sockets Layer, or a newer version of SSL referred to as TLS, or Transport Layer Security. If this is encrypted data, then it's probably using TCP port 443, which is sending HTTPS for secure. Another thing you may notice with the devices that are connected to the network is they all tend to have the correct time and date, down to the second level. We're able to do that through an automated process called NTP, or the Network Time Protocol. Every device on the network, operating systems, routers, switches, and any other device, can use NTP to stay synchronized with their clock across all of those different devices. By default, NTP uses UDP port 123. Being able to synchronize these clocks is more than simply a convenience. In fact, it can be a very critical part of synchronizing log files between very diverse devices. This allows us to go back in time and piece together communications, even though that communication occurred on many different devices. This is a process that usually occurs automatically behind the scenes, and many devices will synchronize their clock multiple times during the day using the NTP protocol. You might also be able to configure this process. Maybe you'd like a device to update its clock every hour, or maybe simply updating once a day is sufficient. This is also a very accurate way to keep these clocks in synchronization. And usually we get about a 1 millisecond difference between devices that are all on the same network. This provides a level of granularity that's sufficient for most applications, and it's something that occurs automatically using UDP port 123 and the Network Time Protocol. As a network professional, you'll be responsible for the uptime and availability of routers, switches, firewalls, and many other devices on the network. One way to manage those devices is through a protocol named SNMP, or the Simple Network Management Protocol. By default, SNMP uses UDP port 161 to query devices and receive information about how that device may be performing. For example, we might have a management station, and we might be querying a device to determine how much traffic has traversed that particular device over a certain amount of time. And then it can provide us with a summary of how much data has been transferred over that time frame. We can then store that data, create graphs, reports, and other information that allows us to manage that device. You might also find that different versions of SNMP may be used on your network. Version 1 of SNMP is the original version. This allows your management station to perform a single query to this device and receive a single response, and all of this is sent over the network in the clear with no encryption. Version 2 of SNMP allowed for bulk transfers, so we can ask for many different variables from this device and receive a large group of data from that device, which simplified the network communication and made it much more efficient. But it didn't provide any type of encryption. All of this information is still being sent across the network in the clear. A more modern version of SNMP is what you may commonly find on your network today, which is version 3. This is a more secure standard for SNMP, which allows message integrity, authentication, and encryption of the SNMP data.
Building your cybersecurity stack isn't rocket science. Simply create your own security apps with Solar. Get answers to the security questions you really care about and act on them instantly. Set up custom alerts, build workflows, or create dashboards. And guess what? No code needed. Don't want to DIY that ish? Sola's app gallery has plug-and-play apps ready for you to use. And with Sola AI, you get your own super talented security wingman. It can do all the work for you. Whether you just need to tie together some loose ends or build up your security stack, Sola's there for your needs. It's simple, quick, and free. Get security done with Sola.
This is a hot flash. This is a not flash. This is a hot flash. This is not. If you have hot flashes and night sweats due to menopause, ask about Veoza, the #1 prescribed hormone-free treatment approved for moderate to severe vasomotor symptoms due to menopause, so you can have fewer hot flashes and more not flashes. Veoza reduces the number and severity of hot flashes day and night. Veoza can cause serious side effects, including liver problems. Your doctor will do blood tests before and during treatment. Stop Veoza and call your doctor if you have symptoms of liver problems, such as feeling more tired than usual, decreased appetite, nausea, vomiting, itching, yellowing of the eyes or skin, pale stool, dark urine, or stomach pain. Don't use Veoza if you have cirrhosis, severe kidney problems, kidney failure, or take CYP1A2 inhibitors. Ask your doctor about more not flashes with hormone-free Veoza. Visit Veoza.com.
One of the things you'll find with this default use of SNMP is the management station is interactively making a query and then receiving a response for that query. So it's up to the management station to initiate that communication. But it would be nice if these devices could identify problems and proactively send that information down to the management station. We can do that by using a feature of SNMP called an SNMP trap. This allows these notifications to be sent directly from these devices using UDP port 162. Many organizations may have hundreds or thousands of devices on their network, and it may be a challenge to be able to keep track of what devices are on the network, what users are connecting to those devices, and how the relationship might be between the user and the device. We're able to maintain a database of all of these devices and all of these users through a protocol named LDAP. LDAP stands for Lightweight Directory Access Protocol, and it commonly uses TCP port 389. LDAP allows us to very easily query these databases and retrieve information that we may have stored. There's also a secure version of LDAP called LDAP Secure. It uses TCP port 636. LDAP uses a hierarchical structure to be able to lay out the network and the devices. This is a graphical view of an LDAP database. It starts with the root of the database, which is an organization. In this case, the organization is Messer Studios. We've also grouped together like devices into organizational units. There is a production OU, a support OU, and an engineering OU. Within those organizational units, there may be common named devices. For example, there may be users such as Jack and Daniel, or there may be a database or storage device named TechDocs. We're able to organize and access these devices through this structure, making it a very common and simplified way of gaining access to this data. Microsoft Windows has some very unique features when it comes to data transfer. Microsoft stores information on the network in a file share. You can also share printers through Microsoft's operating systems, and there is also authentication built into this entire process. To be able to provide all of this functionality, there is a specialized protocol named SMB, or Server Message Block, to be able to share files, share printers, or authenticate to the network. You might also see this referred to as CIFS, or the Common Internet File System. SMB is integrated into Windows itself. You don't need to add additional software. There's no additional FTP or SFTP process. Instead, built into the Windows Explorer or the File Explorer within Microsoft Windows is the SMB functionality that allows us to access file shares, print to remote printers, lock different files on the network, and provide processes for authentication and permissions for all of that data. Early versions of Microsoft Windows used the NetBIOS protocol to be able to facilitate this communication. But most modern versions of Microsoft Windows communicate directly across the network using IP, and TCP port 445 is the one that is usually associated with Server Message Block or SMB. As a network professional, you'll find that you are constantly referring to logs that are being kept on your routers, your switches, your firewalls, your servers, and almost any other device that's connected to the network. One challenge is being able to consolidate all of these different log files to one single location, and there is a standardized protocol for transferring these log files called syslog. Syslog commonly uses UDP port 514 to be able to transfer this log data across the network. You'll often use syslog in conjunction with a security information and event manager, or a SIEM. This is a consolidation point where you can have all of your log files transferred into one single consolidated database. So if you're using syslog and transferring that over UDP port 514, you're probably transferring it to a very large drive array or some other device where you can collect that log information over an extended period of time.
People can go crazy trying to stop a cyber attack. Acronis take the headache out of IT security.
Go get rain.
And clear the closing doors, please.
We store a lot of very diverse information on our databases, but fortunately there is a very common form of storage and retrieval for those databases referred to as a structured query language, or SQL. Some people refer to this as SQL. This SQL database uses a standard language that you can use to be able to query and retrieve information from that database. Microsoft has its own form of SQL database called the Microsoft SQL Server, or MS-SQL. It stands for Microsoft Structured Query Language, and it very commonly uses TCP port 1433. There are other types of SQL databases you might find on your network, and they usually use different port numbers. So if you see TCP port 1433, then you're probably using a Microsoft SQL Server. Many of us start on the help desk to be able to provide support for our end users. And one way that we're able to view the remote desktop of those devices is through the use of RDP, or the Remote Desktop Protocol. RDP uses by default TCP port 3389 to be able to view that remote desktop. The Remote Desktop Protocol is commonly associated with a service that's running on a Windows device. But fortunately, there are many clients that can use RDP to connect to those Windows devices, so it's not unusual to find RDP clients for Windows, macOS, Linux, iPhone, Android, and many other operating systems. There are many different protocols used for voice over IP. One of the most popular is SIP. This is the Session Initiation Protocol, and it commonly uses TCP port 5060 and TCP port 5061. SIP is commonly used as the control protocol that we use when we pick up the phone, we dial the number, it initiates the phone call, and then when the phone call is over, it disconnects the session. You might also see SIP being used for extensions of voice over IP that provide video conferencing, instant messaging, and even file transfers. All of this takes place using SIP over TCP port 5060 and TCP port 5061. There will be many times as a network professional when you'd like to know if a device is on the network and operating. And one protocol that can provide you with that is ICMP. This is the Internet Control Message Protocol. You can think of this as a way to check in with that device, very similar to sending a text message to see if you get a response back from someone. ICMP is another protocol carried by IP, but it doesn't use TCP or UDP. Instead, ICMP is its own protocol. Although ICMP can be used for a number of administrative tasks, it's most commonly associated with a way to send a message to a device to see if it's alive and operating on the network and see if you can get a response back from that device. Whenever you use the ping command to ping an IP address on the network, it's using ICMP to provide that ping functionality. But ICMP can also provide you with information about other things that may be happening on the network. For example, if you're trying to access a network that is not accessible from your location, ICMP will give you a message that that network is not reachable. Or ICMP can tell you that the time to live that's inside of data that you've sent has expired and it's received an ICMP time exceeded message from that device.
Get fresh groceries delivered to your door with Kroger Delivery, proudly serving King Soopers.
Dad, this guy says that we act like Gillette Labs is some miracle, but it's just another razor?
Gillette Labs ain't a miracle, but it sure as heck ain't my old razor. It's Gillette's best shave. And with up to 30 shaves per cartridge, I'm spending less. Its ultra-sharp blades last 50% longer.
And give you a fresh blade feeling time after
Time after time after time. Gillette Labs, the best a man can get.
Keeps getting better.
Another common protocol on our network is GRE, or the Generic Routing Encapsulation Protocol. If you're creating a tunnel between two endpoints, this is commonly done with VPNs, for example, you're creating this tunnel using GRE. This allows us to encapsulate information within an IP packet, send it across this GRE tunnel, and decapsulate it on the other side. This does not, however, provide encryption of this data. We'll need to provide additional VPN protocols to encrypt the data that we are encapsulating in a GRE tunnel. These VPN protocols are referred to as virtual private network protocols, and it's very common to use these VPN protocols to encrypt or protect any data being sent across one of those tunnels. It's often common to use a purpose-built appliance to provide this encryption and decryption process at the central point. We refer to this as a VPN concentrator. Sometimes this is a standalone unit. It's very often integrated into an existing firewall that's connected to the network. These concentrators are often hardware devices with specialized encryption hardware built into the device to add efficiency and throughput. But if you have a limited number of users, it's also possible to use your VPN concentrator as software in an operating system. This is a common site-to-site VPN configuration where a corporate network may be connected to a remote site over a public network such as the internet. We'll have VPN concentrators, which are usually firewalls or routers. Those are connecting these two sites together over the internet, but all of this traffic that's being sent across that public internet is being encrypted using this VPN technology. One of the popular protocols used to provide that level of encryption over those tunnels is IPsec. This stands for Internet Protocol Security, and it's one of the most popular ways to encrypt data being sent across these VPNs. Not only does IPsec provide encryption for confidentiality, it can also provide digital signatures of every packet, which includes integrity and anti-replay functionality. This is also a very common protocol, and it can be used across many different manufacturers' devices. For example, you might have a firewall from one manufacturer on one side of a VPN tunnel, and a firewall from a completely different manufacturer on the other side of the VPN tunnel. Because IPsec is such a standard protocol, those two firewalls can easily connect to each other and transfer information over that IPsec tunnel. When you're using IPsec, there are commonly two primary protocols that are in use. One is the Authentication Header, or AH, and the other is the Encapsulation Security Payload, or ESP. In order for IPsec to be able to send this encrypted data across the network, we first need to create this tunnel. And we do this by performing a series of steps prior to sending any data. Those steps are referred to as the Internet Key Exchange, or IKE. Internet Key Exchange allows both sides of the conversation to agree on the encryption and decryption keys that will be used for the duration of that VPN tunnel. We refer to this agreement as a security association, or an SA. There are two phases to this key exchange process. The first phase commonly uses Diffie-Hellman to create a shared secret key for both sides of the conversation. This usually operates using UDP port 500, and we refer to this as ISACAM. This is the Internet Security Association and Key Management Protocol. In phase 2, we coordinate which ciphers should be used for the encryption and the key sizes that would be appropriate, and it negotiates both the inbound and outbound security association to be used for this IPsec tunnel. So visually with phase 1, we're building the ISACAM tunnel over UDP port 500. In phase 2, we're including the encrypted data over the encapsulation security payload, or ESP tunnel. This gives us the foundation we need to be able to send this encrypted data over the IPsec tunnel. If you're building your own IPsec tunnel, you may be asked whether you'd like to use transport mode or tunnel mode. Both of these work differently and will protect data in different ways. Let's take the original packet, which includes an IP header and some data within that IP packet. We would like to send that over an IPsec tunnel. If we use transport mode to send this IPsec data, we're going to insert an IPsec header between the IP header and the data. All of that is going to be in the clear. Anything within the data portion of that IP packet will be encrypted, and then the IPsec trailer is put at the end of the packet. Notice that the original IP header is not encrypted when using transport mode. And if someone does capture this data, they'll be able to see the original IP header and be able to understand where this traffic is intended to go, even if they can't see the encrypted data within the packet. A much more secure method of using an IPsec tunnel is tunnel mode. In tunnel mode, the original IP header and data is all encrypted, and even if you capture this data, you'll never know what the original destination is for this data. Tunnel mode adds a new IP header, which includes the destination of the IPsec concentrator and includes the same IPsec headers and IPsec trailers that we saw in transport mode. It's probably not too surprising that most implementations of IPsec are going to use the tunnel mode to ensure the highest level of encryption of your original data. Earlier, we mentioned the two protocols that you commonly see associated with IPsec. One of those protocols is the authentication header, or AH. AH is used to validate the information that you're receiving over an IPsec tunnel. And if you're only using authentication header mode, you're sending all of this information over the network in the clear, but you're including some additional hashing to ensure the integrity of this data. However, in most cases, we want to be able to encrypt the data that we're sending over the IPsec tunnel, and for that reason, we'll use encapsulation security payload, or ESP. This protocol is going to encrypt that original data and encrypt the trailer that we're associating with ESP, and then put around this packet a new IP header, an ESP header, and an integrity check value at the end of the packet. This is going to encrypt all of your original data, but also provide the authentication that you need to ensure that the data is received properly on the other side.
The 5-year price lock guarantee is back. It's 5 years of lightning fast gig speeds, 5 years of advanced security, all at a great rate. That's the Comcast Business 5-year price lock guarantee.
Lowe's knows when you need a new appliance, you need it fast. So we offer next-day delivery on hundreds of appliances. Plus, members save more. And we'll haul away your old one. When you need it fast, we've got you covered. Shop Lowe's today. We help, you save.
A unicast is one of the more popular ways of sending information across the network. It is when one station sends information directly to another station. This is a one-to-one relationship, and nothing within that conversation is ever sent to anyone else on the network. If you need two devices to be able to send information to each other and no other device on the network will be involved with that conversation, then you're probably using a unicast. So anytime you're connecting to a website, you're transferring files, or you're checking your email, it's probably all taking place with a unicast communication. This one-to-one relationship is also one of the disadvantages of unicast, especially if you need to send information to many people simultaneously. With unicast, you would have to build separate one-to-one communications with all of those individuals, and you would have to send separate data for each individual device. But for single communication between you and another device, whether you're using IPv4 or IPv6, you're probably going to use unicast. To be able to efficiently send data to multiple devices at the same time, then you'll probably want to use multicast. Unicast is a one-to-many of many communication, so when you send information out, it is sent to multiple recipients all simultaneously. These recipients are usually subscribing to your multicast feed. So if someone is trying to receive multimedia, they're receiving stock exchange information, or maybe a device is sending out routing updates, you can send those out via multicast addresses. Multicast is relatively specialized, and it requires that equipment understand and recognize how to deal with multicast communication. This is why we don't use multicast when we're sending information across to a different network or even within a very large network. But we do use multicast quite a bit with IPv4 and IPv6, and in the right environment, it can be a very efficient way to send and receive traffic. Multicast is used where one device needs to send to many of many devices. Anycast is used when one device needs to send to one of many devices. This is where a single destination IP address may be sent to one of many different devices that are on the network, and it's something that you'll commonly find with both IPv4 and IPv6. In this scenario, the devices that are receiving the anycast communication are all configured in very similar ways. This allows the originating device to simply send data to the unicast address, and whatever device is closest is going to receive that traffic. A good use case for anycast would be something like anycast DNS, where a DNS query can be sent out on the network, and the closest data center will be able to respond to that anycast DNS request. And if you want to send a frame to everyone who's on your network, then you'll want to send a broadcast. This is a one-to-all relationship where a single packet is sent out and everyone on the network receives that single packet. Fortunately, the scope of this is limited to your local broadcast domain. So there's no way to send a broadcast frame from your local network and somehow have that frame appear everywhere else on the internet. This is a type of communication that's best fit for something like routing updates or ARP requests. And although this is something that you will commonly find with IPv4, we decided with IPv6 to remove broadcast completely and go to a multicast form of communication instead.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Sola, the studio where you can build any security app. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. You fit Sola to your needs. It's simple, quick, and free. Get security done with Sola.
At Sprouts, our wide open layout invites you in.
I know that all.
With healthy around every corner and tasty on every shelf. This is that Sprouts feeling.
If you connect to a network at work or at home, then you're probably very familiar with wireless networks. You may have also noticed that no matter where you go with your wireless device and whatever network you connect to, you always seem to have the required connectivity. This is because there is an international standard for wireless network that's managed by the Institute of Electrical and Electronics Engineers, or the IEEE. The The IEEE standard for wireless networks is in their standards committee for the 802 series, specifically 802.11. So anytime you hear anyone mention 802.11, they're referring to the standards associated with wireless networks. Another interesting characteristic of wireless networks is that they are constantly evolving and constantly changing. So you'll want to check in with the IEEE standards to see which type of wireless network you're using. There's another organization involved with wireless networking called the Wi-Fi Alliance. You'll notice there's a Wi-Fi trademark logo on every device that the Wi-Fi Alliance has tested. This ensures interoperability with the standards that are set by the IEEE. In the past, we used to refer to these wireless networks with their standards name. For example, 802.11b or 802.11ax. We've recently added additional names to these standards to make them a little easier to understand for everyone who's connecting to these wireless networks. For example, if you're using the 6th generation of Wi-Fi networks, then you're connecting to an 802.11ax network. But we also refer to this network as Wi-Fi 6. This chart shows a list of all of the major Wi-Fi standards listed by their 802.11 name. I've also included the new generational name for those standards, the frequencies they happen to use, and the maximum theoretical link rate for each of those standards. The first three of these standards, 802.11a, b, and g, are rarely used today, and we did not formally set a generation name to those, although you could colloquially refer to these as Wi-Fi 1, Wi-Fi 2, and Wi-Fi 3. The newer standards of Wi-Fi 4 through Wi-Fi 7 are covered through the standards of 802.11n through 802.11be. You'll also notice there's a difference on the type of frequencies that are used for each of these standards, and most of these refer to the 2.4 gigahertz, the 5 gigahertz, and the 6 gigahertz ranges. There are a number of differences on how these wireless standards can be implemented. There might be a different number of antennas or a different number of radios, and that accounts for the differences in the theoretical link rates that you see in this final column. Notice as we've introduced newer standards of wireless networks that we've also increased the overall link rate of those networks. But we use more than our local 802.11 networks for wireless networking. If you have a mobile phone or a mobile tablet, then you're probably using a wireless provider's network that uses 4G, LTE, or 5G technologies. LTE stands for long-term evolution. It is what we refer to as the 4G technology, and it was a conversion between different standards of GSM and CDMA into a single standard that every provider can use. These 4G networks supported download rates of approximately 150 megabits per second, and the improved version of LTE, which is LTE Advanced or LTE-A, supports download rates that double that to 300 megabits per second. A more modern version of mobile networking is the 5G networking that was introduced in 2020. This greatly improved the performance of wireless mobile networks, and with the right configuration, the goal will be to have 10 gigabits per second as the overall throughput. And in other implementations, you may see more reasonable speeds, such as 100 to 900 megabits per second. 5G has dramatically changed the way we look at mobile connectivity, especially since we're now able to get similar bandwidths over our mobile providers that we currently have with wired network providers in our own homes. This also means that we're able to greatly increase the size of our Internet of Things, or IoT footprint, because now bandwidth is no longer a constraint. This means we can transfer much more data over a shorter period of time. We can receive notifications much faster than we could in the past, and because we can transfer more data, we can process more of that data in the cloud. There may be times when an organization might have a remote location that is not accessible through any type of traditional internet connectivity. For that reason, we may want to use a non-terrestrial form of connectivity known as satellite networking. This means that we can add a satellite dish to a location and begin sending and receiving data from the satellite. This obviously adds additional cost and complexity, and the speeds of satellite networking, although reasonable, are not as fast as those we might have for traditional terrestrial-based networking. For example, satellite networking can commonly provide you with 100 megabits down and 5 megabits up. This means that if you have a remote site that has no other way to communicate, you can add a satellite dish to the roof and begin communicating directly to the internet. As you can imagine, there is a delay as information is sent into space and back down to Earth again. Traditional satellite networking provided 250 milliseconds up and 250 milliseconds down, so each conversation to and from the satellite took approximately half a second. Newer technologies such as Starlink advertises a 40 millisecond latency, and they're working to decrease that down to 20 milliseconds. Another challenge with satellite networking is that it requires a direct line of sight to the satellite that's in orbit above the Earth. This means if anything does get between the satellite receiver and the satellite, then we may have a decrease of performance or lose connectivity altogether. For example, if a thunderstorm was to come through, we would suffer through what we call rain fade, where we lose connectivity while that storm is going over. In those situations, it may be necessary to wait for the storm to blow through, or we may have other forms of connectivity that we might use when a storm is currently active.
People can go crazy trying to stop a cyber attack. Acronis, take the headache out of IT security.
This Charmin Ultra Soft Smooth Tear has wavy edges.
It's no ordinary square. Charmin Ultra Soft Smooth Tear has wavy perforations that tear so much better, with more cushiony softness. Enjoy the go with Charmin.
If you've connected your computer to a wired network, then you're probably using Ethernet. Ethernet is the most popular networking standard in the world, and almost any device you use will be able to connect to an Ethernet network. There are also many different types of Ethernet. They vary in speed, the type of cabling we use, the connectors at the end of these cables, and the type of equipment that's required to connect all of these devices together. Our modern Ethernet networks have many different standards for both twisted pair copper cabling and for fiber optic connectivity. The reason we're able to connect any device in the world to any Ethernet network and be able to have this connectivity is because there is a single set of standards for all of these Ethernet networks. Those standards are created by the IEEE 802.3 committee. IEEE is the Institute of Electrical and Electronics Engineers, and they're responsible for designing and documenting the standards we use to connect all of these Ethernet networks together. For example, a very common Ethernet network would be 1000 base T. This is a gigabit Ethernet network that operates over twisted pair copper cabling and operates at a speed of 1 gigabit per second. A newer version of that standard is the 10G base T, or the 10 gigabit Ethernet network. This also uses twisted pair copper cabling and operates at a speed of 10 gigabits per second. There are also Ethernet networks that use fiber optics. An example of that would be 1000 base SX, which is a gigabit Ethernet network that uses fiber optics and operates at a speed of 1 gigabit per second. This is just a sample of a few of the more popular Ethernet standards, but there are many Ethernet standards to choose from, using different types of media and supporting different speeds. The IEEE has told us that the names they use for these standards don't necessarily correlate back to the details of the standard, but there's usually some information that we can discern from the name itself. For example, if we look at a standard such as 1000 base T, we should be able to break that term apart and determine what type of media and technology is used as part of that standard. For example, the number that's used in the name of the standard is often related to the speed of the standard itself. For example, the 1000 base T, that 1000 refers to the 1000 megabits per second, or 1 gigabit per second overall speed. If this standard started with 10G, then it would be related to a 10 gigabit per second network. We often see the term base in the name of the standard, and that's referring to the term baseband, which means there is a single frequency that is used to be able to send this data over the network. This is in contrast to something like broadband, which uses many different frequencies to be able to communicate across that network. And very often you can determine what type of media is associated with that standard by looking at the additional letters at the end of the standard. For example, 1000 base T has a T at the end, and we can assume that that T means that this is twisted pair copper. If there was an F at the end, it's very possible that this particular standard would use fiber optics. There may be additional letters at the end of the standard. For example, if there's an SX at the end of the standard, it might be referring to a short wavelength light that is sent over that fiber optic connection. As mentioned previously, the IEEE tries to put the name and terms within the standard so that it would be recognizable. That is not a requirement for the name of the standard itself. If you were interested in the details of what that standard supports, you would need to read the entire standard and not just look at the name of the standard.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless. Get $20 off your first order. We'll deliver your groceries in our refrigerated trucks and bring them to your door. King Soopers, fresh for everyone.
Many of us are accustomed to using twisted pair copper, especially if we have networks that we use at home or even at our office. But you may occasionally have a need for fiber optic connectivity, and that fiber optic connectivity allows you to send traffic across the network using light. These are often used on very secure networks because it is very difficult to tap into a fiber optic connection without having some type of notification. This is very different than a copper-based network, which uses RF and is relatively easy to tap and gain information from. Fiber optics are also used over very long distances because the signal doesn't degrade as fast as a radio frequency might. So the same signal that we can send over 100 meters of a copper network might be able to be sent over kilometers if you were using fiber optics. And of course, light is not susceptible to any type of radio frequency interference. And if you're working in an environment where there is interference, you might want to use fiber optics to avoid any type of problem with your network. Just as there are many different standards and many different connectors for copper-based networks, there are also many different standards and connectors for fiber optic networks as well. So you'll want to check the configuration and documentation of your devices and make sure that the fiber optics that you're connecting are using the right type of fiber and the right type of connector. If we were to deconstruct a fiber optic cable, you would have something very similar to this. On one side of the cable is the light source.
All right, everybody, looks like we have made it to lunchtime.
This LED is sending a light through this fiber optic.
So don't forget to log out from class, and I will see you in an hour. We'll pick up a lesson this
Around the
afternoon.
core is a low reflected cladding, and the entire fiber optic run is protected with a buffer coating around the outside. Here's the connector that's at the end of a fiber optic cable.
I gotta go to TA hospital
around the
after this.
outside of the fiber.
Oh, no problem.
Very closely at the
I may not be
middle
back
of this connection.
after,
You
so
can
just
barely
let you know.
make out the
Okay,
core
no
of the
problem. Thanks for
fiber
letting me
that's in
know.
the middle.
Whatever you need,
I'll
we'll get you
highlight
caught
it
up
here
if you
so
need
that
it.
you can really
Thank
see
you.
where that
All right.
happens to be. Let's remove
Bye-bye.
that highlight. Now you can start to see that discoloration where the fiber is connected on the end of that cable. We will generally install one of two different types of fiber optic cables. One is a multi-mode fiber and the other is a single mode fiber. Multi-mode fiber is commonly used for relatively short range communication. This would be up to around 2 kilometers in distance. And often this uses a fixed light source such as a light emitting diode or an LED. The core of the fiber optic is relatively large, certainly larger than the wavelength of the light. And because of that, the light itself can use different modes to be able to transmit through that fiber. And you can see the different modes bouncing off the edges of the fiber optic cable itself. Because there are different modes that are being communicated through this fiber, we refer to that as multi-mode fiber. If we're communicating over a much longer distance, we may want to use single mode fiber. Some standards of fiber-based Ethernet can communicate up to 100 kilometers without needing to regenerate the signal. Because we're going a longer distance, we may be using a very bright and intense LED, or we may be using laser to be able to extend this signal much further. A single mode fiber also has a smaller core, which can only allow a single mode of light to propagate through the fiber.
What's offsides? And how can I sound like I know a lot about the game? You can just ask Google all of that at once. Oh, so that's it.
Cabling is the foundation of everything we do in networking. Whether you're using a router, a switch, a wireless access point, or any other infrastructure device, cabling is going to be a critical part of that communication. Once the cabling is installed, it's very difficult to uninstall or remove that cabling and replace it with something else. So make sure you're using the right cabling for the right infrastructure. And even if your network happens to be mostly wireless, eventually that wireless connection will need to connect to a cable. So you need to make sure you have the right cables installed in the right place to be able to provide the best possible throughput of your network. One of the most common cable types is the twisted pair copper cable. This is something we use for practically all wired Ethernet connections, and it usually consists of multiple wires twisted together within a single sheet. You'll often see that the cables themselves are paired together. That's because there's often one type of signal on one of the wires and a reverse of that signal on the other wire. You may see this written as transmit plus or transmit minus, or receive plus and receive minus. The reason that we have the same signal being sent in different forms is so that we can recognize and correct if there happens to be any type of interference. This twist in these two wires means that at least one of these wires will always be moving away from interference. This allows us to compare these signals on the receiving end to determine what the actual signal should look like. Another interesting part is that the different cable pairs have different twist rates. So if you look very carefully at an individual cable, you'll notice that some pairs of cables are twisted much tighter than other pairs. One common misnomer that I often hear about cables is that a certain cable has a particular speed. But in reality, the cable doesn't have any speed at all. The copper is literally just sitting there in the cable. The cable itself is supporting a signal, and that signal is allowing us to send a certain amount of data over that particular type of connection. The specific Ethernet standard that you're sending over that wire determines just how much data you'll be able to move across that particular cable. If you're ever wondering what type of cable you should be using for the type of Ethernet network that you have, you should go back to the 802.3 standards. Those standards will specify the minimum cable type that's allowed for that particular standard, and it will specify the type of signal and the total throughput expected over that cable. To be able to easily determine the type of cable that's appropriate for a specific Ethernet standard, we've created a set of standards for the cables themselves. We refer to these standards as a category of cable. For example, you might find category 5, category 6, or category 7. If you check the Ethernet standard, it will specify the minimum category of cable that is required for that particular standard. For example, if you're using 1000 base T, you can look at the 1000 base T standards from the IEEE, and it will tell you that the minimum cable category for that specific Ethernet standard is a category 5 cable. If you install category 5 cable or anything above category 5, it will work properly with the 1000 base T standard. Although twisted pair wiring is very common for our local area networks, another type of Ethernet cable that's very often used is a coaxial cable. This describes a cable where two or more forms within that cable share a common axis. For example, you can see the single wire conductor that's in the middle of this coaxial cable. There's also an insulator, a shielding, and a jacket that are also sharing that same axis. One common type of coaxial cable, especially on our Ethernet and internet connections, is an RG6 cable. If you have a cable modem or you're bringing in a cable modem connection into your data center, it's probably being brought in on a coaxial cable. If we put two conductors inside of this cable type, then we have a twin-axial cable. We often refer to this as simply twin-ax. Twin-ax is a type of cable that you can commonly associate with 10 gigabit per second Ethernet. It's often installed as part of an SFP Plus interface. This allows for full duplex communication over a single cable, but it limits the amount of distance that you can send this signal to about 5 meters. This has a relatively low cost when associated with fiber optics, and very often it has a much lower latency when you compare it to using something like a twisted pair connection. If you're at work and you look at the ceiling, you may notice that you're not seeing the actual ceiling of that floor. Instead, you're seeing a drop ceiling and something like acoustic tiles that is sitting above the actual ceiling. There is a space between this drop ceiling and the actual ceiling, and we refer to that space as the plenum. Inside the plenum, we may have network cables, there might be heat sensors, you might have cables for power, there may be other pieces of the infrastructure that run inside the plenum as well. In some environments, there may be a drop ceiling, and above the drop ceiling may be ductwork where all of the air supply happens to flow. You may have air supplied as part of a heating or cooling system in that ductwork, and there may be return air that's using additional ductwork to go back to that heating or cooling system. Since a plenum implies that there is a shared airspace in a configuration such as this where only ductwork is used to transfer the air, there would be no plenum. But if there's no ductwork and we share this same airspace with all of our networking cables, then we need to consider that we're using the proper type of network cables in that shared plenum. This would obviously be a concern in a fire, especially if we're using a network cable type that produces a large amount of smoke or perhaps even hazardous fumes if it was to catch on fire. If this was in a plenum, that smoke and those fumes would be distributed to everyone in the building. This means we need to make sure we're installing the correct type of cable if we happen to be installing this into a shared plenum. Ethernet cables have a jacket on the outside of the cable, and many of those Ethernet cables are manufactured with a polyvinyl chloride or PVC manufacturing. If you're putting this cable into a plenum, then you need a plenum rated cable, and that cable is usually manufactured with a fluorinated ethylene polymer, FEP, or a low smoke polyvinyl chloride, PVC. This plenum rated cable is designed to be much safer in a fire than one that is not designed for a plenum. One challenge when working with plenum rated cable is it may not be quite as flexible as non-plenum rated cable. So if you're going around a lot of twists and turns, it may be a bit more of a challenge to install that cable into the plenum. So if you're installing cable into a new building or you're replacing cable in an existing building, make sure you see where that cable is being run and you use the correct type of cable for that location.
L-pads are gentle and powerful, made without synthetic pesticides or fragrances, and powerful all-day leak protection. Choose L and choose love.
Transceiver is a combination of two words, transmitter and receiver. And these are usually combined within the same piece of equipment or the same component. A transceiver allows for modularity. You may have a switch like this one. You can see there are a number of open interfaces in this switch. You slide in the transceiver that's appropriate for the media or the network type that you would like to use, and now that particular interface will operate with that particular configuration. So if you need a copper configuration for gigabit Ethernet, you slide in a copper gigabit Ethernet transceiver. Or if you need a fiber-based 10 gig connection, you slide in a 10 gig fiber transceiver. This means that you could have every interface on the switch have a different type of media depending on what transceiver you were planning to use. There are different types of transceivers, different form factors, and different transceivers depending on the media. For example, if you are using an Ethernet switch, you need an Ethernet transceiver. If you're using a fiber channel switch, then you will need a fiber channel transceiver. You can't use fiber channel transceivers in an Ethernet switch or vice versa. This means you get to decide what media type works best for your configuration. If you need copper connections, you can use a copper transceiver, and if you need fiber connections, you can use a fiber transceiver. And if you need to change those connections midway through your installation, you can remove the copper transceiver and replace it with a fiber transceiver. This type of modularity often comes at an additional cost, but it does provide you with a way to plug into whatever network type you might need. One common transceiver type is the SFP type. It stands for Small Form Factor Pluggable. For example, you can plug in a fiber SFP and connect fiber connections to that particular transceiver. But if you needed copper, you could easily slide in a copper SFP and plug in your RJ45 connector. SFPs are commonly associated with gigabit Ethernet, so that's 1 gigabit per second. There is an enhanced version of SFP called Enhanced Small Form Factor Pluggable, or SFP+. They look identical in size to an SFP, but they support much higher speeds, up to 16 gigabits per second. So if you have a 10 gig connection, you're probably using SFP+. When you're installing equipment into a rack that's in a data center, you have a limited amount of space available. First, the equipment is only 19 inches wide, and the total amount of space available in the rack is limited by the amount of space you have in the data center. So we want to be sure that we can put as much connectivity into a single space as possible. To that end, we've created the QSFP, or the Quad Small Form Factor Pluggable. This effectively allows you to have 4 times the amount of throughput into a space that's very similar to that of an SFP. For example, an SFP in this form would be a Quad Small Form Factor Pluggable, or QSFP, which consists of 4 channels of SFP. So if one SFP is a 1 gigabit per second connection, a Quad SFP would be compatible with a 4 gigabit throughput. The same thing applies for the SFP+. There is a Quad SFP+, that is a 4-channel SFP+. Since it's common to see a 10 gigabit connection on a single SFP+, a Quad SFP+ can support 4 of those for a total throughput of 40 gigabits per second. This is where we start to see a benefit not only in the amount of space that we're using inside of these devices, but we can take a single fiber connection and effectively extend 4 separate links over that single fiber. There's cost benefit there for equipment and for the media itself. Although the names are very similar, the form factors are slightly different between an SFP and SFP+, and a Quad SFP or Quad SFP+. On the left is an SFP or SFP+. Both the SFP and SFP+ use the same form factor, although the transceivers are obviously very different. The Quad SFP or Quad SFP+ also share the same form factor, but you can see it's slightly larger than the traditional SFP or SFP+. Although it is slightly larger than an SFP, it's not 4 times the size of an SFP, so we are getting an efficiency in space by using a Quad SFP or Quad SFP+. When working with fiber optics, one of the first things you'll notice is there are many different connector types. You have to make sure that you use the right connector type for the right connection. A very common fiber connector type is the SC connector, or the subscriber connector. We also have other names that we associate with this connector. One is a square connector, because the connector itself is rather square when you look at it. You might also see this referred to as a standard connector, although there are certainly other types of fiber connectors that you might use. To use an SC connector, it simply pushes into the connection and snaps in place with a lock. Once you have that connector in place, it's not going to accidentally slip out of that connection. You first have to pull on the connector to unlock it, and then it can be removed from that interface. This is a common connector type, and if you're plugging into a connection in a data center, you're probably using some connections that are identified as SC. The connectors themselves support individual fibers, but they're often combined together into a pair because one of these is commonly used for transmit and the other is commonly used for receive. Another common fiber connector is the LC, or local connector. This is slightly smaller than an SC connector, and as you can see, it has a clip on the top to lock it in place once you put it into the interface. This also means that it won't accidentally get pulled out of an interface, and to remove it, you need to push down on the clip. That will release the lock and allow you to easily remove it from the interface. Instead of local connector, you might also see this referred to as a lucent connector or a little connector. The LC connector can also be combined in a pair, looks like this, and you can plug both of them in simultaneously, and again, one is used for transmit and the other used for receive. Another fiber on our list is the ST connector, that stands for straight tip. It uses a bayonet connector, So you push it into an interface, give it a slight twist, and it is locked in place. This will not easily get removed from the interface unless you reverse that twist, and then you can remove it from the interface. When you're working inside of a rack and there's a large number of cables and fiber, it can be very easy to accidentally dislodge one of those connections. That's why we have all of these different locking mechanisms for these different interface types. Here's a closer view of the ST connector. There is a protective ferrule around the fiber, which you can barely see in this picture, and you can easily see the bayonet connector where you would plug it in and twist it in place so that it is locked into that interface. One of the challenges with the connector types that we've seen so far is that those fiber connections take up a lot of real estate. It would be a lot more efficient if we could put more fiber into a smaller connection, and there is a connector type for that called the MPO, which is multi-fiber push-on. Inside the MPO are 12 individual fibers that are contained in that single cable connection. This also has a lock in place that's very similar to the SC connector, where you would push it in place and you would have to pull it out slightly to unlock it from the interface. You might also see this connector referred to as an MTP. That name is provided by Corning, and they refer to this as an MTP MPO connector. Here's a side view of the connector. It has this lock on the top, and the individual fibers are these smaller dots you can barely see in this picture. If we look at it straight on with some light being sent through the fiber, you can see that all 12 of those fibers are much easier to see on the MPO connector.
Get fresh groceries delivered to your door with Kroger Delivery, proudly serving King Soopers.
One common copper connector we use on our networks today is an RJ11. It stands for Register Jack Type 11. It is a 6-position connector, but we only use 2 conductors inside of this connector. Sometimes you'll see this referred to as a 6P2C, or 6-position 2 conductor. We commonly associate an RJ11 connector with an analog telephone, but you'll also see RJ11 used for DSL connections, since those use exactly the same wires as a telephone connection. Here's a better view of the RJ11 connector, and you can see the 6 positions, 1, 2, 3, 4, 5, 6 are clearly marked, but you notice that there are the 2 conductors in the middle that are used for RJ11. If you're using an Ethernet connection, then you're using an RJ45 connector. This stands for Register Jack Type 45. It is an 8-position connector with 8 conductors inside. So we're using all of the conductors available on an RJ45 connection. This is slightly larger than an RJ11 connector, and it's what you would use if you're plugging in an Ethernet connection. Here's a device that has both RJ11 and RJ45 connectors on it. You can see this is a DSL connection that uses the RJ11, and these LAN connections or Ethernet connections are using the RJ45. You can see that they're very similar in shape, although the RJ11 is slightly smaller than the larger and wider RJ45. If you're using a cable modem connection, then you're probably bringing coax connections and plugging it into a cable modem. And the connector that you're probably using is the F connector. The F connector is a standard connection type. It usually has threads inside that allow you to fasten it very securely to the connector. And if you are using a cable modem, this is probably the connection type that you're using from the cable television infrastructure. This is also referred to as a DOCSIS connector, that stands for Data Over Cable Service Interface Specification. The connection that brings the signal is this single copper connection on the inside of the cable. This is what you would plug in and screw into a cable modem using that F connector connected to the coaxial cable. Another common connector used for coax is a B and C connector. This is a bayonet connector, that's what the B stands for, where you push it into the connector and twist it slightly to lock it in place. The NC in the BNC connector stands for Neil Conselman. This stands for Paul Neil from Bell Labs and Carl Conselman from Amphenol. They both were involved in creating this standard for a BNC connection. If you're bringing in a WAN connection or any other type of coax, it's very possible you might use a BNC connection to lock this in place. That is one of the benefits of using BNC, is that you're able to push the connector in and twist it, and it's not going to easily remove itself from that connection. You would need to untwist before removing that from the interface. Here's a close-up view of the BNC interfaces on a device. You can see where you would plug in the BNC connector, you twist that connector slightly, and it's locked in place onto that device.
These dishes just aren't getting clean.
Problem isn't your machine. It's likely your detergent. I recommend switching to Cascade Platinum Plus. These pods dissolve completely and have Dawn, breaking down 100% of tough stuck-on foods. Cascade Platinum Plus.
Networks can connect to each other in many different ways, and in this video we're going to look at a number of different network topologies and how those different network topologies can be deployed in an enterprise network. This can be very useful during the planning process where you're designing the network. It's also useful during the troubleshooting process so that you can tell how different networks are connected to other networks. This is also useful during the troubleshooting process so that you can visually see how one network might connect to and send data to another network. Let's start this conversation with one of the most popular network topologies in use. That would be a star network. Sometimes you may hear this referred to as a hub and spoke network. This is what we use in most large networks to connect devices together. There is a central device that is used as the central networking component, and then everyone on the network is all connecting to that same central device. A good example of a star network or a hub and spoke network is one that we have with switched Ethernet. Our Ethernet switch sits in the middle of the network, and all of the other devices connect to that same Ethernet switch. If each of these spokes around the network would like to communicate with each other, they all must communicate through this central hub. A mesh network design is if one location or device connects to another location or device over more than one network connection. This means that we could have one link communicating to another, and it might follow one path to get to that location, or it may follow an alternate path to be able to get to that location. One reason we design a network this way is so that if one link in the mesh was to fail, we can use one of the other links to complete that communication. We might also perform load balancing over these links where half of the data is sent over one connection and the other half of the data is sent over a different connection. Although we can certainly design mesh networks for local area networks, we often see them deployed in wide area networks so that we can maintain connectivity to a remote site regardless of what network connection might be available. If you were to look at a large enterprise network, you would notice there are a number of different architectures all being used in different parts of the network. And when we combine all of those together, we've created a hybrid network. One part of the network might be a star network, another part of the network may be point-to-point, and a third part of the network might be a mesh network. Once we combine all of these together, we've created a hybrid architecture. Many data centers take advantage of a spine and leaf architecture. This is where you would have individual switches at the top that are the spine of the network. There would be switches in the middle that are leaf networks, and then you would have different devices connect to the leaf. You'll notice that the spine network is connected to all of the leaves, and the leaves are connected to each of the spines. However, those leaf switches do not connect directly to each other, and the spine switches also do not connect directly to each other. This works very well for an architecture we use in many data centers known as top-of-rack switching. In top-of-rack switching, every rack has a leaf switch at the top of every physical rack. We would then connect all of the physical devices in that rack to the leaf switch that is at the top of that rack. This keeps your cabling very simple because all of your cabling is self-contained within that same rack. There is redundancy because you have this rack connected to multiple spines. This also increases the overall performance of the network because we're no more than one switch away from any other device in the data center. If your data center only has a handful of racks, this may be a relatively inexpensive way to connect all of these devices together. But when you have tens or hundreds or even thousands of racks in a data center, you would need a separate switch for every rack, and of course the cost of that will increase for each rack you have in the network. When looking around the network, you may find some wide area network connections that are point to point, and as the name implies, there is a single point connected to a single point. This was a very common design on older wide area networks where you would use something like a T1 or a T3 connection. We refer to those as point-to-point T1 or point-to-point T3. We might also use this design in local area networks. If you work on a campus, you can connect one building to another over two connections, and the connection between those two buildings would be a point-to-point connection.
I'm sensitive? Am I sensitive?
Your skin is just like your mama's. This is made with just 10 gentle ingredients. I've been using Ivory since I was a kid.
Wow, Ivory's old. A classic.
Ivory sensitive, just 10 gentle ingredients.
Many enterprise networks take advantage of a three-tiered architecture. This is a very common design, and you'll find many organizations use a three-tiered network design for their network. This starts with the core of the network, and this is where we might have the central point for all of our resources. So our servers, our applications, our databases, and other critical points are going to be contained within the core of the network. The second tier in a three-tiered architecture is the distribution layer. This distribution is the midpoint between the users and those core resources. This is usually a series of switches that provides redundancy and connectivity for those users to access those critical resources. And lastly, our users need somewhere to connect, and they often connect to an access layer. These are switches that are usually located very close to the user, usually on the same floor of a building, for example, and that access layer allows us to connect to the distribution, which then connects to the core of the network. This three-tiered architecture is very common to what we might see in a large city. The downtown area of the city is the core of the city, and all of the major resources for that city may be located in a very small geographical area in the center or core of that location. To be able to get to downtown, we need some type of distribution method. For example, we need some type of highway that might connect our homes to the downtown area. And our homes are usually connected to these larger highways through access roads. This allows us to use our local roads for all of our daily chores, but when we need to get to the core downtown, we may need to use those distribution highways. Here's what this three-tiered architecture looks like in a network diagram. The core of the network usually has core routers that are allowing us to connect to other resources in the core. The distribution layer in the middle is the one connecting the core to the access switches, and at the very bottom, the access layer is the one that all of the users are connected to. You'll notice there are multiple links between the access and the distribution, and occasionally you might even find multiple links between the distribution and the core. So if one component happens to fail, we can always use other parts of the network to complete that communication path. This is often combined with multiple buildings. So here on a single campus, we have two separate buildings. All the users are connected on each floor of the building to an access switch. Each access switch in the building is usually connected to one or more distribution switches, and those distribution switches are connected to the core of the network, which may be located in a central data center. If you're a smaller organization, there may not be a need for a much larger three-tiered architecture. Instead, you might want to use a collapsed core architecture. This is a two-tier architecture that combines the core and distribution layer into a single collapsed core. You can see the access layer is still exactly the same as it was before. This allows for a more simplified design and hopefully a much easier design when you're troubleshooting. This is also a lot less expensive to implement because you have less devices that you have to purchase and install onto the network. However, as you can tell by this diagram, there's not a lot of options for redundancy, so this may not be quite as resilient if you happen to lose any of these individual components. When you're describing the flow of traffic within a data center, it's important to know where the traffic originates and what the destination is for that traffic. One way to describe traffic flow is an east-west traffic flow. This means that the origination and destination for this data flow is all within the same data center. This also means that we probably have very good response times from one device to another since they're all located on the same local network. If the traffic flow is one that is leaving the data center or is coming into the data center from an external source, you would refer to that as north-south traffic. This would probably have a bit of a different security posture than something that is east-west traffic, because we really don't know where this traffic is going once it leaves the data center, and any inbound traffic could be coming from potentially anywhere. Here's a better view of this traffic type. If data is coming into the network from the internet, or we're sending information out to the internet, we refer to that as north-south traffic. Any traffic that is inside this local data center, for example, if we have a file server that is sending information to an image server, all of that traffic is staying within the data center and would be considered east-west traffic. In the next part of this course, we're going to talk a lot about IP subnetting. And a big part of subnetting is the ability to convert between decimal and binary. So I thought it would be useful in this video if we step through the fundamentals of performing binary calculations. Binary, of course, is a type of numbering that uses two different numbers, either a 0 or a 1. This means that there are only two possible options when doing mathematics in binary. The answer is either going to include a 0 or it's going to include a 1. Each one of these zeros or ones is referred to as a bit. And when we combine 8 of these bits together, we have a byte. Occasionally you will see a byte referred to as an octet to be sure that everyone understands that this is an 8-bit byte. In this video, we're going to perform a lot of calculations between binary and decimal. So what we need to create is a conversion chart to convert between binary and decimal. We'll create this chart by starting on the right side, and we'll simply put the number 1. Then we're going to double that number and put it to the left. So doubling 1 makes the number 2. If we double the number 2, we have the number 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, and so on. This is the conversion chart that we will use for almost all of our decimal to binary conversions. We created this chart with 8 individual places, but you can keep moving to the left with this chart and go past 128. We'll double it to 256. We'll double that to 512, and so on. You can keep continuing this process so that if you have a very large binary number, you can still perform the same type of conversion back to decimal. Let's now use this chart to answer this question. What is the binary 00000010 in decimal? First, let's write down this value in decimal. So it's 00000010. And of course, we want to know what the decimal equivalent is of that binary value. We'll then layer on top of this our conversion chart. So of course, we start on the right side with a 1, then 2, 4, 8, 16, 32, 64, and 128. Now we have everything we need to perform this binary calculation. In each of these places where we have a binary 0, we're going to bring that 0 down to the bottom line. In every place where we have a binary of 1, we're going to take the number just above that and bring it down onto the bottom line. We're then going to add all of these numbers together on the bottom line. So 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 2 plus 0 equals 2 in decimal. So the answer to this question of converting binary 00000010 is the same as 2 decimal. Let's do another one. What is the binary 10000010 in decimal? We will write down our binary value, and then we'll layer on top of that our conversion chart. Every place there is a 0, we're going to pull that down and put a 0. And every place there is a 1, we're going to pull down the number just above that 1. And you can see we only have 2 binary 1s in this number, and that's associated with the 2 and associated with the 128. So we'll bring down the 128, we'll bring down the 2, we add those together, and we've got 130 in decimal. So the binary value 10000010 is the same as 130 in decimal. And finally, let's do one more binary to decimal conversion. This binary value is 11111111. We'll bring down that binary value and we'll layer on top of that our conversion chart. And because each one of these spaces has a 1, we're going to bring down all of the numbers of our conversion. And if we were to count 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you would have the value of 255 decimal. So the conversion of 1111, 1111 in binary is the same as 255 in decimal. Now let's do the same conversion, but in reverse. Let's take a decimal number and convert it to binary. This question asks, what is the decimal 154 in binary? It's the same process. We're going to bring down our binary number, but of course we don't know what that binary number is yet, so we'll put some place marks here, and then we'll layer on top of this our conversion chart. Now we need to determine which one of these binary values will be a 0 and which one will be a 1 to make up 154 decimal. And there is only one combination of 0s and 1s in this chart that would equal that decimal value. We'll start on the right side where we have our 128 column, and we'll ask ourselves, is 128 less than or equal to 154? This is obviously less than 154, so we'll put a 1 in that column, and we'll bring down the 128. Now let's look at our next column of 64, and we'll combine that next column with the numbers that we've currently brought down previously. In this case, the number 128. So 128 plus 64 is 192. And we have to ask ourselves, is 192 less than or equal to 154? In this case, 192 is more than 154, so the answer is no, and we'll put a 0 in that column. Now we move to the next column, which is our 32. We'll add 32 plus anything that we brought down. That would be 128 plus 32, which equals 160. Is 160 less than or equal to 154? It is not, so we'll bring down a 0 in that column. We'll continue with this process by looking at the fourth column, which is 16. We'll add that to anything that we brought down. So 128 plus 16 is 144. Is 144 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the 16. Our next column is the 8, so we'll add 8 to anything that we've previously brought down. So 128 plus 16 plus 8 is 152. Is 152 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the number 8. Our next column is the number 4. We will add 4 to everything that we brought down into that bottom row. So that all adds up to 156. And is 156 less than or equal to 154? It is not, so we'll put a 0 in the 4 column. The next column is the number 2. We'll add the number 2 to everything we brought down so far. And if we add all of those up, it would be 154. Is 154 less than or equal to 154? It's obviously equal to 154, so we'll put a 1 in that column and bring down the number 2. And obviously we've hit the number 154, so we know that the number 1 on the last column will not be added to this final value. And if we add up everything in that last row, we see it does equal 154. And now all we have to do is look at the middle row to determine what the binary value of this is, and it would be 1001, 1010. If we look at 154 decimal, we know that that is exactly the same as 1001, 1010 in binary. With these 8 individual bits, we can convert any number between 0 and 255. So take any number you would like, put it into this particular format, and see if you can perform the conversion between binary and decimal. As you're increasing the number of bits in a binary value, you're increasing the total possible number of decimal results. For example, if you have 2 bits, there are only 4 possible outcomes: 0, 0, 0, 1, 1, 0, and 1, 1. And if you were to perform that conversion between binary and decimal, that's the same as 0, 1, 2, and 3. If you have 3 bits, then you can have 8 possible outcomes. If you use 4 individual bits, you have up to 16 different options. 5 bits moves you up to 32, 6 would be 64, 7 bits is 128 possible options, and if you were to increase the number of bits into 9 bits, 10 bits, 11 bits, and so on, you would also increase the total decimal number. You can see that this value is listed in this chart, and notice that I've also added the powers of 2 on top of this. This is effectively what we've been doing the whole time. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. So as we increase this powers of 2, we are also increasing the total decimal value. If you've done anything with networking, then you've probably run into an IP version 4 address. In this video, let's look at the different configuration options for IP version 4. The IP address is the unique identifier that every device on the network must have if it wants to communicate using that IP protocol. An IP address is a series of 4 numbers separated by a period. This would be something like 192.168.1.165. To be able to properly communicate on the network, every device needs to have its own unique IP address. The IP address is combined with another value referred to as the subnet mask. The subnet mask is also a 4-octet value, for example, 255.255.255.0. The subnet mask is used in conjunction with the IP address to determine what IP subnet this particular device is on. This isn't something that's usually transmitted across the network. It's instead used by your local device to make the determination of what devices are local on this IP subnet and what IP addresses may be outside of this local IP subnet. This becomes especially important when you need to send traffic outside of your local subnet, and you do that through the use of a default gateway. The default gateway is the IP address of a device that's on your local subnet that allows you to communicate outside of this subnet. For example, if we have an IP address of 192.168.1.165 and a subnet mask of 255.255.255.0, a common default gateway could be 192.168.1.1. This is an IP address that is configured and assigned to the router on your local subnet by your network administrator, and it must be an IP address that is on your local network. There are also other IP addresses you should be familiar with. One of these is a loopback address. This is a way to define your local device without having to know a specific IP address. Every device on the network has a loopback address, and it's a number that is between 127.0.0.1 through 127.255.255.254. So if you wanted to ping your local device, you could ping 127.0.0.1, and hopefully your local device would be able to respond to you. This is often used to confirm that your local IP stack is working properly, and it would then be able to communicate to other devices. We also have a range of IP addresses that we've set aside as reserved addresses. This is a range of IP addresses that should never be assigned to other devices. They're used for future use or for testing in the future. This range of reserved addresses is 240.0.0.1 through 254.255.255.254. Anything that is a Class E address is also a reserved address. We'll talk about classes of addresses in just a moment. And another address type you might run into is one that is not real. It's a virtual IP address, or a VIP. Virtual IP addresses are not associated with a physical Ethernet adapter. Instead, VIPs are addresses that you would assign to the internals of a device so that you can always reference that device using that virtual IP address. For example, you might assign a VIP to a virtual machine, or the VIP may be part of an internal address that you're associating with a particular router. The IP protocol and IP version 4 operate at OSI layer 3. So anytime you're working with an IP address, you're working at that network layer of the OSI model. Let's break apart an IP version 4 address and really see what it's made of. Let's take the address 192.168.1.131. We refer to these 4 values as octets. That's because they consist of 8 individual bits. And you can see the representation of that same IP address broken out into those 4 groups of 8 bits. Sometimes you'll see these 8 bits broken out and described as 1 byte, or sometimes 1 octet. So if you were to count up all of these bits, there are 32 total bits in an IP version 4 address, and that is the same as 4 bytes or 4 octets. Since each one of these individual groups inside of IP version 4 consist of 8 bits, the maximum value that you would ever have in decimal for any of these groups would be a maximum of 255. In the early days of networking, we had to manually configure the IP address, subnet mask, and default gateway all in a manual way. We had to visit that device, change the configuration file, and then that device would be able to communicate on the network. If anything changed with our network configuration or we needed to change the IP address of that device, we had to revisit the device and manually make those changes. Today, of course, we can plug in any of our devices and it automatically receives an IP address. The way that we are able to receive this automated IP addressing is through a protocol known as DHCP, or Dynamic Host Configuration Protocol. When we plug into a wired Ethernet network or a wireless network and we're automatically able to communicate out to the internet, it's because we've received all of our IP configuration settings via DHCP. But if you've ever connected to a network that does not have a DHCP server, you may notice that you're still assigned an automatic address. But this address is not quite as capable as a DHCP address. Instead, it's what we call a link local address because it can only communicate to other devices that are on your local subnet, and we cannot route that traffic outside of your local subnet. For example, if you're assigned a link local address, you can't communicate to the internet because that's outside of your local subnet. In IP version 4, this linked local address is assigned through a process known as Automatic Private IP Addressing, or APIPA. This range of IP addresses automatically assigned through APIPA is 169.254.0.1 through 169.254.255.254. There are also reserved sections of that range. The first and last 256 addresses are reserved and they're not assigned to end stations. So if you receive an APIPA address on your device, it's between 169.254.1.0 through 169.254.254.255. Just as DHCP works automatically to assign your address, APIPA also has an automated process to assign this address. It uses ARP to confirm that no one else on your local network has that linked local address. And if nothing responds to that address resolution protocol query, then it will assign a random number between that functional block. One of the challenges with IPv4 is that there are far more devices in the world than there are IP version 4 addresses. And in recent years, we've used up all of the available blocks of IP version 4 addresses. There are no other IP version 4 addresses that can be assigned in these blocks, so we need to find other ways to be able to communicate via IP version 4. One way that we've been able to extend the functionality of IP version 4 is to create an assignment of IP address ranges that can only be used on the inside of a network. We refer to these as a private IP address range, and anything that is a private IP address cannot be routed on the public internet. Fortunately, these are very large ranges, and we're able to use those ranges on the inside of our corporate networks. If you were to look at the IP address that's assigned to your device right now, it's likely that it's a private IP address. So if your device is currently using a private IP address, and you're watching this video on the internet, how are you able to communicate on the internet with an address that is not able to be routed across the internet? We're able to do that through a functionality called Network Address Translation. This allows us to convert a private IP address into a public IP address and use that public IP address to communicate on the public network. We'll learn more about network address translation as we go through this training course. If you want to learn more about private IP addresses, you may want to reference a Request for Comment, or RFC. RFC 1918 is the standard that defines these ranges of private IP addresses and how they can be used on our networks. If we were to look into the details of RFC 1918, you would see 3 different ranges have been set aside for private IP addressing. These 3 ranges are 10.0.0.0 through 10.255.255.255. And if you were to count up all of the possible addresses in that range, it would be over 16 million addresses. We often refer to this as a single Class A block of addresses, and we often write it as 10.0.0.0/8. If you were to write out the subnet mask of that /8 address, it's 255.0.0.0. This means the host size of this particular IP address range is 24 bits in length. Another range is 172.16.0.0 through 172.31.255.255. This gives us a total of just over 1 million addresses that we can assign in 16 contiguous Class B address ranges. If we were to write this out in CIDR block notation, it would be 172.16.0.0/12. The decimal subnet mask for a /12 network is 255.240.0.0, which means our host ID size is 20 bits in length. And the last range is 192.168.0.0 through 192.168.255.255. This allows us to assign over 65,000 addresses as part of 256 contiguous Class C address ranges. The CIDR block notation for this would be 192.168.0.0/16. That /16 subnet mask is the same as 255.255.0.0. Half of this address is assigned for hosts, so your host ID size is 16 bits in length. As we step through the next series of videos, you'll learn more about CIDR block notation, the different classes of IP addresses, and other details that you see associated with these private address ranges. When you start working with IP version 4, one of the things you'll hear about are classes of IP addresses. And in casual conversation, we might even refer to an address as a Class A address, a Class B address, or a Class C address. This was a method of describing an IP address as it related to its subnet mask. Anything that is a Class A address has 8 bits assigned for the network address and 24 bits that are associated with the host address. This means that the subnet mask for a Class A address would be 255.0.0.0. A Class B address default subnet mask is 255.255.0.0, and the default subnet mask for a Class C address is 255.255.255.0. This style of class-based subnetting is one that we have not used since 1993, but we still refer to some of these addresses in a very colloquial sense. And although you may hear someone refer to an address as a Class A address or a Class C address, in reality, we no longer use a class-based form of subnet masking. So if we don't use classes, why are we doing a video on class-based networking? That's because these classes do act as a starting point when we begin any type of subnetting on our networks. If you're going to subnet a network, it's important to know where to begin the subnetting process. This class-based system is the starting point. These Class A, Class B, and Class C addresses have an obvious demarcation between the network part of the address and the host part of the address. With Class A, that line is drawn after the first 8 bits. In a Class B address, that line is after the first 16 bits. And in a Class C address, that line is after the first 24 bits. Here's a table that defines the different subnet classes for Class A, Class B, Class C, Class D, and the reserved Class E. And you can see if you look on the right side, the default subnet masks are the ones we just saw, where Class A has a default mask of 255.0.0.0, Class B is 255.255.0.0, and Class C is 255.255.255.0. The way that you can look at an IP address and tell immediately what class that IP address is associated with is the very first octet of the address. If the decimal octet is between 0 and 127 as the first number of that IP address, it's a Class A address. If the first number of the IP address is between 128 and 191, that's a Class B address. And if the first number is between 192 and 223, that is a Class C address. If you were to look at that address in binary, if the first bit was 0, it's a Class A address. If the first bits are 10, it's a Class B address. And if the first 3 bits are 110, it's a Class C address. Class D addresses are used for multicast communication, and therefore they are not assigned to an individual line. But there is a range for Class D addresses, and that is between 224 and 239, or the first 4 bits of a Class D address are 1110. And there is a range of IP addresses that are not used for any purpose. This is a reserved range. We refer to this as the Class E range, between 240 and 255, or the first 4 bits of 1111. So based on that chart and those ranges of IP addresses, let's see what class a particular IP address would be part of. Let's start with the IP address of 17.22.90.7. To be able to determine the class, we need to look at the first octet, which in this case is the number 17. And if you refer back to that chart, the number 17 is in a Class A address. Let's do another one. IP address is 220.10.77.40. If we look at that first octet, it is 220, and 220 is in the C class. The next IP address is 165.245.0.1. We need to look at that first octet. In this case, that's 165, and 165 is in the range of a Class B address. Next on our list is 128.90.10.2. That first number is 128, which means that is also a Class B address. The IP address of 191.77.24.250 has the first octet as 191, and if we refer to our chart, 191 is in the range of a Class B address. And lastly, 192.1.12.5, we're looking at that first octet of 192, which falls in the range of a Class C address. When you start calculating an IP subnet, there are 4 different values that are very important to know. The first is the IP address associated with the network address. This is the one that defines all of the other devices on this particular subnet. To calculate a network address, you set all of the host bits of that address to 0 and then determine what the decimal representation of that might be. The second important piece of information you need for an IP subnet is the first usable host address on that subnet. This is always going to be one number higher than this previously defined network address. You also need to know the network broadcast address. This is the last IP address of this particular network address. To be able to calculate the network broadcast address, you would set all of your host bits to 1, which is the same as 255 decibels between the binary and host. And just as you need to know the first usable host address on the network, you also need to know the last usable host address. And to calculate that, you look at the network broadcast address, and it's one number fewer than the broadcast address. So let's calculate those 4 important subnet values. And let's start with the IP address of 10.74.222.11. If we look at our chart, we know that this starts with the number 10, therefore this must be a Class A address. And the default subnet mask for a Class A address is 255.0.0.0. Since we're using this Class A subnet mask, we know that everything that's on the left side of our bar, or this first octet, is going to be our network address, and everything on the right side will be associated with the host ID. So let's add those to our chart. We have a network column and a host column. Obviously, the 10 dot is going to be in the network column. That's what's on the left side of that bar. And then everything on the right side is going to be the host address.
Welcome back from lunch.
And to do that, we set all the host bits.
Good to see everybody.
This means that everything in that second column will be 0, and the network address, therefore, will be 10.0.0.0. The first host address is one more.
That was a quick lunch hour, I'll tell you that.
So our first host address would be 10.0.0.1.
Like, where did the time go?
To calculate the broadcast address for this subnet, we set all the host bits to 1, which means that the broadcast address is 10.255.255.255. And as you recall, the last usable address on this subnet, we need to subtract 1 from the broadcast address. So the last usable address on this network is 10.255.255.255.
Hope everybody had something good to eat.
You'll be able to determine the network address. You'll know if an IP address happens to be one of the usable addresses within that range, and you'll know what the last or broadcast address is for that entire network. Let's do another one. In this case, the IP address is 172.16.88.200. If we look at that first octet, we can see that that is a Class B address, which means the default subnet mask.
So it looks like those that are back are here.
255.0.0.
What I have on the screen right now, don't forget to clock in from lunch. What I have right now up on the screen is we're going to be talking about firewalls a little while. Those fear walls.
and everything.
Talk
from
about that for
websites
about 45
associated
minutes.
with the host address.
And I
Now
think
let's
you guys have a
perform those
great
exact
background
same
about
calculations.
firewalls.
We want to determine
Anyway,
what the network
so
address is.
a couple of questions for
Set
y'all.
all host bits to 0. This means
What does
that
a
the network
firewall do?
address for
In your own terms, in your own words, what does a firewall do for you? What's its primary function? Conjunction. What's your function? We know pretty much every computing device, desktop, laptop, has some sort of firewall, even now phones and tablets. But what is the purpose of a firewall? Charles says, create security for incoming and outgoing traffic. And you would be correct, sir. That's what you do. So you go in there and you will adjust what you need to and dictate what traffic's moving in and out and or where. Elaine says an intermediate security between your computer and that is correct too. That is correct too. So it's that layered security feature in there. Some firewalls, even nowadays, they will scan for, is it safe to say, viruses and malware? They even look for that too, right?
Mm-hmm.
Right. So that's like the Windows firewall you have built into your computer now. The cool thing about firewalls is they're just not, like you have a software-based one that's inside of your computer, but they come in different flavors. So sometimes you'll see like a piece of hardware, like it looks like a switch, but it's actually a firewall that's present on a physical network, not the cloud. So the hardware firewall, standalone appliance, you can integrate that within routers, you can. Or you can do a next generation firewall, new generation firewall, next generation, they're both the same. Those are the ones that can actually scan like your packets to see what's inside of the packets and scan the packets as they go by for signatures of malware or anything. If there's anything wonky going on with your system, it's able to look at that too. And kind of like isolate packets, or it's more reactionary. Let me give you an example. If Charles was to send me 15 years ago a virus through email or on the website, I probably wouldn't be able to catch that until I installed it, and then I noticed my computer's slowing down. File names are changing. Something's going on. Then I know Charles has sent me Charles gave you a virus. But Elaine comes along 20 years later, he's like, you know what, James, we're going to tighten up your security. We're going to put in an application or a new generation firewall that can not only look at traffic as it goes by, it looks for anomalies. So 25 years later, when Charles tries to send me something and Elaine put this device on my network, it catches it like, whoop, whoop. It's the sound of the police. Charles is sending it. It's the sound of
Yeah.
It notices something about this traffic and it says, no. Cuts Charles off. So that's the things that you can see. Now, the next one you see is the software base. It's inside your operating system, where you can download a third party, or you have cloud-based. They call it firewall. Everything is right? Firewall as a service, infrastructure as a service, software as a service, security as a service. Oh my God, SASE, right? Or got one better. We can do what we call the UTM, Unified Threat Management Device. This is like an all-in-one router that you'll see at home, right? In a Soho, but this one has everything in it. And when I say everything, there's an IDS, intrusion detection of device. There's an IPS. There's a firewall inside of there. Access control list. You can set policy. Like a unified threat management device can do a little bit of everything. And it's more reactionary, right? So it'll react on your behalf. We have two flavors of firewalls. The first one is what they call a stateless inspection packet filtering, right? Stateless and stateful. Let's tell the difference. Stateless firewall is basic. It is generic. It is what you usually have on your networks right now. Filters based on IP addresses, protocol, and port numbers. Can't you do that in your firewall right now? You can pretty much dictate what ports are open or closed, what IP addresses can talk to you, MAC addresses, right? Basic filtering. Access to network layers suitable for small networks. Stateful. Let me tell you about the difference about a stateful. A stateful firewall is unlike any you'll see. It's like the bouncer at the door at the club, but think about the stateful firewall looking and taking a snapshot of each individual that walks past him the whole night and monitoring their traffic and what they do on the inside of the club, even though he is still at the front door. So it's like he has 2 million eyes in the back of his head. Each packet that goes by, it remembers where you came from, what you're doing, and where you're going. So if something changes along the way, the stateful firewall can kick in with a couple of changes. So here we go. Inspects packets and tracks the state of active connections. So it remembers. Accesses at the session layer, okay, where the actual communication started from one node to another, host to another, endpoint to another. The point at which it regulates the traffic, that's where it's at. Ideal for corporate networks where it is critical to protect sensitive data. This is the one where companies start catching people on the inside of the company, giving away the secrets. Yes, indeedy. Eat my Wheaties. So as packets go by, it can remember that traffic, record that traffic. If it ever has to be used in court, they'll let you do what you're doing because you think you're getting away with it. Records everything. And it's reactionary. Which of the following network devices would be considered as a perimeter device and installed at the outermost part of the network? Perimeter device installed at the outermost point.
That's it.
The edge, as it will, closest to the exit.
So it would be an access point.
Think about if you were to drop an all-in-one that you have on at home. How many devices are inside that all-in-one? Just got done talking about it. Pretty tricky, huh? Is that question tricky for y'all? Don't know how to answer?
It's
okay.
It's kind of. Let's
think of it this way. When we look at it, a perimeter device, that's anything that's closest to the exit. So you may have a router. Now there's some devices that have firewalls in them, like a Lappy Tappy or a desktop. That's a power button, by the way. I'm so funny. So this is the router. The little signals. So think about it this way. If they're saying, which of the following network devices would be considered a perimeter and installed at the outermost part? I would have to say, it's not a wireless access point. It's not a bridge. It is not a switch. They disguise the firewall because on the inside of this puppy sits a firewall. It is the router. We cut it in half. Controls private, public, and the firewall sits on the inside, guarding the network, right? So you'll see these kind of, I don't like to say trick questions. They like to get you to think. You notice they didn't put router there, right? Isn't a router closest, or is the gateway? It is the edge device. Would you agree? Tough crowd today.
I was just writing. So
it's kind of tricky because the firewall is intermediate, but access point, right? You're right. So if you're ever faced with this type of question, when you look at the perimeter, you got to think what is closest to the exit. That's the wall of your house. Out here is the dub. That is an edge device. Okay?
Yeah.
Which allows traffic to lead to go to the World Wide Web. But on the inside, you know that there's no router listed here, but it says right that that's on the inside of it.
Yeah.
So you kind of gotta drill down to one level, be past the superficial, and kind of really know what each device will do.
Yeah.
Now, a wireless access point is just a point at which in a network, you can just gain access to the network. Is a wireless access point a edge device or is it an interior device?
It's more like an interior.
Yep.
Interior.
Interior, right?
Yeah, interior.
What about a bridge? So you have to know what each one of these, the function of it. What does a bridge do? Can y'all remember?
Yeah, a bridge. Bridge connects.
Charles, you know what?
Connects to.
We'll get back to that. But you did see bridge. BPDUs, remember? Bridge Protocol Data Units, Bridgeport, BP. So I can see why you're thinking like that. So it sends those data units around to communicate with each other, right? In STP.
2 points.
A bridge takes two lands, two separate lands, and connects them together as if they are one.
Mm-hmm.
That's like Charles and Martin. They both game, and they want to share games and files and all that. So Charles lives next to Martin, and they said, let's set up a bridge between your router and my router, and we can just talk to each other anytime we want directly. So now you have two household LANs acting as if they are one because they're letting traffic from both households go back and forth until Martin terminates his end or Charles terminates his end. Does that make sense? So that's a bridge, okay? What is the purpose of a layer 2 switch? Is that an edge device? Well, you can't have edge switches, so I kind of like led you into that one. There is a such thing as an edge switch. But primarily, it acts at what layer? To control what? What layer does it operate on of the OSI model?
Oh, I'd say layer 2. The OSI model is 2, if I remember correctly.
You're correct, Charles, 2. And it reads primarily in the address book of a switch. It reads what in order to route traffic. It reads what in order to determine where is it on the network, the internal network.
It reads a path. All right.
I know Charles is like, I'm brain farting, I can't remember. What's the two sub-layers of layer 2? It's the data link layer, MAC addresses. There you go, Martin. You got it. So it primarily works with frames on layer 2, on the switch, layer 2, in order to route using a MAC address. That's at layer 2. So that's how all that stuff's gonna move. Yep. So that's how we came to the conclusion that it has to be the firewall. Next question. What network device uses access control lists to prevent unauthorized access to the company's system? What say you?
Prevent content.
Which one of these?
filter. What network device? ACL. Uses ACL to prevent.
You already said that's the nickname for it.
Access into
ACLs, access control lists, aka
component systems.
You're correct, firewall. Yep. Anytime you see access control list, think firewall. Right? Because you can do that for programs, ports, content filtering, nicknames, words. Like I can go to a firewall and configure anything. Let's say Jesus is always looking at cars at work, right? And as a manager, he ain't getting nothing done. I'm always going past his desk, and he's always on the internet looking at vehicles, right? I wouldn't say anything to him. I just go to the IT and say, hey, for Jesus' IP address, can you block anything, any search for vehicles or cars? So they'll put all those words into the firewall, right? So when he goes to search, all of a sudden, a page won't come up. Cannot search this. Cannot search this. I'm forcing him to do some work now. He's not just sitting there at work looking at vehicles, right? Not to say you are Jesus. I'm just looking at his example. But that's how you can manage people. Okay, that's why a lot of organizations take away YouTube, Facebook, Instagram, all that stuff. They won't let you look at any of it. Okay, so that's a good way to monitor that. Okay, next we're looking at enterprise networking topologies and what comes along with that. Charles, you had a question about this. We were talking about this. Remember that? It's like a relation of the line staff relationship. Yep, for upper management. So with the tree topology, you have your core switch. These go vertically, and then horizontally, you'll have your additional switches that will help distribute the keep getting notices, restart your PC, and I'm saying no. So if I all right, can y'all hear me?
Yeah, it's
okay. Good. Yeah, see, it's the speaker thing. Hold on one second.
It's breaking up, yeah.
The heck is going on? My computer wants to restart. All right, can y'all hear me now? Good.
Yeah.
All right, sweet.
Good.
All right. But you know what happens if I disappear, I'll come back. Okay, so what we have here, that's the tree topology. All right. And attaching your computers as per ports. So with hybrid technologies, you can use when a basic right? Oh, check this out. I got something for you. You're going to get a crazy question that looks like this. Yeah, I could do that. Well, that's a crazy looking at. But what topology is that?
It looks like
star. You're correct. It's a wonky looking star. It looked like the star been up all night.
Yeah.
Hold on, I can draw that better. Look like the star has been up all night. You can do that a little bit better.
Yeah. That's what that is.
Oh my God, that looks better. Okay, great.
Yeah.
You get a wonky question on the Network Plus exam, and it says, it gives you this, and it says, what topology in here do you see that will determine everything being on one segment? Can you see it in there? The network topology that relies on various computers all being on one segment. I know, right? It's not mesh. You can see all the topologies in a star. It's a mesh in there? Correct, bus. Based off the selections they give you, bus is in there, and you'll have 1, 2, 3, 4 devices. You can see a bus topology in there.
Oh.
Crazy. A star is one of those things where it's like a hybrid situation, but you can kind of see all of the different topologies on the inside of it. Yeah, just a little trivia. So if you see that question on the exam, knock it out the ballpark. Word up. Hey. All right, next. Virtual LANs and subnets when they come off switches. Now, a virtual LAN and a LAN are the same thing. I repeat, they work the same way.
But
one is just more so, I'm talking about cloud. Everything was segmented or done in the cloud on a switch instead of physically. Do you understand what I'm saying?
Yeah.
So if I wanted to say LAN, if I set up a brand new building with 5 rooms and I got 5 different LANs and I physically put all the equipment in a rack, I just made a LAN. But if I set up everything in a cloud switch through Azure or AWS, set it up the same way like y'all do a Cisco packet tracer, right? Using the cloud, they usually call that virtual LAN. That's the only difference.
Yeah.
Okay, so they're the same thing. They're going to give you segmentation, flexibility, and simplified administration. Divide the network into small isolated segments. Doesn't require separate hardware. You can always add users and devices. You can group them by department or function or team, and then right here is simple. You can do network changes behind the scenes. You can change IP addresses and subnets of different machines. So if you need to isolate a machine, the user has no clue that you can change their IP address and put them on an isolated LAN just in case you want to monitor their traffic. They have no clue unless they did IP config/all and noticed something was going on. But they got to be tech savvy for that. All right. If you notice that a machine could potentially drop a virus to the rest of the network, if you see it in a scene, remember we learned about scene, security information and event management. I notice it might be a virus on there. I can ask Aaliyah and say, hey, can you change this computer, move it to an isolated LAN and sandbox it? She can go into there and configure it. Give it a static IP address or move it to a different LAN. The user wouldn't know it. They might get a little hiccup. They might get kicked off for a second, but it'll refresh the IP address and the computer's automatically moved, right? So that's how you can just move stuff behind the scenes and alter it. With VLAN IDs and membership, this is when we start getting into the weeds, y'all. Here we go. Remember I told you about that big giant PVQ that you might see? Yeah. VLAN IDs and membership. Now, you have to have a VLAN ID for each one. And you're like, James, I had no clue what you're talking about. What's a VLAN ID? Well, this is what we're looking at. Let me show you something. Who still has their 101 labs for Network Plus? Remember I dropped that book?
Yeah, I
It
think
has it in there.
I think I still have it too. Yeah, I
In
still
their
have
folder.
it.
Let me show you something. Fire Marshal Bill. In 101 labs, this is what you're seeing. That's why I wanted you to download Packet Tracer. Okay? Because in here, you can try out all this stuff and you're not breaking anything. For instance, we go down here, table of contents. We're gonna do a couple of these, so don't worry about it. Right here, VLANs, lab number 9, and it truly has 101 labs you could do. This is going to help you with hands-on too for the exam. And it uses Packet Tracer. First thing we need to look at, we already talked about subnetting. VLSM, variable length subnet mask. But when you want to set up VLANs, it teaches you how to do it. But let's talk about what's in the book. Here you're going to learn how to configure VLANs. You need a layer 3 device, which is your router, your all-in-one. All you do is open up your Packet Tracer tool and follow the directions. Okay? You're going to set up a VLAN for VLAN 10 and VLAN 20. Now let's talk naming conventions. Everything in IT, just like you do at your normal job or where you're at, and even in the military, everything has a naming convention. It is down to tech pubs, quality assurance, naming reports, right? Everything has a naming convention. So generally in IT, VLAN 10 means VLAN 1. VLAN 20 could mean VLAN 2. They like it to have 2 digits so it can stand out, okay? So in here, I'm guessing right here, it's giving me my starting address for VLAN 10, right? Now here's the 2 commonalities. This is where the naming convention comes in. Darn it, that's too fat. Y'all see it? Who sees that? First of all, what class address is this?
So 192.168. That's a class
Correct.
C.
Class C. So that means anything between 192.168.0.0 up to 192.168.255.255, I can name. So what they did here is said, okay, I want to create VLAN 1. They actually did 10, didn't they? So what they did in the 3rd octet, the first 2, see that? They just named it 10. That's the naming convention. So if you had to look at it and troubleshoot it, just by looking at it, you're like, oh, this is on VLAN 10. Let's go figure out this is the first address on VLAN 10, 0 for the host. They did the same thing over here for VLAN 20. They just started in the naming convention of 20. There's the host. All right. That's what you will see on the exam. So that's how you would identify it. Charles, if I wanted to name a VLAN, let's say I had VLAN 10, 20, 30, what's the next one would you use after 40 for naming conventions for a company? You're correct, 50. I was trying to trip you up like, what do you mean, James? But you actually figured that one out. You got it.
Yeah.
Egg on my face. But the cool thing about this is
it's a sequence.
that means now Charles has a whole range of addresses that just belong to that VLAN. Everything that starts from 10.0 all the way up to 255. You get what I'm saying? So he has all of those freaking addresses he can use for that VLAN. Yep, it's the sequence. Remember, these are the interfaces that the VLANs that are connected to the router. These are the ports. All of them are connected to the router. Anytime you see these arrows go like that, that's a router. Okay? So that's the cool thing about that. What's going to happen is, when you go through, they're going to want you to pull a 2960 Cisco switch off the shelf. You're going to use straight through cables Why are we, see, that's why I like going through these labs, and we could do one too. Why do we like to use a straight through cable? Connect 4 hosts using a straight through cable.
Straight through cable. It's.
You got to know the difference, because on the exam they're going to present to you 4 cables, and you got to figure out what's wrong and why can't these devices talk. It's a troubleshooting PBQ.
Straight through cable.
Okay. Like-minded devices. Good guess, Michael. Like-minded devices are T568B crossover. So you answered the other half of the question I was going to get to. Like-minded devices, one end will be A, the other end will be B. They cross over. And T568 alpha same. Is that right? So T568B connects what? Similar or dissimilar? Michael just said it. T568B connects similar devices. That's why you do a B. I tried to trip you up. You fell for the bait. T56A connects dissimilar devices. Not the same. Router switch. PC switch. Right? You fell for the bait. So that's why up here it says it's telling you to use straight through cable, which is an A. An A is a straight through cable. It is the same pin layout on each terminating end. Okay? All right. All right. So when you do that, so now you got the proper cable. Okay? You're connecting dissimilar devices, so it's a straight through. Okay? You need to allocate IP addresses for VLAN 10 and VLAN 20, and they're saying they want you to start with these. So when you are actually configuring, you would have to go to the interface, put static, and configure the port or interface address, and there's your subnet for a Class C. These are the actual commands that will need to be put in the command line interface, okay, to configure. Now, I'm going to tell you, there's going to be a PBQ that's going to be presented to you, possibly. And they said, Jesus and Brian has been working on installing a switch all night. They're tired. They had 15 cups of coffee and 6 Red Bulls. Still didn't keep them up. Brian said, let's get this done and get out of here. So they configured each one. One port's not working. It's 48 ports. One is not working. Then they have to go back through the instructions or the configuration and figure out what happened. First of all, who was the last people to touch that thing? B and Jesus, right? So it's not a manufacturer issue. Eliminate that one, right? It's not a corrupt file. Eliminate that. They had to configure everything through the command line interface. But when you bring it up, the configuration, it couldn't save because they missed a step. They have to go back and redo that one port. They figured out they did all that, but once they did that, they noticed that it worked. Then they checked the VLANs to show VLAN brief right there, and then they could see the configurations of the VLANs. VLAN 20, VLAN 10 active. They try to ping, it now works. And then they can go in and change the name of the VLANs to what they want them to be. Okay? That's how you set up a VLAN. You have to go inside of the switch and do that. Now we have 30 minutes or so. Who would like to jump into Packet Tracer and do lab number 9?
The packet tracer?
No volunteers. We could try it out. Oh, Michael, we can get the baby to do it. The next IT generation. She'll learn it faster than I ever did. But when you have time, we'll break out the lab, do lab number 9. We'll probably do it toward the end of the day, and you can see how easy it is to actually connect it. This is intimidating. This can be. It's a lot of commands, but notice you're always going to start out. What's the first command that you put in? Config T. Configuration terminal. It tells you. Now, this is the actual command that will come up in the CLI. This is not a note. It is a note, but it will come up. It says enter configuration commands one line at a time. End with Control Z when you're done with everything. Control Z is down here. After end, you hit Control Z. It'll bring you back to this. Okay? You want VLAN 10, you want to put it on interface F0/1. You have to put it in, this is mandatory, switch port mode access. Switch port mode access. Then you have to type switch port mode access VLAN 10. Then you move to F0/2 and over and over and over and go down. They configured all 4 ports on that router or switch. Then show the VLAN brief. It comes up and tells you everything that is configured. All right. That is something that you would need to know when you scan a document in your PVQ to know what's connected properly, or to know what you are looking at in order to find out where the issue is for a VLAN that is not connecting to a switch port. All right. The next one that we have here. So write that one down. There's something to do. Lab number 9. There's another one we need to do. Where is it at? Not jumbo frames, which you can do. So it tells you how to turn on jumbo frames on the switch. Trunking. Oh, since we're here, this is good to do. So right here, it talks about switching loops, the ARP table, static IP addresses. But here's how to configure ripping and RIP, enhanced interior gateway routing protocol, open shortest path first. It tells you go to Packet Tracer. Through this topology, you're going to drag 2 routers, connect the routers using a crossover cable. Right? Similar, same, it's a crossover cable. So you use B2568B. And then you have to go into, see how this looks? See, doesn't this look familiar like it looks inside of a switch? Command line interface will come up, but it says router instead of saying switch. Configure terminal, host name on that interface, or excuse me, that router, tells you once you're done, hit Control Z, and then you start configuring the port. All right? For RIP. Excuse me, for OSPF, I'm sorry. Then you configure OSPF once you have it configured. This tells the router exactly which subnet to use when you advertise. As a quick cheat, you can take whatever subnet value in each octet and take it away, so it's 255. It's just telling you what to give you for when you're doing CIDR, 240 and 252. And you're saying, here we go. Remember when I said area 0? Y'all remember that? And backbone? That's when you start put it in here. When you're using these routing protocols, this is part of your backbone system, so you have to know what you're inputting. Interface IP address with the subnet, area 0. If it's configured properly, this is what you'll see. OSPF, yeah. You can see OSPF has 110 as an administrative distance. And you can show the route. And you can show IP protocols, and it'll show you for 10, there's your OSPF. All right? As I said before, to get through this lesson and understand everything for the exam the first time and the higher probability of passing the exam, you have to at least do these once. I'm not saying you have to do all of them, but at least get into a couple of them to see how it looks. Even if you don't get around to doing all of them, at least do 2 or 3 so you can recognize these terminal commands or these commands on the exam if presented, so you know what you're looking at. If you sit back in class and you're not doing this type of stuff hands-on for the Network Plus exam, it's going to be hard. I'm telling you. I wish it was an easier way to do it, but it's not. I had to learn that myself, so I'm preaching to the choir. Because when I think I told somebody, I think I told Michael this. I went in there thinking, oh, I know networking. Bombed it.
Oh.
There's a difference between learning from somebody else thinking you know how to do it and actually doing the stuff beforehand and then going in there. Because when you learn from somebody else, they leave a lot of stuff out. They leave a lot of stuff out. Kevin says, I'm having trouble finding this PDF. Yes, I can resend it to you, Kevin. Not a problem. All right. So please jump in there. It's a lot of good stuff in there. All right, let's get into last couple of slides and we'll be done with today. All right, so when VLANs, all right, let's go. Current slide, yep. Is it happening? Here we go. What you'll have is what they call trunking in the IEEE. Trunking are physical links, right, into one logical link. When you have a lot of data coming in, and you have, let's say, a core switch, this is the first floor and the second floor. They have their own switch on that floor. There's another switch here. This might go to the MDF closet or the IDF closet. And it has a switch to control the access between the 2 floors. What you're gonna see is what they call this trunk line. There's a special port on here that you can set up on the switch, and it is the information highway. It's saying, I don't need you to go through a CAN table. I don't need you to do it. Just move the information through my trusted devices. That is a trunk port. You're basically telling the network, I don't have time for data to slow down. I need it to keep moving and at a high pace and at a high rate. So we're going to use a trunk port to open up an interior superhighway to move through all the devices, all the switches that I own to move this data. Okay? Oh, thanks, Jesus. Appreciate it. So that's what you see with a trunk port. With VLAN routing, you'll have your router. These are the VLANs that you are controlling. VLAN 16, 32, and 48. These are sub-interfaces. They'll be configured to the physical interfaces. And then you'll have this switch that will control all of these VLANs down here. So that's what's happening. You're having the switch control all of these different VLANs. Let's get down here. Well, actually, let me back that up. So here's a test question for you. When you're configuring a switch, where do you need to go to start putting in command lines to configure? Where do you go on the inside of it? First of all, how do you get to it? So if you have a switch and you're looking at it, what do you need to connect to that switch in order to start configuring it? Let's start there so we can see the bigger picture. Is that essentially saying screw all of your protocols, send me everything? Yes, I'll handle it. Yes. It'll still have protocols, but it's saying we don't have time to slow down. These are all trusted devices. Move it, move it. We got to move it. Okay? So if I have a brand new switch out of the box, what is it that you have to have? Aaliyah says a T56A cable. Try one more type of cable. They have to go in a specific port. So you have to have a laptop. One end plugs in through the laptop. The other end plugs into a specific port in the router, switch. It is the configuration port, better known as the console port. So you need a console cable to plug into the console port, and the other end will go into your lappy-tappy, your laptop. Okay? Now, to get into the switch, you need a terminal console. You just can't get in that puppy like the router by putting in an IP address in the browser. You need a terminal. Okay? Because you're using SSH. So somebody please Google what terminals can I download to use SSH with a switch. There's a couple of them out there. Download a terminal for switch configuration. See what he tells you. Download a terminal for switch configuration. This is the stuff that they don't kind of there you go. Putty's one. I see Martin going. Yeah, Windows has an SSH client. It does, yes. There's one more that's free. Open source. There it is, Tabby. Yep. Quick on the draw, look at that. So now, once you download it, you have to go into, just like East Charmer, she was telling you, Now you connect that, you have your terminal downloaded, it comes up. She said you have to right click on device manager and look for something in order to know which communication port it should go to when you configure PuTTY or Tabby or Bitwise or SSH client for Windows. You have to tell it a specific port to communicate with. Where do you go to pick one? And it's in device manager and you scroll down. I know, right? Kevin says, Nick, it has to communicate. Jesus, I think he just figured it out. What port? Oh my God, Kevin, thank you. Comport. I gave you so many hints, right? It's usually not going to be comport 1 or 2. It's like 3. Right? Aaliyah did it too. Okay, thank you. So you pick out what comport. Now you can go to PuTTY. Pick out the communication port with the serial. Okay, boom, boom, boom. And then it's trying to get into the switch. Okay? So you want to connect the cables, connect the port you want to communicate with, hit connect, and then now you're into the OS of the switch, right? Then you get the CLI, the command line interface comes up. Boom. What dictates the COM port? When I hook up my CNC, it always defaults to COM3 regardless of what system I use to hook it up. Now, that's a good question. So it'll default, but what if it's, I've tried to configure switches before and it'll never default to COM3. It'll it'll go to a serial port. And I'm like, I'm not trying to connect to a serial port. I want a communications port. So you have 2 buttons to hit, serial or COM. So you have to click COM to see which one is available. But good one there. Uh-oh, Kevin's still typing. He's got another question. And he's a typing. And he's sweating. Okay, so would that be a software protocol? It is also very generic Asian market parts, so that it'd be, I guess so. I mean, I would think so. That is configured with that protocol to go into the software. Like they probably coded it already. That makes sense. I'd have to double check that because I'm not 100% sure. But it sounds to me that it was already pre-configured to do that when it connects. Yeah. But we could double check that. So then your command line interface will come up in the switch, and then you'll start hitting
config.
How do you get into the terminal? What's the first command you'll hit? Either a router or switch, because they both say either. If it's a router, it says pound router or pound switch. But you put this in the beginning to kick everything off. If you're trying to configure something. Configure.
Yeah. Configure port.
Config T, yes.
Yeah, I can.
Because you're in the terminal, configuration terminal. Right? And then you start going from there, depending on what you need. If you need to enable a port, you'll enable port number. If you need to start to set up VLANs, VLAN, whatever, right? It all depends on what you're trying to do. You put in, when you're done configuring everything, depending on what the labs tell you to do. Hit Control Z, saves it. You're back to the pound sign, whatever it is. Show interface, show routing, whatever you need to make sure it's there. It's been configured correctly. Okay. So that's what you're going to do there. I just like to do a mental walkthrough, like the Thunderbirds. They do chair flying. And the Blue Angels, they do chair flying. Y'all seen that before?
Well,
Y'all need to watch the Blue Angels
formation
story on Amazon or watch the Thunderbirds on Netflix. They both do the same thing. It's called chair flying. They have all pilots in a room. The lead pilot puts their head down. They visually talk through every maneuver, and each pilot shouts out what they're about to do in their mind, and they do it in unison, like 3 hours a day.
No formation.
Yeah. So by us, yes, with the formation flying, it keeps down on accidents because they're verbally saying what they're about to do. And they can correct themselves right then and there. You weren't supposed to do that right then and there. And they start all over again. Can you imagine? Chair flying. So this is what we're doing. We're chair networking. Dad joke. Oh my God. We're chair networking.
Yeah.
Yep, 3 months to plan it. You're right. It took them 3 months to plan the Super Bowl flyover, and that flyover was all of 15 seconds. Maybe. I wonder if it's just for show, or do they know how to dog fight? I'm sure they do, because you know what? To get to the Thunderbirds, first of all, you put in your package, then you get interviewed, then you get selected. Right? They all come from various backgrounds. Like I was looking at one of the Thunderbirds. He was one of the aces of like the ground war and like the last one we had, the conflict we just had with the war in Afghanistan. Okay. Then he went to teach somewhere else. Then he went back to a unit, became the commander, and then he got picked up for Thunderbirds. So he had a resume of what he could do. So, yeah, very strict regulations. But that's why we walk through this stuff, to hear it, so we can acknowledge it. It's audible learning, and then we can visualize it. So if we see it on the exam, we can be like, oh, we talked about that. I heard that somewhere before. So we're chair networking. All right. And then when we're talking about routing tables, something's going on with routing. You always want to check your routing tables, verify connectivity, review the table entries, make sure your subnet masks are good, examine static and dynamic routes, and use traceroute to find out where your data's going. Default and routing loop issues, verify your host configuration in the NIC card, ping, make sure you can get past the gateway. Ping is not just to check the gateway. Pinging past the gateway, meaning you're pinging the 8s. The 8s live outside your gateway. You're making sure you can walk out the door. That's the only reason ping exists, pretty much. All right? Review your connections, check the router settings, and identify any loops. If you're having problems with VLANs, check your physical connectivity. Ping the loopback addresses, ping the gateway, ping the remote host or server to make sure. You should always ping VLAN, leaving one to another in order to make sure it could leave the VLAN. It has permission to leave the VLAN. Okay? Now, what you'll see too is what's important. I know this is a lot coming at you. My goodness. VLAN tagging is very important. So not only do you have to know how to do link aggregation, there's 3 things you'll see for a PBQ. Link aggregation control protocol, trunking, and VLAN tagging. All of those need to be done in a PBQ, the one I told you. If you get it, it's almost 10 minutes long. Yeah. You have to, just for that one, if you see it, you in your mind, you automatically better know, I need to leave myself for this one at least 8 minutes at the end. Skip past it, get through the questions. Circle back. Okay? You'll have some trash like, you know what, we're on break. I'll talk to you when I get back from break. Take 10. Welcome back, everybody. All right. So, this is before we jump into some breakout rooms and get some studying done for the remainder of the day. This is what you'll see as an example. Here's a little diagram that was shared with me. And it gives you an example of what you might see on the exam. This is not exactly what you'll see, but this is possibly what you're going to run into as a huge diagram of the 10 minutes, the 10-minute diagram that you'll see. Type of trash you'll see is a simulation, maybe. And it says between switch 1 and 3, you need to verify or reconfigure settings. Each device accesses only its correct associated network and disable unused ports. You might see that. Sometimes the PBQ may tell you, just for an example, this is strictly an example. It's not exactly what you're going to see on the exam. I repeat. But some areas will be clickable and some are not clickable. So if you see anything here, you don't need to worry about those. But this is a clear definition of what they call, here's the core switch, and this is a trunk port that has to be opened to make sure it's giving connectivity. From the core switch to switch 1. Port 1 to 1, 2 to 2. Okay? Link aggregation control protocol, trunking. Then you have on this switch number 1, they have servers 1 and 2. As you distribute your signal throughout your network, this particular network has 3 switches, 4 switches in total. The core switch brings in the signal. Signal is redistributed to switch number 1. On that switch, they decided to put 2 servers. Then they said, okay, we need another switch to distribute traffic. So they said 1, 2, 3, 4, 5. We'll use port 5 on switch 1 to port 1 on switch 2. And we'll have LACP set up. Then they said this port 2 on switch 2, we'll use that port, open up a highway. And then they did the same thing down here for ports 1, 2, 3, 4, 5, 6, 7, and 8. 7 and 8 go to ports 1 and 2 on switch 3. So now you have all switches connected somehow, some way. So traffic can move from these different switches up through the core switch and out through the network. Is the core switch layer 3? Yes. So core switch to switch 1 is north-south. Well, it's not really, yes it is. I have to say it is, yeah. So you're looking at vertical movement. The other switches, the distribution switches, and I'm glad you brought that up. Glad you brought that up, Kevin. Core switch to the first switch, going down, core switch, yes, it's vertical. It's moving down to the distribution switches, okay? Core brings in the signal, pipeline, brings it to the first switch, boom. Now we're horizontal. It's bringing information across other 2 switches in the network to distribute, all right? These could be floors. This could be on the same floor. These could be rooms. You get what I'm saying? Could be anything. On switch number 2, they have a PC printer, access point 1 and access point 2, and they have mobile users. Then on switch 3, they have a VoIP phone. So they have a phone connected to a PC, a laptop on that port, a printer on that port, and a printer and a server on that port. The one thing about this is it tells you all these VLANs, allegedly, this is just an example of what you might see. It tells you printers are 60, VLAN 9 are servers, VLAN 120 are wired users, 150 is wide area network LAN, and 220 is voice. I'm saying this for a reason. I have a quick question. Look at the diagram. If switch number 3 needed to make a phone call, port 4, which VLANs do I need to tag? For it to go through. Tagging a VLAN is like saying you have permission to go play in somebody else's backyard until I revoke that permission. So I have to tag you. If Kevin wanted to come on my street and play, I have to VLAN tag him. Okay? So just by looking at and just take a guess. I want to see where your minds are at. That's why we're doing it now. Okay? What VLANs would I have to tag if I want to make a VoIP call, a voice over internet? On the network. So traffic specifically goes to through that VLAN server. Can I make the picture bigger? Ooh, I don't know. Let's see. I don't think so. How about this? Let me see here. I might have to do a snippet of it, maybe. No, that's not either. Darn it. All right, I'll get you a picture of it. So let me walk through it. If I need that port to talk to somebody, I will have to click on that port, and then this is what comes up. So it's saying like here, on switch port 3, port number 8, 1, 2, 3, 4, 5, 6, 7, 8, that's a server. In here, we need to make sure that it's full duplex and gigabit speed, possibly. You have to make sure that the port is turned on because there's something sitting on that port in order for it to work. And if it's not one of these ports, you see this? These trunking ports? If it's not one of these ports, LACP is turned off. Link Aggregation Control Protocol. Then it says, okay, this is a server. What VLANs do I need to tag? Well, I know for servers, it says over here, if people wanted to access this server, I have to tag VLAN 90. So I have to tag on here. I have to add a VLAN 90. Tagging. All right, so I turn on tag, VLAN 90. If I want other users to use it, other wired users, it says up here, it's 120. Do I have other wired users on this network?
Yeah.
In the whole company on 3 switches? You're correct. You can't even see it, can you?
No, I can't see the rest of the picture the same.
You know what? And that was me just forward thinking, so I apologize on that. Mike's right. There you go, Mike. Sorry about that. So here you'll see other wired users. 120. These users on this switch might have to go through the link aggregation control protocol to have permission to play in somebody else's backyard to access info. So now you have to tag VLAN 120. So already on switch port number 8, we tag VLAN 90 in the drop-down box. And we tag VLAN 120 so other wired users can access whatever's on this server. Right? And we're saying, okay, what else do we need? Probably nothing, because it's just a server. If you have a user, see these users up here? Mike, can you see that? You're going to be the one to let me know if you can see it or not. So if you see this up here, this user needs to print something. But there's also a printer right here on their VLAN. If you see this, do not tag printer on a local VLAN because you live in the same house with that printer. How would you correlate 120 to the diagram? Oh, it'll tell you. It's over here. They'll tell you all your VLANs that you could use to tag if you need to. If there's a printer already on the same switch with something, you do not need to tag. It lives there with the same device that wants to print to it.
Okay.
So for that port, you don't need to tag the printer VLAN. It lives with it. Now, if I want to access this printer, I have to tag this port with VLAN tagging, and I have to give it access to 60, no matter what. If I'm printing to a local printer, it will disregard the tag and print. If I need to use another printer in the organization, I have to have it tagged so it could leave, my request can leave and make its way to another available printer on the network. You've seen this when you've been at work in the military, where your printer in your office don't work, but then you're able to print to another office.
Yeah.
It's because they had VLAN tagging turned on.
Oh.
Okay? Did you ever notice that the higher-ups in your command had a designated printer and nobody could print to that printer but them?
Yeah.
VLAN tagging. You weren't invited to the party. Okay?
Yeah.
Meaning all of their computers in the higher-ups office were on one switch. So it defaulted to printing to their printer. Does that make sense?
Yeah.
All right. So quick quiz. If I need a high-speed network open between switches, what do I need to enable?
What? Port?
You're correct. You enable a port, you enable LACP. If I have a resource I need to access on other switches, I'm leaving my neighborhood. I'm leaving my port on my switch to go play in Kevin's neighborhood. What do I need to tag? See, I just gave you the answer. There you go, VLAN tagging for that port.
Mm-hmm.
If you don't understand this, this would look crazy to you on the exam. You'll be all over the place. My recommendation to you is do one thing at a time. Go down the list, read the directions. Don't try to do 3-4 things at one time. Do one thing. We need LACP turned on. Okay, go down. LACP. Everything they said LACP. Let me handle all the LACP stuff first.
Mm-hmm.
Enable port such as a... Okay. Let me enable all these ports. Boom, 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 boom. Okay, now I need to do VLAN tagging. They want this VLAN to be able to talk to this VLAN. Now let me finish off with my tagging. Boom, 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 boom. Done. Okay? In the example, if you ever see anything, make sure everything is full duplex and at 1 gigabit. Full duplex, 1,000. That's what I would do in an example like this. Not showing you how to do the whole thing. I'm just telling you some basic things you just need to look at.
Yeah.
Even if it's hardware sitting in front of you. That's all. That's all I'm saying. Y'all picking up what I'm putting down? Good to go. You know what, Jesus? They are, because you know what? It's a lot to look at. It's overwhelming. It's overwhelming. You know what I'm saying? So if you don't pick it apart and just say, let me just handle just let me follow the directions. And remember I told you, always follow the yellow brick road to what you need to do and disregard everything else. All you see is that yellow brick road they want you to do. All right? All right. Oh, what's the time? Is the time restraint too? Yes, you got to do all of this. Yeah, you're correct, Elaine. Yeah. The time too just goes away from you.
Yeah.
So just get a good idea of what you're looking at. Know in your mind, if you see this, that's at least 8 minutes. Each other one, you need at least 3 minutes, 3 to 4 minutes for each one. So 8, 3 more PBQs, 9 to 11, 12, 13, need at least 15 minutes at the end, at least. All right. So that's how you want to tackle that. 12:01, I had lots of time at the end. 12:02, I was squeaking in by my last. Yeah, it all goes back to how comfortable you feel with your knowledge base too. Now, it can work both ways. You could have a lot of time left thinking, I aced it, and then you get a fail on the screen. Or you could squeak it to the end, and you think you failed it, but you actually passed it. It's like, what just happened? What just happened here? Right?
Yeah.
So whatever the result is, just give it your best shot and don't leave anything empty. Do not do that, because that one thing you leave empty might be that 1 point you need to land on the passing score. Guess if you got to, and I'm saying it, guess. Just throw stuff everywhere if you don't know what it's supposed to do. Put something there. You never know. Okay, Kevin says, I skipped the peepers in the beginning and hit them up at the end. They confuse me so much. I count them as a loss. From the start, but go back. Okay, good. You go back and hit them. Good. Charles, miss 100% of the shots. You don't. Yes, you're correct. Yep. So just flat out guess. All right, that was a long lesson today. Any questions for me? Thanks for getting that, Wayne Gretzky. Yeah, my man, the OG hot. So, this is what we got. I'm gonna open up, Leah, I'm gonna open up some breakout rooms. One will be for A+, pretty much. The other one will be for net. Leah will be running the A+ room. I'll dive into the net plus room. Nobody comes into that room. I'll go into the A+ room and crash that room. But feel free to move about. Yeah. Sounds good? Yeah. All right. It's not mandatory now. This is if you want to do it. But this is what we'll be sitting at. We'll give it maybe 45 minutes. You know what? Should we do this at the top of the hour? I think the top of the hour would be good, because then you get a fresh 45 minutes. Okay, I'll open them up at 4. Do what you need to do now, but when you come back from break, those rooms will be open, so you can just pop in, and we'll be in there. All right, good stuff.
Oh, you said what is my channel about? Oh. So basic chat, basic talk from ranging from financial, dating and relationship, even gaming, console gaming. So the basic things that people can engage in order to better themselves from the individual perspective. That's what I like to do on my channel, particularly. So if everyone individually take the responsibility and the self accountability to make themselves better, so eventually that will accumulate to the collective of people becoming better. So I like to focus more on the individual aspect of things, because particularly everyone is really busy throughout the day attending to their distractions or their responsibilities. So no one really had the time to focus back on yourself in order to really attend to all the distraction that they've been shown or programmed with, to say the least. So I like to focus on self pretty much. My pleasure. I think it's a good thing when each individual can at least come back to really doing a self-evaluation, because not everybody have the time to do that. Everyone is distracted, whether it's school or work. So if everyone can take the time out to, in small increments, it helps, and then that accumulates in the collective of the entire human population eventually. So each person becoming individually better, and I think that helps.
interface to use when we're assigning these addresses to all of those many devices on the internet. Another way to visualize this would be to say that every grain of sand on Earth could have 45 quintillion unique IP version 6 addresses. You can see that this larger address space with IP version 6 resolves that IP address constraint that we have with IP version 4. There are a number of differences between an IP version 4 address and an IP version 6 address. This is an IP version 6 address, FE80:5D18:652:6FFD:8F52. You can see that is a very different style of addressing than IP version 4, where we were only dealing with decimal numbers and periods. In IP version 6, we are using hexadecimal values, and we're separating those with a colon. If we were to write out that entire address into its entire 128-bit form, you can see that it is completely listed here, and that is a much larger address than we deal with IP version 4. If you wanted to view this in a binary form, you can see that we have the representation of that same address listed in binary. You can see here that each section of an IP version 6 address that we separate with colons is 16 bits in length. You can see the 16 ones and zeros listed in each one of those sections. This also means that each section is 2 bytes in length. You may also see it represented as 2 octets in length. So in total, the IP version 6 address is a total of 128 bits, or 16 bytes in total. You might see an IP version 6 address written out with all 128 bits being shown on the screen. But you might also see these addresses listed in a compressed form, which makes it much easier to be able to read. When we're using this compressed form of an IPv6 address, there are a number of rules to keep in mind. One of those rules, if there are groups of zeros that are together, we can abbreviate that entire group by simply replacing those zeros with a double colon. We can only do this one time in an address, but usually that's all we need to make this address much easier to read. We also can remove leading zeros from each group within the IP version 6 address. Let's take an IPv6 address and perform this compression to see what that would look like. The IPv6 address we'll work with is 2600::1111:1111.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Solo. The studio
:0001:000, and you can see the zeros go all the way through to the end to the number 1. Our first rule here is that we can remove any of these leading zeros that might be in all of these groups. This means that our IPv6 address with those zeros removed would be 2600::DDDD:1111, and then each of those leading zeros in all of the remaining groups would be removed. You'll also notice that there are 3 individual groups here that are simply zeros. And one way that we can simplify the writing of this IP address is to abbreviate 2 or more of those groups together with double colons. So all 3 of those zeros would be removed, and we would replace them with one series of double colons. This means that we would have a very simplified form of this address. Instead of having all 128 bits of that address shown on the screen, the address is now simply written as 2600::DDDD:1111:1 double colon and 1. Let's look at another IPv6 address and perform the same compression. This IPv6 address is 2601:04C3:4002:BE00, 3 groups of zeros, and it ends with 0066. Our first step would be to remove the leading zeros in all of this. We have our second group has 1 0 in front of it, and there are a number of groups at the end that have leading zeros that we can simply get rid of. You'll notice in this example that there are 3 different groups of zeros that are combined together, so we can remove all 3 of those zeros and replace it with a double colon. This greatly simplifies this much longer address into 2601:4002:BE00::66. As you can see, the IP version 6 addresses are very different than the IPv4 addresses that we're used to seeing. And because of this, IP version 6 and IP version 4 cannot directly communicate with each other. Therefore, we need some method to be able to have these older legacy systems that only understand IP version 4 be able to communicate on our more modern IP version 6 networks. This creates some communication challenges when trying to combine IP version 4 and IP version 6, but fortunately there are a number of different ways to bridge this gap. One of these methods would be to tunnel the traffic. We would either tunnel IP version 4 within IP version 6, or tunnel IP version 6 within IP version 4. This would give us a way to communicate even across networks that were very different than the protocol that we were using. Another way to bridge this gap would be to use a dual stack configuration where the system that you're using can communicate with both IP version 4 and IP version 6. And another way would be through the process of translation, where we are converting one IP version 4 address into a completely different IP version 6 address. Obviously, these are stopgap measures, and they're not designed to be a long-term solution for connecting these different types of networks together. Ideally, the best long-term solution would be for all of us to move to IP version 6, and hopefully one day we'll be able to take all of our systems and be able to run them as a pure IPv6 environment. In the early days of IPv6, where we did not have a lot of infrastructure devices that understood IPv6, we did a lot of tunneling of that IPv6 traffic. This was obviously designed to be a short-term use, and these days it's not very common to still see this tunneling being used. One of these tunneling types is 6-to-4 addressing. This allows us to send IP version 6 traffic over an existing IP version 4 network. It creates an IPv6 address based on the IP version 4 address that you're currently using, but it requires you to have a specialized relay router to be able to transfer that data. And one big disadvantage of 6-to-4 addressing is it does not support any type of network address translation. Because of both those limitations and because we have more devices these days that natively support IP version 6, we no longer commonly see 6-to-4 being used, and this functionality has now been removed from all Windows versions. If you can tunnel IP version 6 traffic across an IPv4 network, you can also do the reverse with 4N6 tunneling, where we can tunnel IP version 4 traffic across an existing IP version 6 network. Both of these were used as relatively short-term solutions, and it's very unusual to find 6-to-4 addressing or 4N6 tunneling still being used on our enterprise networks. A much more common method of migration, and one you're probably using on your existing system, is dual stack routing. This allows us to use both IP version 4 and IP version 6 at the same time on the same system. You might have an Ethernet adapter on your computer, and that Ethernet adapter has both an IP version 4 address assigned to it and an IP version 6 address assigned to it.
Now that I'm a mom, things are different. Verizon's different too. They let everyone in my family choose different plans. We get what we want and we save money. Love that for me.
Your side works exactly the same as it always has, and all of your applications that use IP version 4 can use that address to be able to communicate onto the network. If you have applications that would prefer using IPv6, they can use the IPv6 addressing associated with that Ethernet adapter. These applications will use the IPv6 address that is assigned to your Ethernet adapter. It will use the routing table within your system for IPv6, which is a different routing table than you're using for IP version 4, and all of the IPv6 settings that are associated are all independent from anything that's happening with IP version 4. This tends to be a very good middle ground because our application can choose IP version 4 or IP version 6, and either one of those will work properly on the network. One of the things that we used with IPv4 to minimize the restriction that we had with IP addresses is to perform a network address translation. We would take our existing internal IPv4 address and translate that into an IPv4 address that can be routed across the internet. We can perform a similar translation to move between IPv4 and IPv6. This translation is called NAT64 and allows us to seamlessly translate IPv4 and IPv6. Just as we need a specialized network address translation router when we're using IPv4, we also need a specialized router when we're using NAT64. This allows us to take a device that communicates via IPv6, but still allow it to communicate with devices that only communicate using IP version 4. The key is in the middle, we're able to use a NAT64 capable router to make that translation change between those two protocols. This also uses a specialized DNS server to be able to translate the DNS requests from IP version 4 to IP version 6. This is called DNS64, and it's an important part of the overall NAT64 process. For example, let's say that you wanted to communicate from your device, which is an IPv6 client, and you wanted to communicate to ProfessorMesser.com. Let's assume for this example that ProfessorMesser.com can only communicate using IPv4. The first thing that happens, of course, is we need the IP address of ProfessorMesser.com, so we send a DNS request to our DNS64 server. This server is going to make a DNS request on our behalf to that IPv4 network containing the DNS server that is used by ProfessorMesser.com, and of course that DNS server is going to respond back with the IP version 4 address associated with that server. Once that IPv4 address is received by the DNS64 server, it creates an IP version 6 version of that address.
All right, everybody, let's hit up break. See you in 10 minutes.
To the IPv6 client, it thinks it's received the IPv6 address of ProfessorMesser.com, but it's really received the IPv6 address of the NAT64 router. So now when our browser needs to communicate to ProfessorMesser.com, it sends its initial send to that IPv6 address, which is the NAT64 router. That router is responsible for performing the network address translation, where it is able to take the IPv6 address that we use and translate that into an IPv4 address that the web server understands. This process is obviously reversed when the response is sent back, allowing these two devices to communicate to each other, even though one device only understands IPv6 and the other device only understands IP version 4. The routers that we use in our homes and our offices have an important job of forwarding traffic between one IP subnet and another. It's a relatively straightforward process, although there is a lot of technology under the surface that makes this happen. But if we were to look at this in a very simplified form, we could see that the router is performing a series of relatively simple steps. The first step is to identify what the destination IP address might be for incoming traffic into the router. It looks into the packet, identifies what the destination IP address is, and makes a note of where it should be sending this traffic. The router then examines some tables to determine what the best route will be for this particular packet. If the destination IP address of this particular packet is associated with a subnet that is directly connected to this router, then the router simply sends the packet onto that local subnet. But in many cases, the destination IP address is on a subnet that is not locally connected to this router. The router will examine that routing table, determine what the best next hop might be, and then send the traffic out that particular interface. This next hop is the IP address of the next router down the line, and when that router receives this packet, it performs the same process again until the packet finally makes its way to its final destination. As you can imagine, that routing table becomes very important, and when we're troubleshooting routers, we refer often to the routing table, what the next hop might be, and determining where these packets should be going once they leave our router. If a router refers to its table and does not find a next hop for that destination IP address, it will simply discard that traffic. So you can see why having a valid routing table becomes very important. Let's look at this network diagram. There are 3 separate routers in this network diagram and 3 individuals that would like to communicate with each other. In this case, let's focus on router 1. You can see router 1 is connected to 3 different subnets. We have a subnet 10.10.10.0/24. There's another subnet between router 1 and router 2 that is the 10.10.40 network, and then another subnet between router 1 and router 3, that's the 10.10.50 subnet. Those 3 subnets are directly connected to router 1, so if we were to look at the routing table for router 1, it would see the route for 10.10.10.0/24, 10.10.40.0/24, and 10.10.50.0/24, and all of those networks are locally connected to this router. The problem occurs if Sam would like to communicate to Jack. Although router 1 knows about the local networks, it has no idea that there are more networks on the other side of router 2 and of router 3. And those particular networks of 10.10.20.0/24 and 10.10.30.0/24 are nowhere in this routing table. This means if Sam wants to send traffic to Jack, Sam will put this packet out on the network. It gets to router 1. Router 1 examines the destination IP address of 10.10.20.2 and then looks through its table and realizes there is no 10.10.20 network in the routing table, and the packet is discarded and never makes its way down the network. One way that we could create a more complete routing table is to build it ourselves. This administrative creation of a routing table is referred to as static routing. And if you would like to build static routes as the administrator of your routers, then you will manually be configuring these routes inside of every router that you use. Static routing is a very quick way to configure a route inside of the router, and if you're managing a smaller network, this might be a perfectly reasonable way to manage where the routes might be. Because we're static routing, there's no overhead that you would normally see from a dynamic routing protocol. We'll talk about dynamic routing in a future video. So there's no CPU cycles, there's no memory usage. We are simply adding the route ourselves, and we don't have to do any additional processing to the routing table from there. This is very common for remote locations where you might have a single internet connection into that remote site, and all communication takes place over that single connection. We often refer to these as stub networks. And because we don't have to worry about any type of dynamic routing updates or having any changes to the router configuration because of those updates, this is a relatively secure form of routing. However, this can be challenging to configure on larger networks. Configuring a handful of routers with their own static routes is relatively straightforward. But if you're managing hundreds or thousands of routers, manually configuring a static route in each of those routers could take quite a bit of time. This also relies on you adding the correct routes to every router. There have been times when I've configured static routes and I've set up my own routing loop within my network because of a misconfiguration. And as the name implies, these routes are static. They don't change once you've configured them. So if there are changes to your network, you'll need to manually log into your routers and make those configuration updates to the routing table that match the changes to your network. This also means that there is no automatic rerouting if something happens on your network. You will need to manually configure these routes if anything needs to be routed in a different direction. So let's configure some static routes for router 1. We know that we have our 3 locally connected routes, but we also have these additional 2 routes, one that's behind router 2 and one that's behind router 3. This would be the 10.10.20 network and the 10.10.30 network. So we might SSH into router 1, and at the command line, we would begin to add additional static routes. For example, we might tell router 1 that if it receives any packet coming through with a destination IP address that matches the range of 10.10.20.0/24, then send that particular packet to 10.10.40.2. So if the packet does come through with that destination that needs to go to the local network that Jack is connected to, it will send all of that traffic to the IP address 10.10.40.2, which is located on router 2. At that point, router 2 will examine its own routing table and know that the 10.10.20 network is locally connected and send that packet on its way. We can do the same thing with the 10.10.30.0 network, so we will manually configure a static route that if any destination traffic is going to 10.10.30.0/24, then send all of that traffic to 10.10.50.2, which means all of that traffic will go to router 3. Now that we've configured those static routes in router 1, anytime those additional networks are seen as a destination IP address, router 1 will know exactly where to send that traffic.
Welcome back to the strongest connection.
With most options, I've been waiting for something special, but it's been buffering.
But underline, our connection is strong and ultra fast. This is gonna last.
Underline, local gigabit internet that loves you back.
In 16 years, Greg Gerstner will land the perfect cannonball. With friends he's already meeting now at AARP volunteer and community events to help make sure his happiness lives as long as he does. The younger you are, the more you need AARP.
Static routing requires the network administrator manually configure every route on every router in the organization. If you have 3 or 4 routers, that might not be a big problem. But if you have tens or even hundreds of routers, you might want to have a more automated way for configuring your routing tables. One way to do that is through the process of dynamic routing. Dynamic routing will have the routers handle this process for you, automatically discover these routes, and update each other as to where the best route might be. This means that you as the network administrator don't have to do any type of static route configuration. You don't have to SSH into the router, make any configuration changes, or update those routes if anything changes with your network infrastructure. Anytime you bring a new router online, all of the other routers will automatically know where the new route is, and if you happen to remove a router from the network, all of the routers also know that that route is now no longer available. There is a bit of overhead required inside of the router to be able to automatically discover these routes and update the routing tables. This will require some CPU and memory inside of the router, so you may need to do additional monitoring to make sure that your router is able to handle that load. This also requires you to initially configure the dynamic routing protocol. This may be a relatively easy configuration process, or it may require additional planning and engineering to be able to implement it properly in the config of the router. Let's look at this network configuration where we have Sam that may want to communicate across the network to Jack or to Till. You'll notice that there are 3 different routers, and for this particular example, let's focus on router 1. You'll notice that router 1 is directly connected to 3 different subnets, but there are 2 subnets on the other side of router 2 and router 3 that router 1 simply can't see. So we need some way to update router 1 with those additional routes. One way to do this would be to have router 2 send a routing update via EIGRP to router 1. Router 1 receives that update and then updates its own routing table with this new route to 10.10.20.0/24, and the way that you get to that network is to go to 10.10.40.2. We also have another EIGRP update that has come from router 3, and when that update is received, router 1 identifies a new route to 10.10.30.0, that's the subnet down at the bottom, and you can see that the next hop is 10.10.50.2. All of these updates occurred in real time behind the scenes without any type of user intervention, and if we happen to add or remove routers from this network, this routing table will be updated with an additional EIGRP update that will either add or remove those routes from the table. Although it looks relatively straightforward to perform these dynamic routing updates, there's actually a lot of work that occurs behind the scenes. First, the router needs to listen to the traffic that is on the local subnet and see if there are other routers that are sending routing updates that it can use to build its own routing table. These are very often sent directly from router to router, either directly or with a multicast. Once a router then builds its routing table, it needs to inform other routers of routes that it knows. So it will send its own multicast to other routers that are nearby, informing them of all of the routes that that router happens to know. Once the other routers receive this update, they need to interpret this information and determine if that's a better route than what they already have, or if they should use this as a secondary route. Different routing tables use different methods to make these decisions, and they will update their routing tables differently depending on the protocol you happen to be using. And of course, if there is any change to the network infrastructure, these routers need to inform all of the other routers that the change has occurred. So if we add a new link into a router, we remove a router, or we add a router, we need to make sure that all of our routing tables are updated across the entire network. There are a number of different dynamic routing protocols to choose from. So which one would be the best for your particular implementation? Different routing protocols make routing decisions in different ways. For example, would you like your traffic to be routed based on the state of the link, whether the link is up or down? Or would you like to be able to make that decision based on the number of hops that a link might be away from you, or the speed of that connection? Based on the routing protocol that you're using, that decision might be very different. Some routing protocols will use a different criteria to determine the best way to get to a remote location. You might also find that some routing protocols are able to make changes very quickly if anything happens to the underlying infrastructure. So if you add a new router to the network, it might take a number of seconds, or it might take a minute, depending on the type of dynamic routing protocol that you're using. And in some cases, we need to take into account the type of router that we're using. Some routing protocols, such as BGP and OSPF, are very common and can be used across many manufacturers' devices. Some routing protocols, such as EIGRP, may work best in a Cisco-centric environment, so if you have a lot of Cisco routers, that might be a better routing protocol for you. Although EIGRP tends to be very Cisco-centric, you may find EIGRP is also available on other manufacturers' routers. But there are some aspects of EIGRP that are proprietary to Cisco, so you tend to see it mostly in Cisco-related configurations. But one advantage of EIGRP is that it is relatively easy to set up. You would turn on EIGRP in your Cisco router, give it a few minor configuration options, and it's now up and running with the EIGRP protocol. When there are changes, EIGRP tends to converge relatively quickly, and it's also able to identify any loops and prevent those from occurring on your routed network. EIGRP is also very good at identifying other EIGRP-enabled routers and sending updates over a minimum of network traffic. This keeps your network more efficient and leaves your bandwidth available for other applications. If you want a more generic dynamic routing protocol that can be used across different manufacturers' routers, then you might want to try OSPF. This is the Open Shortest Path First Routing Protocol, and it's one that you'll find available on a number of different manufacturers' devices. This is often implemented in a network where you have complete control of those
back
systems.
from break.
We often refer to this as an AX, or an autonomous system. For example, if you're running a wide area network that has 50 different routers, those 50 routers would be part of your single
Just in case you have any
system.
questions. So Leah will be in the
Organic and dairy
A plus room, I'll be in the net plus room.
Here we go.
At Sprouts, our shelves are filled with new, exciting, and delicious discoveries. This is that Sprouts feeling.
Staying connected matters.
Hey, Mama. You remember when you taught me how to fish? Feeling a little nostalgic right now, that's all.
That's why in the rare event of a network outage, you'll automatically get a bill credit for a full day service. That's all part of the AT&T guarantee.
Another advantage of OSPF is that it's available on many different manufacturers' devices. This is a common standard, and you can download this standard from the internet and read through every aspect of OSPF. We refer to OSPF as a link state protocol, which means it determines what the best route is based on uptime and availability between the different OSPF routers. OSPFs can be used to assign costs to an individual link, so certain links may have a higher cost than another. This allows OSPF to make routing decisions based on what the least cost might be. This cost is often associated with how much throughput may be available on a particular link, if that link is up or down, and how long it takes to traverse that particular connection. With OSPF, the lowest cost and the fastest path is going to be the best route to a remote location, and if there are identical costs on OSPF, many implementations will allow you to load balance across both of those links. If you need to route traffic outside of your autonomous system to other organizations, then you might want to use an external gateway protocol such as BGP. BGP is the Border Gateway Protocol, and it's commonly used on our wide area networks and internet connections. Connecting the internet together and being able to dynamically update the routes on the entire internet is a daunting task, and this particular routing protocol was designed with this specific task in mind. Sometimes you'll hear BGP referred to as the 3 napkins protocol because it was sketched out on napkins initially to solve this particular type of problem. If your organization has one or more connections to the internet and you want to be able to dynamically route to those internet sites, then you'll want to use a protocol such as BGP. The job of a router is to evaluate incoming traffic, determine what the destination might be for that traffic, and then send it out the appropriate interface. The router is effectively determining what direction a packet might go to depending on the knowledge it has about the rest of the network. To be able to make this decision about where traffic goes, we need a routing table. And fortunately, most devices have a routing table. The workstation that you're using has a routing table, the servers that you're accessing have routing tables, and of course the routers themselves maintain their own routing tables as well. For the router to be able to make the right decision on what the best route would be to a destination, it refers to this routing table. So everything that we do when we're troubleshooting a router will begin and end with the information contained within that routing table. One thing you might even find with a router is that there may be multiple ways to get to a location, and there will be a tie as to which route a router might choose. Fortunately, there are ways to break the tie within the router, and in this video, we'll look at a number of ways that tie-breaking process might occur. Let's look at a routing table. This is a routing table I pulled from a Cisco router, but it's almost identical in form and function to routing tables that you would find in a workstation, in a server, or in any other manufacturer's router. In this particular example, this routing table was built based on a number of networks that were directly connected and routes that were received using the RIP dynamic routing protocol, specifically RIP version 2. If we look at the routing table, the top part of this routing table is a legend that gives us more information about the codes that are used within the routing table itself. In the bottom is the routing table, and you can see that the first set of letters on each one of these lines corresponds back to a different set of codes that are shown in that legend. For example, you can see the first line of this routing table starts with the letter C, which means that that particular route is directly connected to this router.
Dear Friday, let's put good times in gear. Toyota trucks.
Right now, get 2.99% APR financing for up to 48 months on Tacoma. Toyota, let's go places.
Your razor might do the job, but Gillette Labs treats my face like a passion project.
Tell them, Dad. If we want to see the route that was added using RIP version 2, then we need to find a line that starts with an R. And indeed, there is a line that has an R, which means that everything on this line was created because of information that was received by this router using the RIP version 2 dynamic routing protocol. And you can see there is a lot of information contained within this line. We can make out some IP addresses. There are different values such as 120/1, and it does appear there are even counters here along with information about specific interfaces. Let's break out just this line of information to determine what is contained within this line of a routing table. Let's break out this line of information to see which each one of these provides. We know that that first R at the beginning of the line is the route code, and if we refer back to the R in the list of codes, it does say that this was received using the RIP protocol. The next one is 10.10.30.0/24. This is the destination subnet that has been added into the routing table along with a prefix link of /24. We also have the 120/1. This is actually two different values. The 120 is an administrative distance. We'll learn more about administrative distance in a moment. And the next is a metric. We'll also talk about metrics in this video. You can also see that it's via 10.10.50.2. This would be the next hop or the destination that we would be sending this traffic if we needed to go to this particular location. We also have this time value. This is a timestamp that tells us how long this route has been active inside of this routing table. And in this case, this route has only been active for 14 seconds. And lastly, you can see the outgoing interface that would be used. Sometimes this interface is included, sometimes it's optional depending on the routing protocol or the router that you're using, but it's sometimes nice to see that this particular next hop is one that we would reach by going out a specific physical interface in that router. So when the router is making its routing decision on where traffic should go, it's evaluating everything in this routing table to determine if this would be the best possible route to use to forward this traffic along to the next hop. One of the first things that a router is going to evaluate is where this particular traffic is destined. We need to be able to look at the destination IP address and compare that to the subnet IDs and prefix links that are contained within the routing table. If there's a match, then we'll know where to forward this traffic. This means that this IP address range and prefix length becomes an important consideration when we begin to forward traffic. We need to look at both of those together to determine if this is the best possible route for this traffic. And if you were to look at a routing table, you may find that there are multiple routes listed to a particular subnet, but there might be different prefix lengths in each one of those lines. So you might need to evaluate each individual line of a routing table to determine which one is the most specific for this particular route. For example, let's say that you need to communicate with a device that's located at 192.168.1.6, and your routing table has 3 different routes that would match that particular IP address. One of them is 192.168.0.0/16, the other is 192.168.1.0/24, and the third is 192.168.1.6/32. All of these would be valid routes to that particular destination, but only one is the most specific. We need to evaluate not just the subnet ID, but also the prefix length to determine which one of these is the most specific for that particular destination. And if we were to look at 192.168.1.6, we would know that 192.168.1.6/32 would be the most specific route. In fact, that is the most specific route because a /32 is specific to an individual IP address, in this case, 192.168.1.6. Now, if this route was not in our routing table, we would have to choose between 192.168.0.0/16 and 192.168.1.0/24. The /24 is the more specific route than the /16, so we would choose the middle route if we had a choice between those two locations. This can get even more complicated if your routing table happens to have identical routes to a location that go to different next hops. How do you know which next hop would be the correct one if everything else was identical? And the one way that you would be able to make that determination is by examining the administrative distance. Different routing protocols are assigned different administrative distances within the router itself. This allows the router to pick the best route.
Now's the time to upgrade to the new Dell AI PC. It's optimized for AI workloads. An engine
based on the type of protocols or the type of information that it has received. For example, if this is a local connection, it is physically connected to the router, this is the best possible way to get to that subnet, so it has an administrative distance of 0. As you can see here, the lower the administrative distance, the better the route might be. If you have manually configured a static route, the router assumes that you must be the most knowledgeable person for that particular route, so static routes have an administrative distance of 1. If this route was added to the routing table using EIGRP, the administrative distance is 90, and if you receive this route via OSPF, the administrative distance is 110. You can see that other dynamic routing protocols and methods are listed in this table with the appropriate administrative distance for a Cisco router. In some cases, the routing protocol itself may be in a position where there might be duplicate routes to a particular location, and the routing protocol has to make a decision on where the best route might be. In that case, we will want to look at the routing metric to be able to break that tie. Routing metrics are an internal value that are used by the routing protocol itself. So BGP has its own set of routing metrics, OSPF has a completely different set of routing metrics, and EIGRP uses its own set of routing metrics as well. This means that you can't compare routing metrics across different routing protocols. The routing metrics used for BGP are very different than the routing metrics used for EIGRP, and there's no way to compare or contrast those routing metrics across routing protocols. But similar to an administrative distance, BGP might create its own set of routing metrics to a particular site, and then it can determine what the best route might be based on its own internal set of routing metrics. For example, the routing metrics for BGP might be 1 or 2. It will choose the route for 1 because that is the lowest routing metric. Let's look at our routing table for RIP version 2 again. We have that one line in the routing table, the 10.10.30.0/24. It has an administrative distance of 120 because it is RIP version 2, and it has a routing metric of 1. RIP uses the number of hops to a location as its routing metric, so we know that this particular destination is 1 hop away. To be able to reach that particular network, we would go to 10.10.50.2, and we would get to that particular location by sending this traffic out serial 0/3/1 on this router. If you were to use a different routing protocol, for example, EIGRP, you would have a very different routing metric. Here is the same routing table to the same location, but we've enabled EIGRP instead of RIP2. You can see this line in the routing table was created with the code D, and if we refer back to our legend, we can see that D does refer to EIGRP. Everything in this line is very similar to what we saw with RIP version 2, although you'll notice the administrative distance is different. It's a 90 because EIGRP has a higher priority in its administrative distance than RIP version 2, but you'll notice that the routing metric that is determined by EIGRP is very different than the routing metric that we saw for RIP version 2. RIP version 2 uses the number of hops, whereas EIGRP has a completely different calculation that it uses to determine what the best route might be. As you work more with routing tables and begin evaluating these routes on the fly, you'll become much more comfortable with determining where the best next hop might be for a particular packet. One of the challenges we have when working with routers is that there's only one best route to a different location. If you were to look at the IP configuration of your device, you'll notice that you have a default gateway. That default gateway is your local router that allows you to communicate outside of your local IP subnet. But you'll notice that there is only one IP address available to list as the default gateway. You can't list multiple gateways in that list, and this brings up a challenge, especially when you'd like to have redundant routers on a single network. One way to provide redundancy, even though you only have places for a single default gateway, is to create a virtual IP address for the router that's in use. We refer to this virtual IP as a VIP, and the idea is that if the primary router disappears, we can move that virtual IP to another router on the subnet so that you don't have to change everyone's workstation to maintain the uptime and availability of the network. This means you as the end user may have no idea how many different redundant routers might be on your local subnet. And if the primary router on your network was to fail and the virtual IP address was to move, you would seamlessly continue to have connectivity using that redundant router. Here's how this would work. You as the end user would communicate to a router or a default gateway on your network, and that default gateway gives you access to other subnets or allows you to communicate out to the internet. In this particular example, we're going to use the first hop redundancy protocol, or FHRP, in conjunction with a virtual IP address that we've associated with router 1. This is our active router. Also on the same subnet is a standby or backup router. That's our router 2. Our default gateway is going to be associated with the virtual IP address that we've got associated with router 1, and that means that all of our traffic will flow out of our network through router 1.
I didn't think that Factor could help me reach my protein goals. Boy, was I wrong. Free high protein breakfast for a year? Yeah, that's real. Every meal's loaded, ready in minutes, and tastes unreal. I don't have to track macros or plan meals. Factor does it all for me. And the breakfast, so good. These pancakes are delicious, and they're packed with protein. More protein, better food, less work. Sign up now and get 50% off your first box, plus free high protein breakfast for a year.
If router 1 was to fail, there would need to be some type of method to fail over to router 2. But router 2 has a completely different IP address. In this configuration, router 1 and router 2 are always in communication with each other, but if router 2 suddenly realizes that it's not able to communicate with the active router, it then removes that as the active router and becomes the active router itself. Then it takes control of that virtual IP address so that everyone on the network is now able to communicate out to the internet through router 2 using that original virtual IP address. All of the traffic will flow just as it normally did, and the end user has no idea that it's now using a completely different router to be able to perform that communication. Another interesting characteristic of switches and routers is that you can assign multiple interfaces to a single physical interface. We refer to these as sub-interfaces. So even though there might be a single Ethernet interface on a router, we can take that single Ethernet interface and separate it into multiple virtual interfaces. For example, we might have a trunked connection that has multiple IP subnets connecting to a single physical connection. But we may need to reference each individual VLAN in a trunk with a separate IP address on our router. We do that by assigning that physical interface with an additional parameter called a sub-interface. So although the physical interface on that router is referred to as Ethernet 1/1, we would have separate sub-interfaces within that physical interface that might be called Ethernet 1/1.10, Ethernet 1/1.20, and Ethernet 1/1.100. This means that we can set different configurations for each of these sub-interfaces so that we can reference them with the appropriate IP address for that VLAN. Here's how this would look on a network configuration. You can see there are 3 devices. All 3 of these devices are in separate VLANs. There's the red VLAN, the green VLAN, and the blue VLAN. And of course, they're connecting to separate physical interfaces on a switch. The switch then has a single cable between the switch and the router, and it's trunking each individual VLAN within that single gigabit connection. On the router side, we've configured 3 sub-interfaces for that Ethernet connection. Sub-interface G0/0.1, .2, and .3. And then we can assign IP addresses, subnet masks, and have completely different routing tables for each of these individual sub-interfaces as if they were physical interfaces on that router.
I would describe Underline as fast, affordable, and incredibly fast, very reliable, zero lag.
There are many devices connected to the internet. Some estimates are 20 to 30 billion, and by the time you watch this video, it's probably, of course, going to be more than that. One of the challenges, of course, is that IP version 4 only supports 4.29 billion addresses, and we have completely exhausted our list of IP version 4. There are no more addresses or subnets to be handed out. So now we have to find some way to communicate across the internet to these billions of devices using a protocol with a relatively few number of IP addresses. The way that we're able to make this work is through a technology known as Network Address Translation, or NAT. We often refer to NAT as being the way that we are able to extend the functionality of IPv4 and use so many different IP addresses, but NAT can be used for many different use cases. We just in this video happen to be talking about one of the most popular use cases where we are able to translate IP version 4 from a private address to a public address. If you wanted to get more details on the difference between a private IP and a public IP, you'll want to look at RFC 1918, which defines these different ranges of private IP addresses. These are IP addresses that are not routable on the public internet, so we most often use these inside of our homes and inside of our businesses, and will perform translation if we ever need to communicate out to the internet. Certain ranges of these IP addresses are probably already familiar to you. For example, one IP address range that is private is 10.0.0.0 through 10.255.255.255. In a large enterprise network, this is probably the IP address range that you're using. This RFC also allocates 172.16.0.0 through 172.31.255.255. And if you're using network address translation at home, you're probably using the IP address range of 192.168.0.0 through 192.168.255.255. So how are we able to take these private addresses, which we already know we cannot route across the internet, and somehow we are able to communicate to these internet connected sites? We are able to do this using network address translation. Let's take this example where Vala would like to communicate to the Professor Messer web server. Vala's IP address is a private IP address of 10.10.20.50, and Vala wants to communicate to a public IP address of 104.20.19.63. To follow this process, let's break these two addresses out and identify them as the source IP address of 10.10.20.50 and the destination IP address of 104.20.19.63. This packet will first hit a router that is configured with network address translation. This router knows that the source IP address of 10.10.20.50 is an internal IP address, and we can't use this IP address if we want to communicate out to the internet. So this router will change or translate that address to something different. This router already has a list of IP addresses that could be used, and in this case, it's changed that IP address to 94.1.1.1. Now we have a public IP address, so now we can communicate directly to the Professor Messer web server. For this web server to communicate back to Vala, it's obviously not going to communicate back to the internal 10.10.20 address. Instead, it's going to reverse those IP addresses, and the source IP address now becomes 104.20.19.63, and the destination IP address is the 94.1.1.1 that was originally assigned by the network address translation router. When this router now receives that packet, it's going to perform the translation again, except in reverse, and modify that destination IP address to be the internal address of 10.10.20.50, which obviously matches the IP address of Vala, and now Vala has received that message from the Professor Messer website, even though Vala has an internal private IP address. With standard network address translation, we are translating from one IP address to a different IP address. This means that if we wanted to have many people performing this translation, we would need to have many more public IP addresses available. There's a way to make this much more efficient using a different form of network address translation called NAT overload, or port address translation, or PAT. Let's take that same example where Vala would like to communicate to ProfessorMesser.com. Vala's IP address is 10.10.20.50, but you'll notice we'll also include the source port number, which in this case is 3233. The destination IP address is obviously the IP address of the Professor Messer web server at 104.20.19.63, and in this case, Vala is communicating to that server over port 80. When that packet is received by the router, it understands that 10.address needs to be translated to a public IP address, and inside of this router is a network address translation table that shows both the private address and the public address that it's translated to. You'll notice here that the private address of 10.10.20.50.3233 is converted to 94.1.1.1 with a port number of 1055. And when that translation takes place, our source IP address is now a public IP address, and that's what's received by ProfessorMesser.com. Because we're translating both the network address and the port number, other devices on this network could use the same public IP address. For example, let's take another scenario where we have Jonas at 10.10.20.70. Jonas's random port number that's used for this transaction is 5782. And of course, the destination IP address is the same as the ProfessorMesser.com web server with a port number of port 80. When that packet is received by the network address translation router, it knows that that address has not been used before, and it puts that into the network address translation table with a different port number on the public IP address side. So now we're using the same IP address of 94.1.1.1 as our public IP, but notice that the port number has incremented by 1. This means that we can now have many people on the inside of our network communicating externally to a server, all using the same public IP address.
Now that I'm a mom, things are different. Verizon's different too. They let everyone in my family choose different plans. We get what we want.
As a very broad description, a local area network, or a LAN, is a group of devices that are in the same broadcast domain. For example, when we connect devices to a switch, all of those devices are in the same broadcast domain. In this diagram, we have one switch on the left, that's our red switch, and all of the devices connected to that switch are in the same broadcast domain. On the right side is a blue network. This blue network is also on its own switch, and all of the devices connected to this switch are on their own broadcast domain. Because there are two separate switches, and these switches are not connected to each other, no one on the red network can communicate directly with anyone on the blue network. One of the challenges with this configuration, however, is that we have two devices on the red network and two devices on the blue network, but you can see that there are 24 interfaces on the front of each of these switches. This means we're running two separate switches with two separate power sources. They're both taking up space within our rack, and we have to manage each of them individually. It would be much more efficient, much easier to manage, and much less expensive if we could have all of these devices reside on the same physical switch. We can do exactly that and continue to provide that separation between the red network and the blue network on the same switch by using a functionality known as virtual local area networks, or VLANs. The red network is still on its own broadcast domain, and the blue network is on its own broadcast domain, but all of these devices are connected to the same switch. We've gone into the switch and defined each interface on the switch as belonging to either the red VLAN or the blue VLAN, and only devices plugged into the blue interfaces would be able to communicate with each other, and only the devices plugged into the red interfaces would be able to communicate with each other. Instead of colors, VLANs are defined by number. So in this switch, we have a VLAN 1, a VLAN 2, and a VLAN 3. We can see that there are devices that are connected to interfaces that are configured for VLAN 1, other devices connected to interfaces that have been configured for VLAN 2, and still other devices that are configured for interfaces that will only communicate on VLAN 3. This becomes a bit of a challenge when you want to connect VLANs across individual switches. For example, you have two switches in this scenario. One of the switches has a VLAN 100 and a VLAN 200, and the other switch also has a VLAN 100 and VLAN 200. We would like for VLAN 100 on one switch to be able to communicate with VLAN 100 on the other switch and perform the same functionality for VLAN 200. Of course, one of the ways we could do this is to simply connect an Ethernet cable between VLAN 200 on both switches and connect another Ethernet cable between VLAN 100 on both switches. You can tell, however, that we're going to run into problems if we want to connect 10, 20, 100, or even 1,000 VLANs across both of these switches. We can't connect 1,000 interfaces across each of these, so instead we should find a way to connect these switches together by using a minimum of physical connectivity. We can do this by implementing a VLAN trunk. This is also referred to as an 802.1q trunk or a .1q trunk. Instead of having these multiple Ethernet connections between VLANs, we have a single Ethernet connection between these two switches, and you can see that we've configured that interface as a trunk interface. This means that anything sent from VLAN 100 or VLAN 200 across this trunk will be dropped off onto the appropriate VLAN on the other side. So how is the trunk connection able to keep track of what traffic is coming from VLAN 100 and what traffic is coming from VLAN 200? The way we do this is by tagging each frame. This is a normal Ethernet frame. We have a preamble, a start frame delimiter, a destination MAC, a source MAC, a type, a payload, and a frame check sequence. To be able to add additional tags into this frame, we're going to add an additional field right in the middle, right after the source MAC address, and we refer to this as the VLAN tag. These VLAN tags are 12 bits long, and if we're not counting the VLAN numbers that are reserved, we can have a total of 4,094 VLANs that can traverse that trunk connection.
This is the Dell AI PC, built for AI. It was designed to optimize your battery life, so it works longer without a charge, and in places without a charger.
This makes the process relatively easy for connecting these VLANs together between switches. Instead of having 4,000 physical interfaces that we are connecting to each other, we have a single interface, and we're simply tagging all of the data sent over that connection. Before there was an 802.1q standard to provide this trunking functionality, there was a proprietary form of trunking known as ISL, or Inter-Switch Link. ISL is relatively outdated at this point, and it's likely that any trunk that you'll ever run into will be an 802.1q standard trunk. Let's see how these trunks will use that tag functionality to be able to transfer data from a VLAN 200 on one switch to a VLAN 200 on the other switch. We'll start with a normal Ethernet frame from a device that is connected to an interface defined as VLAN 200. This packet needs to find its way to a device that is on the other switch on VLAN 200, so that packet will be sent to the trunk interface on the switch. At that time, an additional tag will be added that includes the VLAN 200, and it is sent across that trunk connection to the other switch. The switch that receives that frame will look at the tag, see that it was destined for VLAN 200, it will remove the tag from the frame, and send that traffic to the end station. So now we have a much more simplified design. Instead of having a separate cable that's running between switches for VLAN 1, VLAN 2, and VLAN 3, we can have a single Ethernet connection between those two and simply trunk all of the traffic between those switches. When you first configure a switch, there will be a default VLAN for this switch. That means that every device you connect to this switch by default will be connected to a VLAN. Very commonly, this is VLAN 1 that is defined as the default VLAN. But there's another type of VLAN configuration that you would have inside of a switch known as a native VLAN. A native VLAN is one that can traverse a trunk, but a VLAN tag is not added to any of the traffic going over that trunk connection. So it's common to define a single native VLAN within a switch that will never be tagged as that traffic is sent over that trunk connection. This is because there are some devices that will not communicate over an 802.1q network, and some of the administrative functions within your switches, where switches are communicating with each other, may need to use the native VLAN to perform that communication. For example, management traffic or switch notification messages may use the native VLAN rather than being tagged as a separate VLAN inside of that switch. If you're defining a native VLAN on one switch, you'll need to make sure that that native VLAN is identical on the other switch that you're connecting to. Otherwise, you'll see error messages appear in the log of your switch. Up to this point, we've been describing a traditional layer 2 switch, that is referring to the OSI layer 2 or data link layer, where switches make their forwarding decisions based on the MAC address of an Ethernet frame. But there's another type of switch known as a layer 3 switch that's able to make forwarding decisions based on the OSI layer 3 or network layer of an IP packet. This is looking at the destination IP address and making a routing decision on where that traffic should go. You're effectively taking switch functionality at layer 2 and router functionality at layer 3 and combining both of those into the same unit. With the layer 3 switch, we're not changing the switching process. The switch is still operating at layer 2, And we're not changing the way that a router operates. The routing functionality within this device is still operating at layer 3. But both of these are now combined within the same device, saving space, saving power, and making the administration process that much easier. This means that we can have layer 2 functionality within our switch where we might have separate VLANs within the same physical switch. But now we can also have routing functionality that allows us to route between those VLANs all within the same switch. This means that we'll need to configure interfaces inside of the switch that are designed to route from one VLAN to another. We refer to these as SVIs, or Switched Virtual Interfaces. If you have a layer 3 switch, it may not have the layer 3 functionality turned on by default, so you may need to enable that in your switch configuration. Many switches require you to restart the switch once you make that configuration change. And you may be thinking, why don't we use layer 3 switches for everything? Instead of having 2 separate physical devices, it seems that having one single physical device would be much easier to manage. And in many cases, that's true, but the routing functionality of a layer 3 switch tends to be less capable than the routing functionality of a standalone router. There is a term within the industry where we tell the switch needs to switch and a router needs to route. When you start combining those devices together, you begin to lose functionality. So if you have a smaller remote site or perhaps even an internet router at home, you might have this layer 3 switching functionality to be able to route and switch within the same device. It's very common on our corporate networks to need both data functionality for our computing devices and voice functionality to be able to make telephone calls. Before the days of voice over IP, we would need to run one cable for our Ethernet network and a separate cable for our telephones. Our Ethernet cables would connect to a switch, and our telephone cables would connect to a PBX, or a private branch exchange. With the advent of voice over IP technologies, we can get rid of that individual voice cable completely and run both voice and data over the same Ethernet connection. And in many enterprise environments, you have a switch that is on the network, you have telephone that you would connect to the switch, and on the back of the telephone is an additional Ethernet cable where you can plug in your local computing device. One of the challenges that comes with adding both voice and data to the same network is that you now have a great deal of contention between both of those technologies. Data likes to use a lot of bursty bandwidth on the network, but voice communication prefers a very consistent level of access. If there's any type of congestion or a lot of usage on the network, this could affect the voice over IP communication, and none of your phone calls would sound very good. To resolve this issue, we can put our voice communication on one VLAN and put our data communication on the other VLAN. But of course, we're using a single wire to connect both our phones and our computers, so we can use VLAN technologies to do that within that same cable through the use of trunking. This requires you to use a switch that will recognize that you're connecting both a phone and a computer at the same time, but once you're using the right equipment, this becomes a relatively straightforward process. So now with this switch configuration, we can assign our phones to be VLAN 200, assign our computers to be VLAN 100, and send all of that traffic to our switch, where it will be able to break those two apart and put them on the correct VLAN for that particular use. This means we can now download as much information as we'd like from our computer while we're on the phone communicating with others and be able to perform both of those seamlessly.
Wait, is this you when trying to build a website? Because I got you.
Oh, check out Blue. They have an AI site creator that makes it a breeze.
When you're configuring a router interface, a switch interface, or an interface that's in your local computer, there are a number of options available. In this video, we'll look at some of those interface configurations. We can start with the basic connectivity that we have to the network. When we plug in an Ethernet cable, there are a number of Ethernet settings we need to consider, and two of the most important are the Ethernet speed and the duplex. The speed is obviously going to be how fast this connection is going to run. This might be a 10 megabit connection, 100 megabits, 1000 megabits, which would also be 1 gig connection, 10 gig, or even faster. We have to be sure that this configuration is the same on both sides. So if we have a computer that's connecting to a switch, the speed on both of them has to be configured the same. In many cases, we would set this to automatically configure itself. So you can simply plug in any device and the switch will automatically adjust to the configured speed. The other option we might have available is either half duplex or full duplex. In most cases, this is also set to automatic, but if you do set these manually on both of these devices, you have to make sure that both of them are set to be the same. If you have the speeds mismatched on both sides, the connection will not work at all. You'll never get a link light. But if you mix the duplex configuration, where one side is set to half duplex and the other side is set to full duplex, you'll find the connection does operate, but you'll notice that it is not quite as efficient as it should be. And in fact, you'll have very poor performance if you start putting a lot of traffic over that link. This is why one of the initial configurations we'll look for when we're troubleshooting Ethernet is the speed and the duplex and make sure that they're the same on both sides of the connection. If those match, then we'll shift our focus to the Internet Protocol or the IP configuration for that interface. This might be an Ethernet connection, it might be a VLAN config, we might be setting up management interfaces, and all of these will need an IP address, a subnet mask, a default gateway, and perhaps other IP configurations as well. These will usually be values that have been assigned by a network administrator. So we'll want to configure and make sure that the IP address, subnet mask, default gateway, DNS settings, and everything else matches the configuration that we've received from our admin. If this configuration doesn't match what we've been given, let's say we've used a different default gateway IP address, or we put in the incorrect subnet mask, then we may find that we're not able to connect to other IP devices on this network. Fortunately, this is a relatively easy configuration to validate. We can simply look at what we've been given and look at what we've configured in the system and make sure that both of those match. Another useful configuration, especially between switches, would be one for link aggregation. This is sometimes referred to as port bonding, or you might see it abbreviated as LAG for link aggregation. This means that we are connecting multiple interfaces together on these two devices, which normally we would not want to do because we would be creating a loop. But if you've configured all of those interfaces as link aggregation, the switch will interpret them as one very large connection rather than 4 individual connections. So if all 4 of these were gigabit Ethernet connections between this switch, we would configure those as lag, and you now have 4 gigabits of throughput to be able to communicate between those two devices. Some switches will support an automatic configuration of this link aggregation using a protocol called LACP. This is the Link Aggregation Control Protocol. This allows you to simply configure the interface as LACP, plug in the interfaces, and all of the underlying link aggregation configs will automatically configure themselves between those two devices. If you were to capture traffic between these two devices, you would see LACP traffic being transferred from one switch to the other. To be able to have the most efficient communication from one device to another, we need to be able to send packets across that will not be fragmented along the way. Since we don't always know what networks are located between the two devices, there may be times when our data is fragmented and therefore is less efficient to transfer across the network. Fragmenting a packet tends to slow down the overall communication, and if we lose one of those fragments, then we have to resend the entire frame again. Normally, the determination of the most optimal MTU, or maximum transmission unit, is done automatically when you first connect to a device. But sometimes filtering and firewalls won't allow the automated process to work properly, and you may need to manually configure an MTU on your system. On some networks, we're not trying to minimize the size of our communication. Instead, we're trying to maximize the size of our frames. And one of the ways we can do that is through a method called jumbo frames. Ethernet frames by default are 1,500 bytes in length. If we're transferring large amounts of data, we may want to increase the size of those frames to make the communication that much more efficient. And with jumbo frames, you can increase the size of an Ethernet frame up to 9,216 bytes of an MTU. On many devices, you'll find that they'll use 9,000 as the accepted high end of a jumbo frame. fact, here is the configuration from my computer that says that I can configure frame sizes on my network to be between 1280 and 9000 bytes. This means I can transfer a single frame that contains the same amount of information as 6 normal frames on the same network. This means there are fewer packets to have to switch or route through my network, and I can transfer much more in a shorter amount of time. The challenge, though, is all of the devices that are in that communications path must understand jumbo frames. So all of your switches, all of your routers, and the other devices you're communicating to have to also be configured to use these jumbo frames. If there's any device in the middle of this communication that doesn't understand jumbo frames, then they will drop these frames and you won't be able to communicate to that device at all.
Your workflow is important to us. Please wait indefinitely.
With Monday.com's intuitive work management platform, you have the power, not.
If you had 2 switches and you connected them together with an Ethernet cable, and then you connected another Ethernet cable to those switches, you would create a loop on the network. This means an Ethernet frame would loop around that particular connection until you disconnected one of those cables. There's no mechanism at the MAC address level to count how many times you've seen a frame. So as these frames are going around this loop, you're adding more and more frames to the network all the time. Those are continuing to go around this loop, and eventually you'll overwhelm the capacities of your switches. This can happen relatively quickly. Once you create a loop in a network, it might be a number of seconds until people start calling the help desk stating that the network is down. Fortunately, this is relatively easy to resolve. You simply go back to the switch where you plugged in that cable, you disconnect the cable, which removes the loop from the network, and now everything is back up and running. But of course, we're not always standing in the data center ready to plug or unplug a cable from a switch. We need some type of automated method to recognize a loop on the network and to prevent those loops from occurring. Fortunately, we have a standard that's able to recognize and prevent loops on a network. This is the IEEE 802.1d standard, one that we call the spanning tree protocol. Spanning tree can configure interfaces on our switch in a number of different ways. It may configure the switch port to be blocking, which means it's not going to forward any traffic. This is commonly used to prevent loops on a network. If we were to plug in that second cable to our switch, Spanning Tree would recognize that a loop was being created, and it would cause one of those interfaces to be in a blocking state. The listening phase is used by Spanning Tree to clear out existing tables and restart the process. It's going to go through a learning process where it listens to understand where all of the other switches might be and if there might be any loops on the network already running. And then it will configure an interface to be forwarding, which means traffic can be transmitted through that interface, or will configure an interface to be blocking. We might also have interfaces that are administratively disabled. Those obviously would not participate in this spanning tree process. Here's a network that is already running spanning tree, and there are a number of switches. They're identified as bridge 1, bridge 6, bridge 5, and so on. You can see there are 5 of them in this particular design, and you can see that many of these switches are connected to each other, and if we didn't have spanning tree running, there would be a loop on this network already. But on this network, we already have spanning tree that's operational, and it has configured a number of different interfaces. There are 3 different types that you can see on the screen. One is the root port, or RP. This is the interface on a switch that is connected ultimately to the single root bridge on the network. There's also a designated port, which would be any other port that can forward traffic, but is not the port that is connected directly to the root bridge. And there are blocked ports. These are ports where Spanning Tree has disabled that port from sending or receiving any traffic. You can see on this network that bridge 21 has a blocked port and bridge 11 has a blocked port, and those have been blocked so that there is not a loop on the network. If we were communicating from bridge 11, you can see there's a single root port, and you can follow that all the way back with those root ports to the final root bridge. The designated ports are also available to be able to send and receive traffic. In this scenario, let's say that we're on network A and we've been communicating with a device on network M. You can see that we can communicate through bridge 6, which has a designated port and a root port that allows us access to network M. But what if there is a problem on this network and we lose connectivity between network A and bridge 6? Now we need some other way to communicate to network M, but as you can see, there is a blocked port on bridge 11, so we would not be able to communicate through that connection. Fortunately, Spanning Tree recognizes that we have this disconnection, and it begins clearing out the existing configuration and relearning the topology of the existing network. Spanning Tree has changed bridge 5 so that the root port is now on the other side, and it has removed the block port on bridge 11, allowing us on network A to be able to now communicate all the way through the network back to network M without having another loop on the network. On many networks, we do talk about enabling Spanning Tree and making sure that our Spanning Tree configuration is turned on inside of our switches, but in reality these days we're probably running a newer version of Spanning Tree called the Rapid Spanning Tree Protocol. This standard is the 802.1W standard. In the original Spanning Tree protocol, it might take 30 to 50 seconds for the convergence process to occur. And on today's networks, that is a very long time to wait without any type of connectivity. With Rapid Spanning Tree Protocol, this convergence process goes down to about 6 seconds, which means anytime there's a disruption on the network, we can be back up and running relatively quickly. Fortunately, this Rapid Spanning Tree Protocol is backwards compatible with the original Spanning Tree, so if you have a mixed set of devices on your network that support one or the other standard, you can run them all at the same time. Fortunately, Rapid Spanning Tree Protocol works very similar to the original Spanning Tree configuration. It simply operates much faster. There are some shortcuts and other configuration settings within the Rapid Spanning Tree Protocol, but it has such familiarity that if you understand Spanning Tree Protocol, it will be very easy for you to understand the details of Rapid Spanning Tree Protocol.
Staying connected matters. Hey, Mama. You remember when you taught me how to fish? Feeling a little nostalgic right now, that's all.
That's why in the rare event of a network outage, you'll automatically get a bill credit for a full day's service. That's all part of the AT&T guarantee.
With the Amex Gold Card, every meal is a reward, earning you 4 times membership rewards points at restaurants and U.S. supermarkets. That's an opportunity in every bite, sip, slice, and scoop. Whether you decide to stay in or go all out. Earn rewards on everyday meals with the Amex Gold Card.
We've become so accustomed to wireless networks being available that we often forget that there's a lot of work that happens behind the scenes to create these wireless connections. This work is done primarily by the Institute of Electrical and Electronics Engineers, or the IEEE. There's a committee in the IEEE called the 802.11 Committee, and that is the committee that focuses on creating worldwide standards for wireless networking. In the past, we've referred to the standards name to be able to describe the network. For example, we'll describe 802.11ac, 802.11ax, or 802.11be. The IEEE committee realized that these numbers and letters combinations weren't very appealing for most people, so they've also assigned separate names that are a little easier to keep track of. For example, 802.11ac is Wi-Fi 5. 802.11ax is Wi-Fi 6 and Wi-Fi 6E, the extended version of Wi-Fi 6, and 802.11be is also called Wi-Fi 7. As additional major releases of the 802.11 wireless standards are released, they will also increment those Wi-Fi numbers, so in the future we should see Wi-Fi 8, Wi-Fi 9, and so on. There are a number of technologies used by 802.11 wireless networking, and the first is the frequencies that are in use. 802.11 commonly uses 2.4 gigahertz, 5 gigahertz, and 6 gigahertz frequency ranges. Sometimes there's a combination of those. You may have an access point that supports both 2.4 and 5 gigahertz, and some access points may support all of those frequencies at the same time. Instead of having to memorize individual frequency numbers, the IEEE has created groupings of these frequencies known as channels. These channels help us easily understand what frequencies we may be using. For example, on this access point, we're using both the 2.4 gigahertz range and the 5 gigahertz range.
All right, if
The
you need to take your
2.4
last break
gigahertz
of the day,
range
go
is
ahead and
using
take it.
channel 6, which is centered on 2.437 gigahertz, and the 5 gigahertz band is using channel 44, which is centered on 5.220 gigahertz. You can see that referring to this as channel 6 is much faster and more efficient than saying that this particular access point is centered on 2.437 gigahertz. The amount of frequency that we use is referred to as the wireless bandwidth. And when I say that channel 6 is centered on 2.437 gigahertz, there's actually more frequencies that we're using for that single channel. Different frequency bands have different sizes of bandwidths that can be used, but it's very common to see 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz bandwidths. Here's a diagram that shows the 2.4 gigahertz range, the 5 gigahertz range, and the 6 gigahertz range that's used by 802.11 wireless networks. We'll start with the 2.4 gigahertz spectrum. You can see there are 3 non-overlapping channels in that particular range, and it's using the 20 megahertz bandwidth to describe those 3 channels. Next is the 5 gigahertz spectrum, and you can see there are many more frequencies available in the 5 gigahertz range. You'll also notice that we might use different bandwidths depending on the access point that we're using. So we might use anywhere from 20 megahertz to 160 megahertz, and you can see the ranges that are available for those particular frequencies. And in the 6 gigahertz range, we have even more frequencies available, giving us options to be able to transmit and use these wireless networks without conflicting with other wireless networks that might be nearby. As you can tell, there are many frequencies available to choose from for your wireless networks, but not every frequency is going to be the best one to use. There may be differences in the environment where you happen to be, where one frequency might work better than the other, or there may be other access points that are already using certain frequencies. You might also be using older devices that aren't able to communicate on the 5 or 6 gigahertz ranges and may only be able to communicate on 2.4 gigahertz frequencies. But if you have a modern wireless device, you might have options. Your phone, for example, may be able to support 2 or more different types of frequencies. It just needs to be able to choose the optimal frequency for where you happen to be. Your access points can be set up with a feature known as band steering. This allows you to specify how the users might be able to use the frequencies in the best possible way. For example, you might have a user that has a mobile phone, and that phone can support either a 2.4 gigahertz connection or a 5 gigahertz connection. And you might have access points that also support both of those frequencies. So which frequency does your phone choose when it's connecting to that access point? If band steering is not configured in the access point, the device will simply use the one that has the best possible signal. Sometimes that best signal will provide you with the best throughput, but that's not always the case. And you may find that you get better throughput using a different frequency, even though that frequency may not be the one that has the strongest signal. If band steering is turned on, the administrator of the access point can determine what frequency a user will choose if they have a choice. For example, if a user is connecting to an access point with band steering enabled, and that device can support either 2.4 gigahertz or 5 gigahertz, you can force it or steer it into using the 5 gigahertz frequencies by default. One of the challenges with these wireless networks is that each country makes its own decisions about how this wireless bandwidth is to be used. For example, in the United States, we have the Federal Communications Commission, and they are responsible for managing all of the frequency allocations in the U.S. Of course, the FCC can't control how other countries manage their frequencies, but they do work very closely with other countries around the world to make sure that everyone is properly managing these very important frequencies. Another challenge with this is that we are coming up with new technologies and new ways to use these frequencies all the time, and we sometimes have to make sure that different services can use similar frequencies without any type of conflict. The popularity of these wireless networks has almost required that all of these countries work together to come up with standards that everyone can agree on. A good example of these organizations working together can be found in the 802.11h standard. This adds a number of interoperability features to 802.11 wireless networks so that you can have many different wireless networks in one area, but still allow all of those networks to work together. There are a series of guidelines for wireless communications that are published by the International Telecommunications Union. The ITU provides a worldwide approach to managing these many different wireless technologies. One of the things that is included in these standards is called DFS. This is Dynamic Frequency Selection. This allows our wireless access points to use frequencies that are not going to conflict with other access points that may already be operating. This is one of the reasons that when you turn on your wireless access point today, that you don't have to manually configure any of the wireless settings inside of that device. It automatically looks at the frequencies that are in use and chooses a series of frequencies for you that are not going to conflict with anything that may already be operating. And if something does change with the wireless environment and your access point needs to change its channel, it will tell all of the devices on that network to also move along with the access point. Another interoperability feature is TPC, or the Transmit Power Control. Traditionally, we've set the power that we would use for these wireless networks on our clients, but TPC puts the transmit power control in the hands of the access point. This means that the access point can tell a client to use less power to be able to communicate over this wireless network. This means that we can have many devices communicating at their optimal power level without having any type of conflict with other third-party services.
This is the new Dell AI PC, built for AI. It's like a trusted personal assistant. Learning your habits, keeping you on track.
When we think about wireless networking, we often think about connecting to an access point. But of course, you can communicate directly to another device without an access point. We refer to this as Independent Basic Service Set, or IBSS. You might also see this referred to as an ad hoc connection. This allows us to configure one device as an ad hoc connection, configure the other device as an ad hoc connection, and simply connect those two devices to each other over those wireless frequencies. You might have used this functionality when you've configured an Internet of Things device, such as a door lock or lights in your home. This is a way to connect to a device over an ad hoc connection, provide that device with information about your existing wireless network, and then have that device connect directly to the access point. And in most environments, we have an access point that many different devices are connecting to be able to network everyone together. Behind the scenes, we're using different parameters to configure this device. Two of those parameters are the SSID and the BSSID. SSID stands for the Service Set Identifier, and it's the name of the wireless network that we're connecting to. So you might have an access point with an SSID of SGC1, and when you bring up the list of all of the available access points in your area, you will see that SSID name appear in your list of available networks. Of course, this same SSID might be configured on multiple access points, especially if you have a very large home or you're in an environment where there are multiple areas of the building and you want to have wireless connectivity wherever you might be in that building. To be able to differentiate between one access point and the other, we need some type of hardware address on that access point, and that hardware address is known as the BSSID. This is the Basic Service Set Identifier. So although there is a wireless network name that we see, such as SGC1, there's also a hardware address that we normally do not see behind the scenes. In this case, this wireless access point has a BSSID of 603 Delta 26112233. As we've already mentioned, in your home or a very large business, you may have tens, hundreds, or even thousands of access points to manage. All of these access points need to be able to work together so that as you are passing from one building to another or from one area of the building to the other, you're able to seamlessly move from one wireless access point to the other. This is often done by using the same SSID or wireless network name on each of the wireless access points. We refer to this shared network name that's used across access points as an ESSID. The E stands for the Extended Service Set Identifier. With the ESSID configured across all of these different access points, you can start on one end of the building, walk to the other end of the building, and you will be moving automatically and seamlessly from one access point to the other. Here's a configuration that uses ESSID to provide that seamless roaming from one access point to the other. In the middle at the top, we have a network switch. This switch has an Ethernet connection to an access point on the left and an access point on the right. And you can see that the BSSID, or the Basic Service Set Identifier, which is the hardware address of the access point, is different on this access point than it is for the other. Although these are obviously two different pieces of hardware, they are sharing the same SSID. You can see it's configured as SGC1 on this access point. It is also configured as SGC1 on the other access point. As we move outside the range of one access point and move into the range of another access point, that access point will automatically pick up that we are nearby and seamlessly connect this device to that same SSID without any notification on your mobile device. This means you can continue to surf the internet, transfer files, and use the network normally, even if you happen to be moving at the same time. When you first connect to a wireless access point, you may be prompted with a screen that gives you information about the network or requires you to authenticate to gain access to that network. We refer to this screen that appears and the prompt with the authentication credentials as a captive portal screen. For this captive portal to work, there is a centralized access table that identifies individuals that are already authenticated to the wireless network. And if it notices there's a new device that has not previously authenticated, it will present this captive portal screen to the end user. On the captive portal screen, there may be a series of terms that have to be agreed to, or it may prompt for a username, a password, or some other type of authentication factor. If those credentials are entered properly, then that information is added to the access table, and you gain access to that wireless network for a predefined amount of time. For example, your captive portal may be good for 24 hours, and at the end of that 24-hour period, you have to re-authenticate to gain another 24 hours of access. There are many different ways to configure security on a wireless network. And if you look at the configuration of your access point, you may find that there are a number of different options that you could choose from. For example, on this access point, the security level is currently defined as WPA2 personal. This access point can also disable security. It can configure a security mode on this access point known as OWE, which stands for Opportunistic Wireless Encryption, which effectively allows someone to connect to the wireless network but prevents them from communicating directly to any other wireless device. This access point also supports WEP, different flavors of WPA, WPA2, and WPA3. An open system, of course, means there is no security. There is no authentication process, and anyone on this wireless network can communicate to anyone else on this wireless network. This access point supports WPA, WPA2, and WPA3 using a personal type of security. Sometimes you'll see this referred to as PSK, which stands for pre-shared key. This means to gain access to this wireless network, we need to provide someone with a pre-shared key that everyone will use. For example, you may be at a coffee shop and there may be a notice at the coffee shop that the pre-shared key that everyone can use to access the network is hot coffee. Of course, if you're in a business environment, having everyone share the same password for the wireless network is inherently insecure. So most enterprises will use a different type of wireless security known as
When Verizon gives you a free phone on any plan, you use AI a lot.
Gemini, show me the concealer. The long, thin tube in the middle.
But hey,
a username, password, or some other type of authentication to gain access to the wireless network. And most people will use their own personal credentials to be able to provide that access. This means you would use the same username and password you would normally use to log into other devices in that same enterprise network. This means if someone leaves the organization and their account is disabled, they no longer have access to that wireless network. If you look at the different antennas that are used on many of today's wireless networks, you may notice a number of different styles. The style of antenna that you see connected to this access point is an omnidirectional antenna. It's a very common antenna type to find on our consumer or home-based access points. An omnidirectional antenna will evenly distribute that wireless signal on all sides of the antenna. So you can put your access point in the middle of the room, and everyone in the room will have the same signal strength as everyone else. This means you can put your access point in a centralized area, and anyone who's nearby will be able to gain access to the wireless network. But this may not be the optimal antenna type to use. For example, your access point may be in the corner of an outside room, and you're effectively only seeing a portion of that signal, while the rest of it on this omnidirectional antenna is sent to places where no one will ever connect. In that scenario, you might want to use a directional antenna, where you can take that wireless signal and send it into a single direction. This allows you to focus the transmission and receiving of wireless signals to a device that may be in the corner of a room or may be connecting different buildings to each other. You'll often see these antennas measured as a total number of decibels. For example, a directional antenna may increase the performance of that signal by a certain decibels of gain. For example, you may see in the specifications of a directional antenna that it effectively increases the overall power by 3 dB. And for every 3 dB, we are effectively doubling the amount of power available. One type of directional antenna is a Yagi antenna. This is an example of a Yagi antenna. It is very directional and has a very high amount of gain. We also have other directional types, such as a parabolic antenna, where multiple signals can come in and bounce into a single feed horn in the front, so it's focusing all of those signals into a single point on the antenna. This is especially useful over longer distances where you need to collect that signal and focus it into a single spot. Most of the access points that we use at home are autonomous access points. This means that the access point doesn't require any type of additional hardware or software to be able to operate. It's effectively a standalone device that doesn't rely on anything else to be able to maintain that wireless connectivity. But in an enterprise, you may not be using autonomous access points. Instead, you may be using lightweight access points. This separates the wireless functionality into the hardware that you would mount into the ceiling, and the configurations and intelligence of that device are often maintained on the switch the access point is connected to. This not only allows us to have less expensive access points that we can deploy, it also gives us functionality for being able to manage those devices. One standard for managing wireless access point is known as CAPWAP. This is control and provisioning of wireless access points, and it allows you as the network administrator to manage and configure all of these wireless access points from one central management station. We refer to this central station as a wireless LAN controller, and allows us to connect and view the entire wireless infrastructure from one single screen. We often refer to this as a single pane of glass. From this single management station, we can deploy new access points. We can monitor the performance of our existing access point infrastructure. We can make changes to the configuration of our wireless network and deploy those changes to some or all of our access points. And this might also create reports showing us how much of the wireless network is being used and by whom. This wireless LAN controller is often paired with the wireless access points themselves, so you're often getting the access points and the wireless management station all from the same manufacturer. There are a number of different ways to connect and configure wireless networks, and in this video, we'll look at some of these different wireless network types. One popular wireless network type, especially in home-based environments, is a wireless mesh. This is where you would have multiple access points that can all communicate to each other within a relatively close area. And then you would have other devices that are located on the outside of those access points that are able to communicate to that single access point and ultimately to the rest of the network. This meshing of access points in the middle is something that you would configure on the access point, and if you were to add additional access points onto this network, they would also be included in that same mesh of access points. Of course, this doesn't have to be access points. There are some devices that can mesh amongst each other in an ad hoc form. This allows for different options for sending data over these networks because all of these devices are now communicating to each other. And if one device leaves the network, it can automatically identify that that device is no longer there and self-heal itself to maintain connectivity to everyone who's left on the wireless network. If you only have two devices, you might want to connect them together without an access point. We refer to this type of connectivity as an ad hoc connection. This is where you would use the 802.11 wireless functionality of your device, but you would not be directly connecting to an access point. This uses the 802.11 wireless network functionality of this device, but instead of connecting to an access point, you simply connect to the other wireless device. You might also see this referred to as an independent basic service set, or an IBSS. This might be something that is a very long-term connection. If all you have are two devices, you can simply connect those two together and they will communicate as long as that connection is available. But you might be using this on more of a temporary basis. This might be used in conjunction with an Internet of Things, or IoT device, where you would initially connect to the IoT device over an ad hoc connection. This may allow you to transfer configuration details, such as the name of your larger wireless network and any security configurations that have to be included to connect to that wireless network. At that point, the ad hoc connection is then disabled, and the Internet of Things device can connect to the larger access point network using those configuration parameters. Some wireless access points allow you to connect two devices directly to each other over a point-to-point mode. The point-to-point mode is commonly used to connect larger distances to each other. For example, one building connecting to another building. I've run this exact configuration between two homes, so you could have an access point in one house connected to a switch and all of the internal devices of that network connected to the same switch, and then you would have the same configuration in another home and have all of those networks now connected to each other over that point-to-point mode. Not all access points support this point-to-point mode, so you'll want to be sure that the software of the access point supports point-to-point, and you'll want to be sure that the hardware on this device is also able to transmit over that extended distance. You may, for example, require additional types of antennas to be able to bridge that gap between the access points. There might also be a requirement to change the power output between these two devices and to make sure you're using frequencies that are able to communicate over that longer distance. And perhaps the most common way to connect to a wireless network is in something called infrastructure mode. This is where you would have a centralized access point, and this is probably the type of wireless networking that you're using at home and in your office. All of the wireless devices in your home or office connect to that central access point, and you're able to communicate out to the wired network or between other wireless devices over that same access point. Some wireless access points give you the option to allow devices to communicate with each other over that wireless network, or to isolate each of these wireless devices to only be able to communicate directly to the access point and any networks beyond that access point. You'll want to check your access point to see how it's configured for these devices and make sure the proper security is configured on that device.
I would describe Underline as fast, affordable, and local. Incredibly fast, very reliable, zero.
The wireless networks we use both at home and in our businesses are sending private, confidential, and sensitive information all the time. And we're very concerned that someone might have access to that data, especially on a wireless medium that effectively could be tapped into and listened to by any device that happens to be nearby. One way that we provide security on this wireless network is to limit what users are able to access the network. We would commonly do this with some type of authentication method, such as a username, a password, or some type of multi-factor authentication. And of course, we want to be sure that everything sent over this wireless network is protected, so we need to add confidentiality in the form of encryption. And to be sure that we've received the correct information over this wireless network, we include a message integrity check so that we can verify the information that we've received is exactly the information that was originally sent. One of the first encryption types on wireless networks is a method known as Wired Equivalent Privacy, or WEP. Unfortunately, WEP was discovered to have some significant cryptographic vulnerabilities, so we needed to very quickly replace WEP with something that was much more secure, and that replacement was known as WPA, or Wi-Fi Protected Access. WPA was implemented as a temporary stopgap between the insecure WEP and a more secure version of WPA. This first iteration of WPA was designed to work on exactly the same hardware as that older style WEP that we were replacing, but we knew that we would need enhanced security that we would not currently have available in this initial WPA. This replacement to WPA we named WPA2. This is Wi-Fi Protected Access version 2, and it's a version that's been around since 2004. You'll often see WPA2 referenced with a block cipher mode known as CCMP. If we were to spell this out, it would be counter mode with cipher block chaining message authentication code protocol, or counter/CBC-MAC. This effectively combined encryption and integrity in the same protocol. The encryption was available with AES, and the message integrity check was enabled using CBC-MAC. The update to WPA2 is WPA3. This is Wi-Fi Protected Access version 3, and it was introduced in 2018. This includes a different and more capable block cipher mode known as GCMP. This is Galois Counter Mode Protocol. This continues to use AES for data confidentiality, and we are using a message integrity check with the Galois Message Authentication Code, or GMAC. If you're planning to implement any type of security on your wireless network, you want to use the highest level of security available in your access points and on your client devices. And if you have the option, you should consider upgrading all of your devices to use the most capable security method available.
Known for building special bonds. No one wants to be known for cancer, but
A distribution frame is an area of the network where you are passively terminating cables. This usually involves punch-down blocks like the ones we see here, could be patch panels, or any other method where we are terminating those cables, usually in a data center or some other large facility. You will usually find this distribution frame on the back wall of the data center, and it's often terminating cables that are coming in for your local area network and voice communication. And although the punch-down blocks and patch panels that we have on the wall are technically the distribution frame, we often refer to the entire room as the distribution frame room. For example, the primary distribution frame is called the main distribution frame, or MDF, and we often refer to the entire room where it's located as the MDF facility. The MDF is usually a single room. It's often the data center or central point of the network, and this is where we might bring in wide area network connections and punch those down, along with all of our internal local area connections as well. Since we have all of this connectivity in one place, it is a perfect testing point, especially if you need to test both your internal local networks and your external wide area network connections. And even if your network doesn't have this large set of punch-down blocks in the back, we sometimes even often refer to this central data center room as the MDF. Here's a view of one MDF. This one contains a number of different racks with computer equipment and the networking components as well. Here's another MDF. You can see a large number of punch-down blocks or patch panels that are on the single rack and some on individual racks as well, and it's intermixed with the equipment that we need to run inside of this data center. Another type of distribution frame is the intermediate distribution frame, or the IDF. Usually the IDF is in a separate floor or a separate building, and it's often directly connected to the MDF. Most IDFs these days include switches, routers, and other equipment that you need to be able to connect this area of the network to the larger MDF. You usually find this combination of MDFs and IDFs in medium to larger scale environments where you need to have many different remote rooms all connecting back to this central data center. Here's a view of what that would look like, where you have the MDF. Maybe this is where our internet connection comes in. There might be a core router and a core switch. You might even have file servers and database servers in the MDF. Maybe on different floors of the building, you would then have individual IDFs. In this case, there are two, but there might be more than that in this particular environment. And in the IDF, you might be connecting users on the floor to a central switch in the IDF, and that switch is connecting back to the main core switch in the MDF. We've already seen an example of an IDF and MDF, and one of the things that you'll notice is there are racks that are very common in each of those environments. That's because the racks that we use in these environments are standardized, and most rack sizes are 19-inch racks. They're 19 inches across in each of these, and we design our equipment to fit perfectly into that 19-inch width. You also notice that the equipment in these racks might also have different heights, and we have a standard for those heights known as a rack unit, or a U. One U would be 1.75 inches, and we can measure a different number of units based on that value. So you can easily tell somebody that we need 2U or 3U of space to be able to install a piece of equipment. And most racks, like the ones we see here, are generally about 42U in height. Although the width is standardized, the depth of these racks can often vary. There might be racks that are very shallow, or others that might support a much longer piece of equipment that you would install. Fortunately, most devices follow this standardized form. We know that if we're receiving a piece of equipment that is rack mountable, that it will most likely be 19 inches wide. We'll just need to make sure that we have a rack that is deep enough to handle that particular piece of equipment. Since we have these standard widths, we can start stacking this equipment and using every bit of real estate that we might have available. For example, this system administrator has installed a server that's about 3U in height, and they're installing another set just above it so that they can stack them one right on top of the other. Now that we have all of this equipment in the data center and it's all running constantly, it's creating quite a bit of heat. We need to make sure that we have a way to cool this data center so that all of this equipment continues to work optimally. We would do this by implementing an HVAC or HVAC system. This stands for heating, ventilating, and air conditioning. This is very different than simply purchasing a window-mounted air conditioner and turning it on. There's a lot of engineering that goes to designing and implementing an HVAC system in these large data centers. For example, we not only need to make sure that the HVAC can support the amount of heat that's going to be created by these systems, we also need to make sure we have enough power to run the HVAC, and we also need to make sure this is integrated into the fire system so that we're able to turn this off automatically if a fire is detected. One thing that you'll notice in a data center is that the different aisles of the data center may be designated as a hot aisle or a cold aisle. This hot and cold aisle is an important designation, especially as we're installing new equipment into the data center. We want to be sure that we're installing the equipment in a way where the hot air is being blown into the hot aisle and it's pulling in cold air from the cold aisle. Here's a cross-reference of a data center. On the left and right sides, we have our HVAC system, and in this particular environment, the cold air is going under the floor and the hot air is being pulled out of the ceiling. The cycle starts with the HVAC creating the cold air, and that cold air is going underneath the floor in this raised floor environment. There are vents and holes in the floor that will allow the cold air to flow into a cold aisle. This is often the front of the servers, and the servers are pulling in that cold air to cool the inside of the server itself. Once that air is heated up, it will be sent out the back of the server into a hot aisle, and that hot air is going to rise into the ceiling, where it will then be pulled back into the HVAC, recooled, and the entire system repeats again.
Now is the time to upgrade to the new Dell AI PC. It's optimized for AI workloads and engineered for the future. So no matter what's next, you're ready.
Here's a data center where we can see both the hot aisles and the cold aisles. You'll see the cold aisles are covered with this plastic to keep that cold air inside, and the hot aisles would be the ones on the outside without the plastic. You'll also notice this is a bit different than the previous diagram because there is a concrete floor and there's no way to have a raised floor in this environment. So it looks like they're blowing the cold air directly into the cold aisle from above. It's being pulled through into a hot aisle, and then it goes back into the ceiling where the entire process repeats. When we install network cabling, one of our goals is to not move or touch that cabling again. We want to be sure that once it's installed, we can trust that that cable will always be working optimally. One of the things that we'll commonly do is have all of the desks that are on a floor of a building all have single runs of wire all the way back to an IDF. Inside of the IDF closet, we'll have a patch panel, and commonly we might have a patch panel with a 110 block where we will punch down those wires onto the back side of the patch panel, and on the other side of the patch panel will be the traditional RJ45 modular connectors. This means that if we need to connect any user on the floor to any switch on our switches, all we have to do is run the appropriate cable from the RJ45 connector. We no longer have to touch any of the cable that's running from the back of this patch panel to the end user's desk. So we can begin installing all of the connections we need through these patch cables from the patch panel itself into the switch that we might be using. This also allows us to address any type of moves, adds, or changes. If someone out on the floor moves to a different desk, we can simply move where their patch cable happens to be and plug them into a different connection. And of course, if we hire new employees and we want to make sure that they have the correct network connectivity, we don't have to run additional cables because we've already run those cables. All we have to do is add new connections from our patch panel to the appropriate switch connection. Here's what this patch panel looks like in our IDF. You can see on this side of the patch panel, we have the RJ45 connections, and we're coming out of those RJ45 connections and we're plugging them into the switches that are directly underneath. This means we can keep all of those cables in place between the patch panel and the desk out on the floor. All we have to change are the internal connections inside of our IDF. Here's another view of a patch panel. This one is connecting from the patch panel directly to the switch that's above it. And notice there are numbered connections on that patch panel, so we know exactly which desk we're connecting or disconnecting. There are similar but slightly different configurations for fiber optics. This is a fiber optic distribution panel where we're bringing in fiber runs from another building or another floor, and we're bringing all of those back to connections that we have access to on the distribution panel. One of the important characteristics when installing fiber optics is making sure that we don't exceed the bend radius. And you'll notice in this distribution panel that we are looping together in a very large loop the fiber to make sure that we don't break the fiber by bending it too far in the panel itself. And it looks like in this distribution panel we have some additional fiber that is wrapped around. We refer to this as a service loop, so that if we need to move this distribution panel or add additional fiber, we can simply extend it with the fiber that's already run. This gives us flexibility in the future to be able to make changes without having to rerun a very expensive fiber optic connection. In some of the previous pictures of the data centers, you saw that some of the racks were open, but there were some racks that were completely closed that had locks on the front of the rack. This is not uncommon in any type of data center because it allows the system administrator a level of additional security and control over the components inside of the rack. We'll often install these racks side by side directly to each other to optimize the space that we have in the data center. And it's not unusual to have a door on the front of the rack where we can have a lock and a way to prevent others from gaining access to the equipment inside of the rack. Here's a good example of racks that are completely locked up. You can see in this case that we do have ventilation in the front. There's often ventilation in the top and the bottom as well, so that the equipment inside is able to be cooled properly. Here's a closer view of these racks. You can see that each of these racks has a handle with a lock on it, and you can see where you would add the key to be able to gain access to the equipment that's on the inside.
Nature's Bounty. Nature's Bounty supplements your journey with advanced menopause.
In this video, we're going to talk about power, and an important thing to remember is that you should never put yourself in a position where you will be able to in some way come in contact with any type of voltage. You want to be sure that when you're working with the device that you are always disconnecting from the power source before ever putting your hands or any part of you near that particular component. Even when you disconnect from the power source, you should also keep in mind that some devices will store a charge in capacitors. Older CRT monitors, laser printers, and other devices can easily shock you even when they're not connected to a power source. Your goal should never be to connect any part of your body to anything that could potentially be energized. For example, you should never connect yourself to the ground wire of an electrical system or anything else that might have some type of voltage go across it. If you respect electricity, you will have no problems keeping yourself and others around you safe as you're working on these devices. When you start looking into the electrical specifications and the design of electrical systems, you'll see a lot of different terms being used. One of those is an ampere. We often refer to this as an amp, and it's often abbreviated with the capital letter A. This value measures the rate of electrons that are moving past a particular point in a single second. You'll often hear electricity compared to a water hose, where electricity flowing through a wire is very similar to water that may be flowing through a water hose. The amount of water that you can fit through a hose will depend on the diameter of that hose, and the diameter would be the number of amps. We also measure electricity in terms of voltage. This is often abbreviated as volt or the capital letter V. This is describing a pressure of electricity flowing through a particular wire. If we go back to our hose analogy, as we are turning the water on, we are increasing the amount of pressure of that water through the hose, and as we increase the pressure, we are increasing the voltage. For example, you'll often see electrical systems described as a 120 volt system or a 240 volt system. And if you need to describe how much power is being used, we would describe that as a number of watts. You'll often see this abbreviated with a capital W. We can calculate watts by multiplying the number of volts times the number of amps. For example, if you're connected to a 120 volt power source and you have a device that is using 0.5 amps, you are using a total of 60 watts. The type of power that we usually get from our wall outlets is alternating current, or AC. AC power is relatively easy to distribute over long distances, so it is perfect to use for bringing into a home or an office. You'll often see alternating current abbreviated as AC, and it's often represented as the wavy line. This wavy line demonstrates the directional change of this power as it's moving through the wire. That up and down frequency of that wave is different depending on where you happen to live. If you're in the US or Canada, we commonly see 110 to 120 volts of alternating current, and it's usually running at a frequency of 60 hertz or 60 cycles per second. If you're in Europe, it's common to see 220 to 240 volts of AC current, and its frequency is 50 hertz. Our electrical components often use DC power to operate. This is direct current, where all of the current is moving in a single direction with a constant amount of voltage. This is often abbreviated with a DC, and the symbol for direct current is this solid line on top with the multiple lines across the bottom. This is why when we look on the back of our routers, our switches, and our other devices, we often see that we're plugging into a wall outlet with this alternating current, and we are converting that alternating current to direct current using the power supplies that are in those devices. This conversion may be occurring in power supplies built into the device, or it may be in the power cord that you're using to connect that device. And obviously, as an information technology professional, power is one of the most important components we have. None of these systems would work without this power source, so it's important to consider how our switches, our routers, and our other devices will continue to operate even if there's an interruption of that power. One way to protect yourself against a power outage is to use a UPS. This is an uninterruptible power supply. This is usually a device that is connected to our power source, and inside of this device are a number of batteries that provide us with additional power if we lose that main power connection. This can also help if the voltage on our line tends to drop a bit. We refer to that as a brownout, And if the voltage tends to spike or go much higher, we refer to that as a surge. UPS will even out that particular surge or brownout and provide us with the power we need to remain up and running. There are a number of different types of uninterruptible power supplies. One of the least expensive are the offline or standby UPS, which is simply waiting for the power to go out before it kicks in. As you can imagine, there's a small amount of time where there would be no power available to your systems, and often with switches and routers, that small gap of time is enough to cause that device to reboot. One step up from that is the line interactive UPS. If you happen to have brownouts and your voltage begins to drop, the line interactive UPS will begin to increase the amount of power provided to be able to compensate for that drop. But many data centers prefer to run an online or double conversion UPS where you are always running from battery power and the batteries are constantly being refreshed by the power source. If you lose the power source, it has no effect on the systems that are connected to the UPS because they've always been running from that primary battery power. There are many different types of UPSs with many types of features. There are some that can automatically shut down your system if the batteries happen to become very low. Some of them have a higher battery capacity than others. The number of outlets on the back of the UPS can vary, and some of them have additional interfaces to plug in phone lines or cable modem connections. Another useful power component is a PDU. This is a power distribution unit. And although it looks like a normal surge suppressor, these are actually relatively intelligent devices that allow us to remotely connect to the device, manage each of those interfaces, and even allow you to power off and power on a device from a remote location. You can see this one is a rack mountable unit, and we would put that in our rack and connect our routers and switches to these interfaces. There's also an Ethernet connection. We would assign an IP address to this device. Inside is a web server, and that allows us to connect and manage this device from wherever we happen to be.
Staying connected matters. Hey, Mama. You remember when you told me how to fish? Feeling a little nostalgic right now, that's all. That's why in the rare event of a network outage, you'll automatically get a bill credit for a full day service. That's all part of the AT&T guarantee.
You have design samples and a vision for your brand. Now all you need is a website to match your hustle. Well, I recommend starting with Bluehost.com. Just type in what your business is.
In the United States and indeed around the world, we have many different data centers that are operating 24 hours a day, 7 days a week. It is estimated that approximately 2% of all U.S. power consumption is used by these data centers. Much of the power we use in these data centers is to manage the environment where all of this equipment resides. This allows us to manage the humidity, the temperature, and other environmental controls. Managing humidity in a data center can be a bit of a challenge. If you have a high humidity, then you've got condensation, and having any type of water in a data center is never a good idea. If your humidity is too low, you could have excessive static discharge, which is also potentially harmful to the equipment. Many industry guidelines put the ideal humidity levels somewhere around 40 to 60%. This is high enough to prevent any type of static discharge, but low enough to prevent any type of condensation. This can vary a bit depending on the geography, but these humidity levels tend to be the average that you'll find in most data centers. A lot of this power also goes to keeping the data center cool. As this equipment is running, it's generating heat, and all of that heat needs to be cooled down. There is an optimal temperature range, and many data centers are trying to keep the temperature somewhere around 64 to 81 degrees Fahrenheit. The cooling equipment in our data centers is constantly working to keep the temperature at that range. But of course, there are external influences that can affect the temperature inside the building. For example, the outdoor temperature may increase or decrease, and that may add additional load to the cooling systems. You might also find that as your system load increases and you're creating more heat from the systems inside of the data center, that we will need to add additional cooling. Most data centers will have a well-engineered heating, ventilation, and air conditioning system. This is an HVAC. This HVAC system is designed to maintain a particular humidity and temperature level Most of these HVAC systems have sensors that are located throughout the data center, and they're working to make sure that the same temperature and humidity is the same across the entire data center. Another important concern for data centers is what you do if there is a fire. Data centers contain a large amount of electrical equipment that are in a very large area, so we need to be sure that we have some way to suppress any type of fire. Normally, we would use water to be able to control a fire. But in an environment such as a data center, when you have this much electrical equipment, you'll want to use other means for fire suppression. If you were to look into the back of the data center, there's probably a tank that contains some type of inert gas or chemical agent that is designed to either suppress the fire or remove any type of oxygen from the air. If somebody pulls the fire alarm, all of those chemicals are dispersed throughout the entire data center, and although this may cause damage to the equipment, it will prevent a fire from spreading. You'll often see these fire suppression systems integrated with the existing HVAC. This means that if a fire is detected, the HVAC system will shut down and prevent any type of oxygen from feeding that fire.
Welcome back to the strongest connection.
With most options, I've been waiting for something special, but it's been buffering. But Underline, our connection is strong and ultra fast. This is gonna last.
Underline, local gigabit internet that loves you back.
How long do I have to wait?
We are almost there.
Your favorite shows are now on Hulu and Disney Plus,
Heard you were having a party.
so you can keep up with new episodes and entire seasons.
Showtime. 911.
One common type of network documentation is the network map, and there are different types of network maps that you might want to create. One type is a physical network map, which shows the physical layout of the equipment, the cabling, and everything in between. This is an example of a physical network map. It shows a connection in from the internet with the physical cable plugging into the internet router, which can be found at 10.1.1.1. There's a physical wire connecting to the internet firewall, and then another wire connecting to the core router, which is located at 10.1.10.1. This physical connectivity continues on through the rest of the diagram, and if you were to go into this room, you could track back that cable to this equipment using this physical network map. We can often create these network maps using third-party software such as Visio, OmniGraffle, Glyphy.com, and many others. This software can be used to create physical network maps. It can also be used to create logical network maps. Logical network maps show a higher level view of connectivity where you're not focused on individual.
All right, everybody, we're getting toward the end of the day. We got like 5 minutes
more on
left.
how the entire network is connected.
So just do a quick recap. Today we learned about VLANs, VLAN tagging, which is 802.1q. You'll see that. Trunking,
This are a number of routers,
right?
switches, and other
Black
servers.
P.
But all of that
And we
is
saw a
roughly
great
shown
example,
as
which you
a
might see
single
on the
location
exam, as far as a big giant PVQ, right?
These might be good maps
With
to
like
use
4
if you're
switches, a
planning
core
additional
switch at the top,
locations.
and then distribution
Use the layout
switches
of
on
the
the
existing
next level.
binary network cloud, and then decide
And
where
that
the
how
best
important it
location
is to
might
set
be
that
for
up,
another
enable the
installation.
port, LAC P, link aggregation control protocol of 2 switches need redundancy on 2 ports to move data, right, and all that good stuff. And if something's sitting on another VLAN that you need to use as a resource, you have to tag that port that you are on with those different VLANs in order for you to go play in their backyard, right? So those are the important things that you learned today. Ciphering always comes into play. It's always good to go over that. 'Cause the more and more we do it, I can see everybody, pretty much 95% of everybody's understanding ciphering, if you look at it. In some way, somehow, even if it's a piece, you're understanding it. Like, oh, I get what's going on.
Yeah.
There's little stuff we can brush up around the edges, but that's key. All right, so keep asking those questions. I'd like to give a shout out to Leah for hosting that 1201, 1202 recap, just being available while I went to the Net Plus room. Now listen, I asked her, nobody made her do it.
Another
She's like, this is good practice if I can explain and help my classmates. So I'm just glad she did it. So if anybody else wants to host, you can too. But she said, hey, let me go ahead and do it. So shout out to Leah. But if you want to do that too, hey, feel free. I try to open them up on Tuesdays and Thursdays for like 45 minutes. You know what I mean? Give everybody a chance to do it. What else?
And you can see that each drop for each one of these
Man, we just done rock today.
This allows you to correlate the network
We learned something else today.
at each individual
Did
desk.
we watch the video this morning?
Drops that are connected to the
What was that about?
inside of the wiring closet. These are not just useful during the installation
Except one
process,
channel.
but they're also useful.
Yes! How can I forget that? That's the most important.
Wire was run inside of the building.
Yep, routing.
Okay, three quick questions, and I know you'll knock them out of the ballpark. It's about routing.
You can also.
Which two routing protocols are for Soho? Primarily that you'll see.
So routing protocols, it'll be.
One deals with IPv4, one is IPv6. One is version, there you go, bam.
RIP 1 and RIP 2.
As we escalate and more devices come on the network to control traffic, what is the other routing protocol, which is a link state routing protocol that you would use for enterprise? What y'all say? What y'all say?
Link state protocol.
Charles got it. OSPF. When we're doing OSPF, since it's a lot of network stuff happening, what are a couple of things that's taken into account when finding the fastest or better route?
The path number.
Since it's a link state protocol?
What is it? The
Yep, Michael Starner's got the answer. She's yelling it out right now.
path number.
OSPF. LSA, that is the key thing. Link state advertisements, which tell what? Remember, I do that little 5'9" router, black hair, right? So what is the advertisement saying to the other routers and switches?
Yeah, path number.
The link state, what is it saying?
Path number. All right. Broadcast ID.
How about bandwidth, delay, congestion, and how long it's going to take to get there? Right, comes into account. When you're talking about RIP and RIP version 1, version 2, hot count, 15, max, bam. If you don't get there in 15, you're dead. And what's the last one for the World Wide Web that they use? BGP. There you go. Public address is being used on the World Wide Web. Everything's being moved around, and then you're looking at your ISPs. Good job, everybody. Any questions for me today? All of y'all rock. That's what I got to say. If there are no questions, as I do every class, Brian, with the drone over my house. Hey, Brian. Skibby hip and doodaloo. Till tomorrow morning.
I'll see you guys in the next one.